One of our goals in this learning path is to analyze our data in order to extract meaningful insights. Before we get to that, however, let's put this analysis phase in the correct context by exploring the various phases of data analysis and the different roles which are involved. Let's take a look at what exactly Power BI is, and if you have covered the first learning path in this journey, specifically prepare and process data in Power BI, you will be familiar with this definition. Power BI is essentially Microsoft's business analytics service, and it includes data visualizations, a variety of business intelligence tools, as well as the ability to compile visualizations into reports, which allows end users to get insights from data. And now let's zoom in on what exactly business analytics means in this context. So this is where we look at past data about a business or organization, which could also be a government, for example. And the goal is to extract insights from this data. Have their revenues increased or decreased in the past year? What are the employment numbers like across various sectors of a country's economy? Once these insights have been obtained, well, the end goal is to be able to apply the insights and then drive business or policy decisions. For example, should a company open up a new factory in a particular region, or should a government offer incentives to a specific industry? Such big decisions need to be backed up by data, and this is what Power BI can help us with. But the process of business analytics involves multiple steps. Here are just a few of the important ones. First of all, we need to identify the sources containing the data which we need. What is a trustworthy source for employment figures, for example? That information will then need to be loaded into Power BI, and it is very rare that the data can be used directly. Some transformations will need to be performed, and this will enable correct analysis, and then modeling the data correctly can also help the visualizations perform in an optimal manner. Beyond that, it is also important to choose the right visualizations themselves. If we want an industry-wise breakdown of employment numbers, we may use a column or bar chart. Or if you want to analyze market share in a specific industry for a number of companies, a pie or donut chart will be more appropriate. In the end, it's not one, but a collection of visualizations which will need to be compiled into reports and dashboards. You can think of visualizations as individual pages or chapters in a book, a report being the book itself, while the dashboard is a summary of the book. The reports and dashboards are meant to be analyzed, and for this, they will need to be shared with a number of end users. In this learning path, we will be focusing on the last three of these points, with a specific focus on the advanced analysis features available for certain Power BI visuals, which are also crucial to understand for the DA-100 certification exam. Before we move on, let's quickly visit the difference between business analytics and data analysis, since we will often run into these two terms in the context of Power BI. Well, essentially, these two terms are used interchangeably, and for many individuals, there is no difference between these terms. However, in some cases, business analytics focuses on the business end of data analysis. This will involve exploratory data analysis and also extracting insights from visuals, and not on loading, cleaning, and transforming data. With that said, let's now focus on the different phases in analysis. So, we typically start off with gathering the requirements for the data. What exactly is the goal for the end users? If they happen to be the upper management of a manufacturing company, do they wish to know whether to build a factory in a particular state? Or do they want to know whether to switch the suppliers of certain raw materials? Based on these requirements, we will need to identify where exactly the appropriate data can be sourced from, and then following that, we will also need to figure out how to manage that data in the long term. Do we store it in a relational or NoSQL database, or do we simply store it within flat files? And then we move on to cleaning and processing the data, which will include applying a variety of transformations so that they can be used in visualizations. And then comes the phase of exploratory data analysis. This is where we would play around with the data and a number of visualizations to figure out exactly where the insights can be gathered. Again, sticking to our example where the management needs to figure out whether to open a new factory, we may use column charts to point out that sales are very high in specific regions, but profits are relatively low. And a waterfall chart could be used to convey that a bulk of the expenses are related to transportation. Once these visuals are compiled and then communicated over to the end users, they can decide whether to open up a new factory in a region in order to cut down on the transportation costs. Now, again, the emphasis of this learning path is on these last two phases, where we perform some exploratory analysis with a little help from Power BI's own built in analytics tools, and then communicate the reports by setting the right permissions on workspaces in the Power BI service. So, from the different phases in data analysis, let's take a look at the different individuals or the different roles involved in this particular process. There is, first of all, a data analyst who you can think of as pretty much a jack of all trades. Someone who is very similar is a business analyst, but with more focus on the business end of things. Then there is a data engineer who focuses more on managing the data and making sure it is ready for visualizations. This overlaps a little bit with the role of a data scientist who will also perform some exploratory analysis. And then there is a database administrator whose task is quite specialized and manages the databases where the information is stored. Let's put these roles in the context of the different phases of data analysis. So here we have the 5 different phases in pretty much chronological order. So a data analyst will pretty much get involved in each of these 5 phases. You can think of this as a very general purpose role, but keep in mind that the definition of each of these roles varies with each organization, or perhaps even within teams of a large organization. As for a business analyst, well, focus on the phases which are highlighted in an orange color. So these include requirements gathering, report development, and report communication or sharing. So business analysts will work with the business users to figure out what data is required, how exactly they would like reports to be compiled, and then finally on sharing those reports with them. As for data engineers, they will ensure that the data is in a form which can be used in visualizations. So they will need to model the data correctly and in an optimal manner. And then they will also need to clean and transform the data so that meaningful visualizations can be created from it. Moving along then to the role of a data scientist. This is an individual who is more concerned with data processing and also building the reports. This is a role we will be focusing on throughout this learning path, where we perform exploratory analysis of the data to figure out what data and visuals are the most meaningful when it comes to extracting insights. And finally, there is the database administrator. As mentioned, this role is quite specialized and comes under the purview of data management. So a DB administrator will make sure that the data is available to the required users and that data access is smooth and reliable. This could involve managing relational database management systems as well as the servers on which they run. And to wrap up this video, let me emphasize that it is these last two phases, specifically report development and report sharing, which is the emphasis of this learning path. More specifically, some of the advanced analysis features when it comes to building reports, and then communicating the reports via Power BI Workspaces. While in the previous video, we covered the different phases in data analysis, we will now dig a little deeper into two of those phases, which involves analyzing and sharing data and how Power BI fits into the picture there. So, these are the 5 different phases which we took a look at, and we also discussed that developing reports and the sharing of reports is what we will focus on in this learning path. But as someone who wishes to become an expert in Power BI, it is important to recognize where exactly these phases fit in when working with this business analytics tool. So, you will be familiar with the fact that there are various components of Power BI, beginning with the Power BI desktop, where reports are essentially developed, and then we publish these over to the Power BI service. And this is where reports can be viewed and also shared with other users. In fact, once a report is published to the service, these can also be made accessible via Power BI apps. Depending upon the types of visuals used, Power BI apps may either give you a full picture of the data or give a quick summary before more detailed analysis is performed on the service. With that said, let's now explore the life cycle of a Power BI report and how the different components of Power BI feature here. So, we start off by building a report using Power BI Desktop. For this to happen, data will need to be loaded and processed before visualizations are built from it and compiled into reports. Next, the report can be published to the Power BI service. This is where sharing of the reports enters the picture, and you could share the reports with other collaborators who can help you develop your reports further, or you could also just share it with the end users directly. It is expected that end users will take a look at and interact with the reports from the Power BI service, though they may also do the same using the Power BI mobile apps. Though, of course, interactions may be a little more constrained on this platform. In this learning path, though, we will focus on the Power BI desktop and the service. With that said, what exactly is involved when it comes to analyzing data from Power BI desktop? Well, first of all, we need to keep in mind exactly what the end users need from the data. While this may seem rather obvious, it is important to know that the end users may not have the same technical ability as a data analyst, and they may want to work with visuals focused on a specific portion of the data, which is more relevant when it comes to making business decisions. So, as a data analyst, you will put yourself in the shoes of the end user and then perform some exploratory data analysis to figure out if there are any useful patterns or insights which can be extracted. Revisiting the example from the previous video of a manufacturing company which is looking to set up a new plant, you may use visuals to explore the sales and profits in those regions where a manufacturing plant currently exists versus those where there is no plant set up yet. If there are differences, well, these can be thought of as interesting insights. Such insights, however, are easier to obtain if the right set of visualizations are used. The goal is for the end users to gather as many insights as possible without spending way too much time playing around with the visuals. So, in this regard, picking the right visualizations becomes crucial, as does picking the right set of visualizations which convey a meaningful story. So, you may choose two simple visualizations rather than one complex one in order to convey the same bits of information. So, this is how the Power BI desktop can be used in order to perform some exploratory analysis and then come up with a final report. And then this report can be published over to the Power BI service. So, this is where the data is ready to be shared either directly with the end users or with some other collaborators who may help you with further development of the reports. In either case, the report will need to be published over to a workspace in the Power BI service. From the reports in a workspace, it is possible to compile dashboards which essentially summarize the contents of one or more reports. So, a workspace essentially serves as a container for reports and dashboards. And then a workspace can also be translated into an app which is eventually shared with end users. We will delve into what exactly apps are in the Power BI service a little later. But once we have our reports, dashboards, and apps, these can be communicated with other collaborators if further development is needed, or just given over to the end users. So while the Power BI desktop can be used to perform exploratory data analysis, it is the service where the final analysis is performed as well as the sharing of reports. With that said, let's take a look at some of the crucial components of the Power BI service. And these are terms which you will need to know like the back of your hand for the DA-100 certification exam. So, reports and data sets which are created in the Power BI desktop can be published to a workspace in the Power BI service. Following this, a dashboard can be created from one or more reports, in essence, to summarize them. And once reports and dashboards are ready to be shared, well, this can be accomplished by means of an app. So, a workspace still represents a point where some development work is performed on reports and dashboards, while an app is when it is ready to be shared and interacted with by the end users. One more component of the Power BI service, which we will explore in depth, is a pipeline. This essentially allows us to put a Power BI workspace through three different stages: development, testing, and production. Alright then, so we now have an idea of the different components of the Power BI service and how Power BI desktop and the service feature in data analysis and sharing. So now, let's look at analyzing data from a slightly different perspective, that is, in the context of the precise steps involved and the features of Power BI which can be used. So the goal, of course, is to extract meaningful insights from the data from which business decisions can be made. And for this, we will need to make use of various visualizations and then analyze our data to see if anything meaningful can be gathered. So we may use pie charts, map charts, and so on to see if there are any interesting patterns which are visible. And in Power BI, we can also make use of a variety of AI related features which are available in order to help us extract these insights. For instance, Power BI line charts include an anomaly detection tool, and scatter charts have a way for us to identify clusters in the data. So it's not just the visualizations themselves, but also these features which can help us gather these insights. Furthermore, we can also perform some formatting at the visualization level. For example, we can group various categorical values into our own customized groups, or even transform numeric fields into categories using the concept of binning. These will be covered in depth in the course Extracting Insights from Data using Power BI, coming up next in this learning path. It is keeping these features in mind where we can make the selection of the right set of visualizations to convey a story. So, if you'd like to perform a forecasting on time series analysis, you should consider Power BI's line chart. Of course, extracting the right insights from the data means that we need to interpret it in a certain way, and this is where we really need to understand exactly what our end users require to help them with their decision making. Going back to our example, if the end users need to figure out whether to open up a new factory or two, while performing exploratory data analysis, we will need to consider data related to regions where there is a factory and those where there is no factory at the moment. Of course, coming up with the right interpretations will require some degree of domain or business knowledge. As a data analyst, you are not expected to understand the business inside and out. However, some idea of what the business seeks to accomplish with the data is crucial. This, of course, means that you need to think from the point of view of your end users before you apply your technical skills in order to build your reports. Speaking of which, let's get down to some of the mechanics of building reports so that your end users are able to extract the most amount of information with the minimum amount of time spent. For this to happen, you will need to ensure that your visualizations as well as slicers are distributed meaningfully across the pages of your reports, and that you give thought to how exactly visual formatting and themes are applied. The goal is to make sure that your reports are not too noisy. The themes and formatting are a means to extracting insights from the data and not an end in itself. And it is also crucial that you keep the performance of your visualizations in mind, especially when working with very large datasets or when you use the direct query storage mode. Power BI includes a very useful performance analyzer tool in order to help identify potential bottlenecks in performance in your reports. So at this stage, While keeping the end users in mind, you have built meaningful reports, which means that the next step is to publish these reports over to the Power BI service, more precisely to a workspace in the service. As mentioned earlier, you can think of a workspace as essentially a container holding reports, datasets, as well as dashboards. You can set up a workspace to include collaborators who may have view or even edit permissions on your reports. And then, of course, you may also set up one or more dashboards in order to summarize the contents of your reports. So at this point, we've come to the sharing phase of data analysis. But there are, of course, different degrees of sharing, which brings us to the various roles in a Power BI workspace. The simplest of these is a viewer who has the ability to view your reports and dashboards and also interact with them. And this is also the only role in which row level security applies. This is also the role which you're most likely to apply to the end users or consumers of your report. Then there is a contributor role, and this is for someone who plays a limited role in report development. So, such a user has the ability to add, modify, or delete reports and datasets from within a workspace, but cannot create or update an app. That is something which a member of a workspace can do. So, this user can do pretty much anything with a workspace except delete a workspace or add administrators. And of course, the admin can do pretty much anything with a workspace. And finally, let's explore what exactly is meant by an app in the context of Power BI. So this is very closely related to a workspace because each workspace essentially maps to a single app and vice versa. However, you can think of a workspace as where you share your reports in order to collaborate with other developers and maybe even testers. It is once the reports are all ready to be shared, is that an app is created out of it, and that is what is given out to the consumers. We will explore apps in more detail in the course Sharing Power BI Reports and Workspaces later on in this path. We will now explore various features available in the Power BI service and how these can be managed in order to develop and share reports. So far in this course, we have covered the fact that the Power BI service can be used to collaborate with other users when it comes to building our reports, and also to communicate them with the end users. And in this regard, we cover the different degrees of permissions which can be assigned at the workspace level. Those workspace level roles are important to understand correctly from the point of view of the DA-100 certification. But beyond that, what they emphasize is that report development in Power BI is not that different from application development with any programming language, where you might have different types of developers, reviewers, and testers. Once we think of report or Power BI app development as any other kind of software development, well, you will know that it is important for us to streamline this process. And this is what Power BI helps us accomplish by means of pipelines. Beyond that, once our apps have been shared with the consumers, Power BI also helps us monitor its usage to understand how exactly our audience is working with the data, which pages of our reports are being viewed, and who exactly is looking at them. So now that we know that Power BI apps can be thought of as any software applications, well, you will recognize that this can help by going through a process of development, review, and testing before it is finally shared with the consumers. In order to go through these various stages, it does help if we have separate environments for each of them. This will also mean that we can assign different permissions for each environment so that developers can access the development environment and make changes to reports. Testers have access to a separate environment with their own sets of permissions. All of this is made possible by means of pipelines in Power BI, which allow us to configure development, test, and production stages in the lifecycle of a Power BI app. Each of these three stages will map to a separate workspace, and this can really streamline the lifecycle of an app. To see how, let's explore the different stages of the pipeline, starting with the development stage. So this is where we will have a separate development workspace where we will have the ability to design and compile reports. Development work is usually done by a team of individuals, which means that the various developers will need to be assigned the right degrees of permissions in the development workspace. This could be as members or contributors, or even as administrators if needed. Once the development team is done with compiling reports, well, they can publish the workspace over to a test environment. This is where the workspace is effectively mirrored in a test workspace containing the same datasets, reports, and dashboards. However, it is at this workspace level where testers will be given permissions to ensure that the reports and dashboards are compliant with the business requirements. This can include checking for the user friendliness of the reports, that is, that they are intuitive and easy to interpret, and also that they perform well with large volumes of data. Any changes suggested by the testing and review team can be done in this environment, and following this, you may consider the app ready to be shared with the end users, in which case it is deployed over to the production environment. It is at this point where you may assign the right degrees of permissions to the production users. So these may only include view permissions on the corresponding workspace to ensure that no changes are made in the production environment. So now that we have an idea of the different pipeline stages, let's explore some of the best practices when it comes to working with Power BI pipelines. First of all, it is crucial to set up the permissions separately for each of the three stages. This will make sure that developers, testers, as well as the final consumers are all treated differently. Next, another good practice is to make sure that each stage of the pipeline is connected to different databases. So, if you're sourcing your data from a relational database, for instance, you may have a dev, test, and production database hooked up to each of the different workspaces. Again, this ensures that changes can be made at the dev and test stages without affecting what is in production. When this is done, it may help to make use of parameters in Power BI in order to store information such as connection details and other information specific to each pipeline stage. And also, if you'd like to set up version control for various workspace resources, such as datasets for example, you can hook them up with Microsoft's OneDrive. Let's move along then to a concept which is crucial for any application and is also important for the DA-100 certification, specifically user permissions. So you will cover that permissions can be assigned at the report level as well as for a dataset, and these can also be set at the level of a workspace. If you have looked into the learning path design data models in Power BI, you will recognize that row level security can be set up for viewers to ensure that they only view their own data. We will also explore this concept in more detail later on in this learning path. Just keep in mind that row level security applies to the end users of an application as opposed to the collaborators who will be assigned permissions at the workspace level. Another important feature in Power BI is object level security, and this is something which can be applied in order to hide sensitive columns as well as entire tables from the view of the end users. Let's zoom in on the security features, starting with row level security. So this is where we effectively apply filters within the dataset so that users only have access to specific rows. The security can be set up by means of a region column, for example, to ensure that an individual only views sales or profit data within their own region. And this kind of row level security can be set up in Power BI Desktop and also tested there before it is eventually deployed to the Power BI service. And while row level security differs from the permissions assigned to users at the workspace level, users will need to be granted viewer privileges at the workspace for this feature to apply to them, since all other workspace level roles essentially make all data accessible. Moving on then to object level security. This is also similar to row level security in that it involves the creation and configuration of roles. However, rather than rows, it is entire columns or tables which are hidden from end users. These may be columns which contain sensitive information such as private customer details. But before using this feature, keep in mind that, at least as of October 2021, this is not supported by Power BI Desktop natively, and it does require the installation of an external tool. So, security can be set up at the workspace, row, and object levels in Power BI. And with that, let's move along to a rather useful feature when it comes to keeping track of who exactly is using our Power BI apps and how often. And this is a monitoring feature. This is something which is available for each report, and Power BI will essentially generate metrics for each of them. These reports will tell us who has been viewing our reports, what pages of each report have been viewed, and by what users. The viewership of your report can also be compared with the viewership of other reports from your own organization. And then there is a paginated reports feature. So you will be familiar with the fact that Power BI reports are quite interactive, and this also applies to paginated Power BI reports, which can be shared with end users via the Power BI service. However, one feature which distinguishes paginated reports from the regular ones is that these are meant to be printed out on paper and then distributed to end users. So while these can be interactive, they are not meant to be. So paginated reports can be set up with data sources as well as parameters, much like any other Power BI report, but the use case is quite different in that they are meant to look good when printed out on paper and then shared. Paginated reports cannot be created in Power BI Desktop, but they can be added to a workspace in the Power BI service. So within your workspace, you may have regular reports which are meant to be shared online, and then paginated reports which are meant to be printed out and then distributed. And finally, we will take a glimpse into one more Power BI feature, which is a data flow. This is essentially an ETL, or extract, transform, and load feature which is available in the Power BI service. And as you can imagine, this is meant for us to set up various steps in order to transform one or more data sets, which can then be used within visualizations. So we can essentially set up a workflow in order to apply these transformations, which include steps such as getting data from an Azure SQL database, eliminating some columns from a table entirely, or just transforming specific columns to say whole numbers rather than decimal numbers. And why exactly are data flows useful? Well, once we define a sequence of steps which need to be applied to data, a data flow essentially allows us to reuse those same steps for any other data set. Once you complete this learning path, you'll be pretty much all set to go ahead and give the DA-100 certification exam. However, just to get you oriented towards the exam, we will now discuss some of the mechanics related to it and also some things you need to be mindful of. First of all, let's quickly go over the skills which the exam tests you for. So, about a quarter of the questions will test your ability to prepare data for analysis. These topics were covered in depth in the learning path Prepare and Process Data in Power BI earlier on in this journey. Another quarter of the questions will focus on modeling data for analysis, and these topics were covered in depth in the path Design Data Models in Power BI. A further 20% of the questions will test your ability to use the right set of visualizations in order to convey data, and these were covered in depth in the path Visualize and Interpret Data in Power BI. And then in this learning path, we will focus on analyzing data in order to extract insights, and this covers about 15% of the exam questions. And finally, there is deploying and maintaining Power BI assets, which cover a further 15% of questions, and which we also explore in depth in this learning path. Next, Let's take a look at the precise steps involved in taking up the DA-100 certification test. First of all, of course, you will need to study for the test, and by taking this course, you are already doing that. You will also need to register for the exam, which you may have already done at this point. We will soon take a look at some of the things you can do to set things up for the test the day before the exam, and then we will also take a look at the mechanics around taking the test itself. So let's take a look at some of the steps around test registration. Now, in order to register for the exam, you can navigate to the DA-100 exam homepage at this URL, and there will be a link in order for you to sign up for a specific date. Keep in mind that the test is usually managed by an exam partner for Microsoft, which at the time of this recording is Pearson VUE, and the test can be given either online or even in person. In either case, you will require a Microsoft account, which you will also need in order to access and download the data analysis certificate if you pass the exam. Once you have registered for the test, well, let's see how we can prepare for an online test if this is what you choose. First of all, you will receive an email upon registration, and this will contain detailed instructions on how you can set up your machine as well as the physical environment when you give the test. The email will also include an access code which you must keep in handy in order to download and install the OnView software which you will use in order to give the online test. So make sure that you set up your environment as well as set up the software at least the day before the exam, and don't rush things through on the day of the test. You can also use the OnView software in order to test out your microphone, speakers, and internet connection so that you uncover potential issues before the test itself. And keep in mind that you will require an ID before you begin your test, and that the name of this ID should match exactly what is specified in your Microsoft account. These, of course, only cover some of the details when it comes to setting things up for the test. All of the information can be accessed by navigating over to this URL. From the setup work, let's move on to what you should keep in mind on the day of the exam. So, for the online test, make sure that the desk you're working on does not contain any clutter, that is, no gadgets or books. And while you can keep your cell phone in your room, you may need to keep it further away from your desk. The cell phone will be useful in order to upload your ID using a link which will be supplied to you. Make sure that you check in for the exam using the OnView software at least 30 minutes before the scheduled start. This is just to iron out any potential issues which might arise with the connection or the microphone and so on. Also, the OnView software will pretty much disable all applications on your machine, including browsers and text editors. Once you have completed your sign-in using the OnView software, a proctor will come online and then may perform a physical inspection of the room. And keep in mind that this may also happen in the middle of the test. There will be a total of between 40 and 60 questions, which will be adjusted to a total of 1000 points. And you will need to answer all of these in 180 minutes, that is 3 hours. So the passing score as of this recording is 70%. So you need to get at least 700 points out of 1000. So how exactly does the test itself work? Well, you will of course be presented with questions, and for each of these, there will be multiple options for an answer. You can select your answers and then hit the submit button or mark the question to be answered at a later point in the test. Keep in mind that there may be multiple correct answers, or a correct solution may in fact require you to select multiple options in the correct order. Now, once you make your answer selections and hit submit, well, you will no longer be able to revisit that question. However, those which were marked to be answered later on will appear at the end of each section. If you run into any issues, specifically technical issues, you can use the chat feature available in the OnView software to talk to the proctor. And once you're done answering all of the questions, or the 3 R's are up, well, the results will be available to you in just a few minutes. Let's move along then to a type of question which you may be posed. So case studies are extremely common in the DA-100 certification exam, and you may come across a handful of them. Let's just say one case study involves the sale of a product across multiple countries in the world, and you are asked to create a measure which gives you the total sales recorded in the country of South Korea. The correct solution here involves you making 3 different selections from these 3 sets of options supplied. In this case, a correct solution will involve selecting calculate for the first function to be used, and then the first argument to calculate may involve computing a sum of the sales column in a table. And then to complete the calculate function, you will require a filter context to be set, and this could be where the country column in the table is South Korea. So this is how you will answer the question, by effectively making 3 different selections from 3 sets of options. So this is just one example of the types of questions you may come across. And once again, I will emphasize that case studies are crucial in the certification exam. Typically, you will be presented with a scenario involving a fictitious business. The questions here may involve certain processing steps around data, the definition of DAX measures in order to make certain calculations, and you may even be asked what type of visualization should be used in order to convey a certain piece of information correctly. Permissions related to workspaces as well as row-level security are also important topics. So in the end, the goal is to test your knowledge of the features available in Power BI and, significantly, your ability to apply them to a specific situation. So it is not just rote learning of the features which is going to help. You will need a conceptual understanding of them as well. One crucial skill of a data analyst is the ability to pick the right set of visualizations which will allow the end users to easily extract insights from the data and then make decisions based on those insights. This requires data analysts to have at least some understanding of the business themselves and then to understand their data from that perspective. Using this particular data set which you see in front of you, which contains information about various cars which were up for sale, we will explore the data in order to extract insights from the point of view of a fictitious car dealership which has all of these vehicles in their inventory. This dataset is available as part of your course materials, but can also be downloaded from this URL on kaggle.com. So, what exactly does this dataset contain? You'll observe that it contains a total of 16 columns. So these are represented as A through P in this Excel file, and each row represents a single vehicle which is up for sale. Well, except of course for row number 1, which contains the column headers, and then for each row, we have the make, model, and year of the vehicle, along with the type of fuel required for its engine, which is available in column D. We have the horsepower generated by its engine in column E, and then the last column contains the price of the vehicle. And then, if you were to scroll further along in this dataset, you'll notice that there are over 10,000 vehicles here. So clearly, this information is not something which can just be analyzed looking at the raw numbers, but we will need to use a tool such as Power BI to extract meaningful information from this large dataset. Speaking of which, I'm going to switch over my window to one where Power BI is up and running. More precisely, Power BI Desktop. You will notice from the top that I have created a new PBIX file called Outliers, where I am going to create a new report where we analyze the automobile data we just took a look at from various angles. And we will start off by identifying some outliers among those vehicles. Alright then, we will first need to load the data into Power BI Desktop. So for that, we head first to get data and then to text/CSV. Since it is a CSV file, which contains the data we just looked at. Next, we navigate on our file systems to the location of the CSV file. So I'm already in that folder and have selected the car data file, which I will now proceed to open in Power BI. And then we get to preview the contents of this file. So here we can see all of the columns in their entirety. We also get a glimpse into the fact that Power BI has automatically promoted the first row of the dataset to column headers. So here we can see that the columns include the vehicle style, the miles per gallon for both highway and city, as well as a popularity metric for each vehicle. So for the sake of our example, let's just say we are data analysts who need to build reports which will help the top management in a fictitious car dealership decide the strategy for sales in the upcoming season. So we do have a good amount of information to work with over here, but it's time now for us to identify some meaningful patterns in this data which can help management come up with sales strategies. Now to pull this data into Power BI Desktop, we can just hit the load button so that it is loaded with the default configurations. And once we do that, in a few seconds, you should be notified of the fact that a shade under 12,000 rows have been loaded in all. And on the right, you can see the car data table appear under the Fields menu. Expanding this gives us a glimpse into the different columns here. Significantly, we can see that columns such as City MPG, Engine HP, Highway MPG, as well as MSRP can all be summarized, which means that these have been set as numeric values as they should be. For a quick sanity check, let's just head over to the data view. And then from here, well, we can confirm that the data has been loaded, and now it's time for us to move on to analyzing it. So let's just say our dealership has higher margins on vehicles where the engines are more powerful. That is where the engine horsepower values are higher. Given that, we may wish to analyze the engine horsepower against another column, let's just say the MSRP, which is the manufacturer's suggested retail price. And if you are familiar with vehicles, you will know that typically when the horsepower rating of an engine is higher, the MPG values of the vehicle, that is the miles per gallon or the fuel economy, tends to be lower. So we could say that vehicles whose engines generate a lot of horsepower but whose highway or city MPG values are also high tend to be outliers, and potentially these are the vehicles which the customers of an auto dealership may be willing to pay a premium for. So now let's move on and try to identify such outliers. But first, heading over to the engine HP column, we can pull up the menu, which will give us a few options with regards to this column in this view, but we are more interested in the distinct values which appear here. Importantly, you will observe that there are a number of blank values, and in fact there are quite a few of them, and these can throw off a lot of our visualizations, which means that we do require some data cleaning to be performed in order to use this column in our visualizations meaningfully. And for this data cleaning, we can first cancel out of this view, and then heading over to the home menu, we pick the option to transform data. Now I assume that you are already familiar enough with Power BI Desktop to know that this will pull up the Power Query Editor, which will allow us to apply a variety of transformations on the data, which includes cleaning some unwanted rows. So now that Power Query Editor is up, let's just scroll along to the column of interest, which is Engine HP, and you'll observe that at least in my view, the data quality information is available just below the column headers. So for the Engine HP column, 99% of the values are valid, there are no errors, but about 1% are empty. So when we just hover over this, we get an idea that out of the 1000 rows sampled in this case, 997 are valid and just 3 values are empty. However, given that we have about 12,000 rows in all, we can imagine that there will be more empty values, and these can really throw off our visuals. So we will soon go ahead and clean out these empty values. But before that, we can confirm that the column right next to engine HP, which is engine cylinders, contains 0 empty values, at least in the first 1000 row sample. And this also applies to the transmission type column. Finally, let's just take a look at some of the other columns, and from the data quality metrics, we can confirm that there are no empty values for any of them. So it is just engine HP which we need to take care of. And for that, we can just head over to the data quality metrics which are available. And then from the pop-up which appears, well, for one, you will notice that there is a little light bulb here, along with the suggestion for us to remove empty values. This is a suggestion made by the AI which lies beneath Power BI. And throughout this learning path, we will come across other instances where the artificial intelligence does make useful suggestions. Let's follow this suggestion for now, however, by expanding the menu by clicking on the 3 dots and then choosing to remove empty values. This means that any row in our dataset which contains an empty value for the engine HP column will be removed entirely. This of course means that there are a number of cars which we will be taking out of consideration when it comes to performing analysis, which also means that analysis based on some of the other columns for those vehicles will not be possible, even if they contain valid data. However, when the number of invalid rows is rather low, as in this case where it's comfortably less than 1%, this is usually a trade-off worth making, because we are still left with enough vehicles for us to perform meaningful analysis. So let's just move on and just choose to remove all the rows which contain empty values for HP. And you can see in the applied steps that a filtered row step has now been added. And then heading over to the data quality details for engine HP. Sure enough, there are no longer any empty values. Just in case you're wondering, the cleaning of empty values has been applied to the entire dataset of nearly 12,000 rows and not just to the sample which we view here. Alright, with this change made, we can save things down by choosing the option to close and apply. So we are no longer interested in applying further transformations. And with that, well, down below, you'll notice that we are down to 11,845 rows. So about 100 rows have been eliminated due to our cleaning. And then when we take a look at engine HP, sure enough, there are no more blank values, which means that we are now ready to perform analysis based on this column. Before we build any reports from this data, however, let's apply one more change, this time to the formatting for the MSRP column. Given that this represents a price, and specifically a price in US dollars, it makes sense for us to represent the values here as a currency. So let's just select this column and then head over to the column tools in order to apply formatting here. So this has already been set as a whole number, but let's expand the currency option and then explicitly mark this out as US dollars. Now I have marked the region on my machine as United States, which means that the default currency is the US dollar. So I can just click on this dollar sign, and sure enough, the dollar symbol now appears next to the MSRP value. Furthermore, you will also notice that the 1000 separator has been applied, so it will be easier for us to tell whether a vehicle costs $3,000 or $30,000. So with these changes made, we are done with the processing of our data and we are ready to use it in a visualization where we'll try to identify outliers in our data for vehicles which have high horsepower but also good fuel economy as represented by the MPG values. However, we will look into this in the next video. In the previous video, we had loaded this automobile dataset into our Power BI desktops, and our goal was to perform an analysis of this data in order to identify certain outliers in terms of vehicles which have very powerful engines but also give us good fuel economy. this is something which we consider as important for the upper management in our fictitious automobile dealership company, assuming that they typically get higher margins on vehicles with more powerful engines, and they could charge a further premium for cars which have powerful engines but also good fuel economy. To identify such vehicles, however, let's switch from the data view in Power BI Desktop over to the report view. And we will now make use of a scatter chart where we will plot the engine horsepower of a vehicle against its fuel economy. So once we add this chart, I'll just resize it so that it occupies much more of the screen. In fact, I'll just switch to focus mode. And then to populate this visual with the fields of interest, we'll expand the car data table. And then first, for the x-axis, we'll drag and drop the engine HP field. So given that the engine horsepower has been summarized over here, there is just a single dot in our scatter plot. And this is a value which appears just below 3 million. This means that the sum of all horsepowers of the vehicles in our dataset is a little under 3 million. But of course, summing up horsepower does not really make sense. So we will need to choose a different form of aggregation or no aggregation at all. We will get to that in just a little bit, however. First, we will drag and drop the other field of interest over to the y-axis of our scatter chart. So this is highway MPG. Once this comes in, well, we still have just a single dot, and this is because the highway MPGs have also been summed up. Again, this does not really make sense, so let's just adjust the aggregations for each of the axes, starting with the engine HP on the x-axis, and we now choose the option to not summarize, since we want a single dot to appear for each individual vehicle, and we don't want any aggregation to be carried out at this point. Then, we'll repeat the trick for the highway MPG by expanding the menu and then choosing the option to not summarize. And with this selection, well, this is the visualization we are left with. So you can see that most of the vehicles appear towards the bottom here and also closer towards the left of the visual. This means that aside from a handful of vehicles, most of them tend to have lower values of engine HP and lower values of highway MPG. Keep in mind that the expected relationship here is that as engine horsepower increases, highway MPG should decrease, given that usually more powerful engines consume more fuel. That relationship is not quite obvious in here thanks to a couple of outliers in this dataset. So let's just hover over them to see what exactly these represent. First of all, there is this little marker right next to the 1000 value for engine horsepower. Hovering over that, we can see that this does in fact represent a vehicle whose engine HP value is 1001 and with a highway MPG of 14. So given that this particular vehicle is far away from all of the others in our scatter plot, this can be considered an outlier. So, from the point of view of the upper management in our fictitious dealership, we may want to focus on the sales of this particular vehicle separately from the others. Then there is the other very clear outlier. So in this case, the engine HP is 252, which is definitely high, but does not quite stand out in our dataset on its own. However, it is the highway MPG which sets this apart from all of the other data points. At 354, this is comfortably above the next most fuel efficient vehicles, where the highway MPG stands just a little over 100. Now, given that this particular data point is so far apart from the others, it tells us one of two things. Either this vehicle is truly an exception, or there is an error in the highway MPG value here. In fact, I can tell you that it is the latter which is true. So, there is an error in the highway MPG metric, which means that we have now identified a potential erroneous data point in our data. And before we build any visuals and reports based out of this dataset, we should be sure to exclude this particular point. However, let's take a look at some of the other outliers within our dataset. I'm just hovering over this particular point where the highway MPG is over 100, 102 to be precise, but with a very low value for engine HP, just 66. Let's move along and take a look at the next vehicle. So this still gives us a highway MPG of over 100 and with an engine HP of 115. Well, this is more in line with other vehicles in our dataset. However, the outliers which we wish to identify are those which do have higher values for engine HP and still give good fuel economy. In this case, well, we have identified such a vehicle. With an engine HP of 200, the engine is certainly quite powerful by standards of most vehicles, and a highway MPG of 110 is definitely very impressive. However, what exactly is the type of fuel which is used here? Is this a hybrid, electric and gasoline powered vehicle? Well, to get that information, we will need to consider one more dimension in our analysis. Specifically, let's include the engine fuel type field from the car data table and use this in the legend axis for our visualization. And if you're familiar with scatter charts, you will know that based on the engine fuel type, there will be different colored markers which appear within the scatter plot. So, before we examine each of the markers in more detail, I'll just go ahead to the formatting pane and then apply some formatting changes to this visual to make it a little more readable. First, we'll head over to the Legends menu, and then from here, we'll place the legend not at the top where it appears by default, but instead towards the right of the visual. So the values now for the engine fuel type are a little easier to read since they appear in full. And then you can also go on and adjust the text size in case you feel it better helps with visibility. Once this has been set, well, it's time for us to perform more detailed analysis. So we can head back over to the Fields menu and then hover over some of the points where, in addition to the engine HP and highway MPG, we can also examine the engine fuel type. So this particular vehicle, which is an outlier in terms of engine HP, uses premium unleaded petrol, and we can see that each of these orange markers represent vehicles where the engine fuel type is electric. So these represent vehicles with potentially hybrid engines, so the high values for highway MPG does make sense. However, when we move on to this particular outlier, well, given that the engine fuel type is premium unleaded, so it is a gasoline powered engine, this is further indication of the fact that the highway MPG is in fact wrong. So there is now a stronger case for this particular data point to be left out of the dataset. For each of the markers in our scatter chart, we can see 3 different dimensions of data. However, this does not really tell us what vehicle it is. When it comes to coming up with a sales strategy, we will need to know the make as well as the model corresponding to the marker, and we will now add those 2 fields from the car data table over to the tooltips for the scatter plot. First, let's drag and drop the make field over and then repeat the trick for the model. You will notice that what appears in the tooltips points to the first value of make and the first model corresponding to a particular marker. This of course assumes that each marker represents an aggregation of values, but of course in our case, we have disabled aggregations for both the engine HP and highway MPG, which is why each marker represents just a single vehicle. And now when we hover over this outlier, we can see that this corresponds to a Bugatti Veyron 16.4. Once again, when we hover over this outlier, we can see that this represents an Audi A6. So this is one more bit of information which points to the fact that it is the highway MPG here which is off, since at least at the time of this recording, there was no Audi A6 with this type of fuel economy. Let's hover over some of the electric vehicles in here with high values for engine HP and good fuel economies. So this particular marker represents a Chevrolet Bolt. And then moving further along, there is the Mercedes-Benz B-Class. Alright then, to further help with our analysis, let's head over to the analytics options within our visualization and then add in a trend line in our scatter chart. So let's just go ahead and add a trend line and then we can see what this looks like. Of course, this trend line has been considerably skewed by the outlier, which represents the erroneous data point. However, it is still clear that the relationship between engine HP and highway MPG is one where an increase in engine HP brings the highway MPG down. So now that we have identified some outliers within our dataset, well, let's drill down a little further into each of the engine fuel types to see whether there are any outliers within each of the categories, rather than in the dataset as a whole. That, however, is something we will look into in the next video. In the previous video, we examined the entire automobile dataset in order to identify outliers when it comes to comparing highway MPG versus engine horsepower. As far as what exactly those outliers were, we saw that there was one erroneous data point. There is one vehicle with an exceptionally high value for engine HP, and then the other outliers here are all of these orange markers which represent electric or hybrid electric vehicles. We did all this analysis from the point of view of identifying those vehicles which potentially have high values for engine HP, which typically translates to higher profit margins, since customers who want more powerful engines are typically willing to pay just a little more for it, when compared to customers who just want to use a vehicle to get from point A to point B. But then there are also customers who are more sensitive to the running costs of their vehicle, in which case they may be tempted to splurge a little more when buying a vehicle as long as the highway MPG is very good. While we know that electric vehicles or hybrid electric ones do offer better highway MPG values, let's perform some more detailed analysis to identify the outliers within each engine fuel type category. So for that, we will need to expand the filters menu, since we will be applying a few filters on our data. Again, I expect that you are familiar with visualizations in Power BI and have used filters in order to perform more detailed analysis. But just as a quick refresher, this will allow us to filter the contents of the data which is displayed in our scatter chart based on various fields. So the fields of engine fuel type, engine HP, make, model, and highway MPG are already available for us to apply filters on, given that these fields are already associated with our visual, but we could also go on to add a few more. However, I'm going to stick with the default fields here and then minimize the fields and visualizations menu so that we have a little more room for our own chart. Next, let's expand the engine fuel type filter and then restrict our view to those vehicles which use regular unleaded petrol or gasoline. So we can see here that out of the 10,000 or so rows of data in our dataset, a little over 7,100 represent this particular fuel type. So it is by far the most well represented within our dataset. So it does help for us to analyze this in isolation. So when we apply this filter, well, it is much clearer now what the relationship between highway MPG and engine HP is. The trend line is clearly decreasing in nature. So it is clear that as engine horsepower increases, the fuel economy tends to get worse. However, the goal now is for us to identify potential outliers in this dataset to see whether we could potentially charge a premium to the customers, given that they will like a more powerful engine and also one with good fuel economy. And in this particular case, the customers don't have to shell out extra money for premium fuel. So the most powerful engine in this particular set belongs to the Ford F-150, which is a pickup truck. So you can see that the horsepower here is 450. But of course, you might expect that from a vehicle which is expected to haul rather heavy materials. Let's move on and take a look at some other outliers. So this is a Mercedes-Benz 600 class. So the horsepower here is definitely rather high at 402. However, the highway MPG is rather poor. This, however, is due to the fact that this vehicle is a vintage one. So again, it is an outlier not just in terms of horsepower, but also in terms of the kind of vehicle it represents. Let's take a look at some of the other outliers in terms of vehicles which have both low values for engine horsepower and highway MPG. Unless these are vehicles which have rather unique characteristics, such as being vintage vehicles, for example, we can assume that the management of our fictitious dealership will be keen to get rid of these vehicles as soon as possible. This marker, however, does represent a rather special vehicle. It is a Volkswagen Vanagon, and even though it has a rather low highway MPG of 15 and a not so impressive engine HP of 90, it is because it is firstly a van and a somewhat old one at that. So this is one more vehicle which could be considered vintage. And then of course we can hover over each of the individual data points to get additional bits of data. But let's zero in on this vehicle, which at a little over 200 horsepower does contain a rather powerful engine and also gives excellent fuel economy with a highway MPG of 47. This is a Honda Accord hybrid, and we can assume that it is possible for the dealership to charge a premium on this, given that customers will like the power given by the engine and the fact that its overall running costs will be rather low, given the good MPG value, as well as the fact that it uses regular unleaded petrol. Let's expand the filter then, so that we also consider vehicles which require the use of premium unleaded fuel. Now, of course, there are more data points within our chart, and there are also a number of vehicles with a higher value for engine HP. So this, of course, represents the point where we get to the more premium segment of the market. When a vehicle requires the use of premium fuel, well, we should expect that the customers will be willing to pay more, and that the engines themselves will be a little more sophisticated than the ones which require regular unleaded fuel. Of course, the Bugatti Veyron appears over here, but since we are considering gasoline-powered vehicles, let's complete the set by including vehicles where premium unleaded fuel is recommended but not required. Of course, this pulls in the outlier or the erroneous data point in a dataset. This is the one which contains an abnormally high value for highway MPG, and this of course skews the data. Let's move along then and examine one more category of engine fuel type. I'll just go ahead and uncheck each of these boxes for the different gasoline-powered vehicles, and then scroll over and check the diesel-powered option. And this is where once again we can see a decreasing trend line, conveying that even among diesel vehicles, as engine HP goes up, highway MPG drops. Now to identify outliers here, we need to stay as far away from the trend line as possible. For example, this vehicle does come in as the most powerful diesel-powered vehicle in our inventory, and this represents an SUV, which is the Volkswagen Touareg. Looking at the bottom left of this particular dataset, we can see that this Mercedes-Benz 300 class does have rather poor MPG, and the engine horsepower is not as impressive for other vehicles which use diesel fuel. I can tell you though that this is also a vintage vehicle, so perhaps we shouldn't be too put off by the relationship between highway MPG and engine HP here. And of course, we can continue looking at each of the other data points to get a better understanding of what qualities exactly make these outliers in our dataset. So now that we have covered different ways in which we can perform a visual inspection of our data in order to identify outliers, in the next video, we will aim to identify outliers based on a calculation by casting them into a separate table. So far, we have covered how outliers in our dataset can be identified by visually inspecting the markers corresponding to various data points in a scatter plot. Now, however, let's switch over to the data view, where we will construct a table using a calculate table function, and we will populate this table with what we identify as outliers based on our own criteria. First of all, I'll draw your attention to the bottom left, where you can see that this car data table contains a total of a little over 11,800 rows. So clearly this is a fair amount of data for us to work with, though of course, realistically, you may be working with hundreds of thousands, if not millions of data points in your own organization. However, let's just proceed and then define a new outliers table, for which we head over to table tools, and then define a new table using a DAX expression. Let's give this table a name of outliers. As for how exactly this table will be constructed, we will make use of the calculate table function. Just in case you're unfamiliar with this is a function which allows us to define a table based on one or more filter conditions applied to an existing table. The first argument which we need to supply to calculate table is one of the existing tables on which the filtering conditions will be applied. So in our case, there is just one table to speak of, which is car data. Next, we can supply one or more filtering criteria. Let's go ahead and supply the first one. In this case, let's just say we're looking for cars which have good fuel economy. So we will define this in terms of highway MPG. So let's just select that particular column, and then for the condition which is based on the highway MPG. So if we are looking for vehicles which give us very good fuel economy and also have high engine horsepower, well, let's define the first filtering criterion as one where the highway MPG of the vehicles is greater than 1.3 times the average highway MPG. So in this case, we just complete the formula by making sure that the highway MPG is greater than 1.3 times the average of the highway MPG. So this concludes the first of our criteria for our outliers definition. But beyond good fuel economy, we are also looking for outliers in terms of the engine horsepower. So for our second condition, let's just select the engine HP field in car data, and then we define an outlier as a vehicle where the engine HP is greater than the average horsepower. So we'll just apply the average function and use this on the engine HP column, and this concludes our calculate table function. So just to summarize, we define outliers as those cars in our dataset, specifically in the car data table, where the highway MPG is greater than 1.3 times the average highway MPG, and the engine horsepower is greater than the average engine HP. So to view the outliers, we can quickly just reformat this formula and then hit enter. And this is what we are left with. At the bottom, we can see that there are a total of 15 rows or 15 outliers based on our conditions. In the make column on the left, we see that there are Volvo, Lotus, Audi, BMW, and Infiniti vehicles. And as for the engine fuel type, we see that there is a good mix in here, but there are no electric vehicles, presumably because none of them have greater than average engine horsepower. And it is just the two Volvo S60s which appear at the top, which use regular unleaded fuel. Since we no longer require the formula, I'm just going to minimize the view here, and then let's just scroll along and take a look at some of the other properties corresponding to these outliers. So we can take a look at the highway MPG here, and we still have what we assume is an erroneous data point containing a highway MPG of 354. Also, the retail price for each of these is rather high as well, but this is of course understandable given the conditions which we have specified. Now a question you might ask at this point is, what is the point of extracting the outliers as we have done over here? Well, now that we have each of these data points in a separate table, we can in fact perform an analysis purely on the outliers. That is, the outliers based on our own definition. And for that analysis, we can switch over back to the report view, and then we will continue using this scatter chart, but on new data. So let's just uncheck the filter which has been applied first, and we can see the full view across all data points. But now, expanding the visualizations and fields panes, I'm just going to perform a little cleanup here. First, by heading over to the field view in the visualization, and one by one, we'll just eliminate each of these different fields which have been applied to our scatter chart visual. So with a clean scatter chart, let's use the formatting which we have defined here in order to plot a chart for just the outliers. So once again, we drag and drop engine HP on the x-axis as we did before, and then highway MPG on the y-axis. I'll then minimize the filters pane. Sure enough, there is just a single marker in our chart, given that engine HP and highway MPG have been summarized. So once again, let's apply the don't summarize option for engine HP, and then repeat the trick for highway MPG. And this is our new scatter chart. Once again, the trend line is skewed by the fact that there is an erroneous data point here. Without it, however, you will notice that among our outliers, the relationship between engine HP and highway MPG is really not that clear. Even the markers towards the right of this chart, representing higher engine HP values, don't seem to have any drop in MPG. Now keep in mind that we have a total of 15 rows in our outliers table, but there seem to be fewer than 15 points in this scatter chart. And if we head over from the report view over to the data view, we can see why this is the case. Specifically, while there are 15 different vehicles, many of them have the exact same values for engine HP as well as highway MPG, given that they represent the same vehicle make and model as well as year. So the corresponding markers will simply overlap. Alright then, let's now redefine our outliers criteria so that we have more data points to work with. First of all, we will now look for vehicles where the highway MPG is not 1.3 times the average, but simply greater than the average. And then where the engine horsepower is more than 1.2 times the average horsepower. So I have just hit enter over here, and right away at the bottom left you can see that our table now contains 546 rows. So this is not as exclusive a set as our previous one. However, we have more data points to analyze. Also, I'll draw your attention to the fact that the first few rows which you can see in this view here represent Cadillac CT6 vehicles. All of these have the same value for engine horsepower at 335, and scrolling along, they have the exact same highway MPG value of 27. So once again, these points will overlap in our scatter chart. So we will not have 546 distinct markers. However, given that they all represent essentially the same vehicle, when it comes to defining a sales strategy, this really may not be a problem. Alright then, we can scroll along and take a look at some of the other vehicles in this new definition of outliers. But now when we switch back over to the report view, well, given that the outliers table has changed, so has this visualization which has been built from it. Here we can see that the relationship between engine HP and highway MPG is really not that clear-cut. While there is a decreasing trend line, the angle of decline is rather low, so it is essentially a flat line. However, even among these outliers, we still have outliers here. First of all, this one represents a vehicle which is very powerful in that the engine horsepower is 580, and the highway MPG overall is also rather impressive. Then when we take a look at this outlier, again the engine horsepower at 400 is rather impressive, and the highway MPG is definitely an outlier even amongst these outliers. Of course, we don't really have any additional information about these vehicles, so to throw some more color, let's add in the tooltips, the make as well as the model for each vehicle. So one by one, I'll just drag and drop each of these fields here. And now hovering over the data points, well, this vehicle, which has a very powerful engine and still manages to give better than average fuel economy is a Porsche 911. While the brand name alone does carry a lot of value, we can expect that the very good fuel economy will allow a car dealership to charge just a little extra premium. Once again, sticking to the higher end of the horsepower values, we have the Audi RS7, and then there is also an Audi S8. And then let's head over to the outlier in terms of the fuel economy, and this is a Lotus Evora 400. So all in all, we have seen that it is possible for us to identify outliers not just by performing a visual inspection, but also by defining our own table of outliers based on filtering criteria. And then it is possible for us to perform analysis based on the outliers themselves. All of this information can be useful to the management in our fictitious car dealership, where they could potentially come up with a marketing strategy to target consumers who are interested in premium vehicles which have very powerful engines but are still relatively friendly to the environment with fuel economies which are comparable to regular vehicles. In this course, you got to identify some of the important factors when it comes to analyzing and sharing data and the Power BI features which simplify this task. You covered a lot of these from a theoretical standpoint before using Power BI to identify outliers in your data. You started off with a look into the important points to consider when building Power BI reports, including a phase of exploratory data analysis to understand your data. You then explore the different features available in the Power BI service to collaborate with others when building a report. This includes streamlining the steps around report deployment and sharing your reports with consumers. You touched upon Power BI pipelines, which help you manage large and complex report deployments. You also covered some of the important practices with regards to securing your reports to limit the data accessible to your viewers. You saw what row level and object level security are and how they differ from one another. You also dived into some of the important things to keep in mind when preparing for the DA-100 certification exam after all your test prep is complete. Finally, you got hands-on with Power BI Desktop and performed some preliminary analysis in order to identify outliers in your data. Now that you have finished this course, you are all set to perform a deep analysis of your data to identify exactly what needs to be included in your reports and in what form. This has set you up to move on to courses where you focus on extracting meaningful insights using the tools offered by Power BI. We will now continue performing some exploratory data analysis of the cars dataset we have been working with so far, but now we will focus on some of the summary statistics, more specifically the types of aggregations which we can perform on the data, which will give us some interesting insights on what exactly our data represents. More precisely, we will take a look at some of the summary statistics based on the vehicle style for the cars in our dataset. For that, well, let's select a clustered bar visual. This will mean that there will be different horizontal bars for different categories based on a specific column in our dataset, and the categories will be based on the distinct values for vehicle style. So let's just select this and drop it as the axis for our visual, but we will need to specify a value which will determine the length of the bars corresponding to each value for vehicle style. So for this, let's just drag and drop MSRP. And there we have our bar chart. So we have a total of 16 different bars in here corresponding to different vehicle styles. And the length of each bar represents the sum of the values of each vehicle based on the MSRP or the manufacturer suggested retail price. Alright then, I'm just going to apply a few formatting changes to improve the visibility of our bar chart. Firstly, we'll head over to the y-axis and then adjust the text size. So it is now clear that the top bar over here represents the value of all sedans. Heading over then to the x-axis, again I'll adjust the text size, and now we have an idea of the sum of the values for each vehicle style. It is good practice when using either a bar chart or a column chart for us to turn on data labels. When we do this, a viewer does not need to strain their eyes to figure out exactly what value each bar represents. And while the text of the data labels may not quite be visible here, we can clearly see that the sum of the value of all sedans in our fictitious car dealership's inventory happens to be higher than any other vehicle style. Next come 4-door SUVs, then coupes, and then convertibles. So when we sum up all vehicle prices, we get to view the total value of the inventory corresponding to each vehicle style. And while this might be useful in some regards, we cannot tell from the visuals whether the value of sedans put together happens to be higher because sedans are more expensive than the other vehicle styles, or simply because there are more sedans overall. So while this visual can tell us the value of all sedans in our inventory, if you'd like to know what the average price of each sedan is or each convertible is, we can switch over to the fields view for the visualization and then change the aggregation for MSRP. So by default, it is the sum which is applied. But now if we switch over to average, well, our visualization has changed. Now when we hover over the longest bar, so this represents convertible vehicles where the average price of a convertible in our data set is a little over $84,000. So clearly these are rather expensive vehicles. Next on the list are coupes at a little over $76,000. And then we can see that sedans on average are just a shade under $40,000. So we already have a better idea of the cars in our dataset. However, even the average prices may not necessarily represent a typical vehicle in a specific vehicle style, and this is because we may just have certain vehicles which are very expensive and pull up the average corresponding to that category. To understand this, well, let's take a look at one more summary statistic. So we can change the aggregation for MSRP from average to maximum to see what the most expensive vehicle for each vehicle style is, and this is what we end up with. So we can already see that there is a massive skew in this particular bar chart, given that the most expensive coupe is just a little over $2 million. Looking at the bars towards the bottom of this chart, we can see that these values pale in comparison. Even the most expensive sedan at a little over $500,000 is just a quarter of the value of the most expensive coupe. And then going all the way down to cargo minivans, well, the most expensive one in our inventory stands at just about $28,000. So we saw just moments ago that the average value of a coupe in our inventory is about $76,000, but we can easily imagine that the most expensive coupe at over $2 million is really pulling up that average, which is why we can move along now and apply one more aggregation for the MSRP, where we switch over to a median. With this, of course, the prices of the extremely expensive or maybe even extremely cheap vehicles are diluted to a great extent, and we end up with bars which are a lot less skewed. And in fact, even though we end up with convertibles and coupes at the top of the pile in here, just as we saw with the average prices for vehicle styles, the median values are quite some way off the averages. So for convertibles, we saw that the average price was over $80,000, but is just about $44,000 in terms of the median price. So this median is a little more representative of the typical convertible in our inventory. When we take a look at a regular cab pickup vehicle style, we have a median price of $16,000. And then, of course, we can take a look at any of the other categories here as well. And while we continue exploring this bar chart, we can make use of the fact that this is in fact a clustered bar chart, which means that we can add one more dimension in here. So there will be different subcategories corresponding to each of the vehicle style categories. For example, if you were to drag over the driven wheels field and then apply this to the legend, well, for each category of vehicle style, we have subcategories of driven wheels. Now, this little change has made our bar chart a little too crowded. One piece of best practice when it comes to any kind of visualization, including ones in Power BI, is for us to make charts as easy to read as possible. And in this particular case, one way to do this is to add in a filter. When we expand this pane, you'll observe that we can apply filters based on driven wheels, MSRP, or vehicle style, or even add in any of the other fields from the car data table. But let's apply a filter based on vehicle style. We can set the type of filter to top N so that we only view a limited number of categories for vehicle style. So in this case, we can restrict the number of categories of vehicle style to 5, and this can be based on the MSRP. Much like with the visualization itself, there is an aggregation which we can supply here for the MSRP. So this is defaulted to sum, but we will change this to median. And then when we click apply filter, well, our chart is a lot more readable. While the text is not quite readable in here, I can tell you that when it comes to the convertible vehicle style, it is the all-wheel drive vehicles, which are the most expensive, followed by rear-wheel drive convertibles, and then front-wheel drive convertibles. Now, if you find that even this bar chart is a little too crowded, we can just eliminate the driven wheels dimension, and we are now down to 5 bars in total. Alright then, I'm just going to go ahead and clear out the filters so that we're back to the original set of 15 bars. Alright then, we have now successfully applied different types of summary statistics to our automobiles dataset. In the next video, we will continue exploring summary statistics, but we will see how we need to be a little mindful of the type of summary calculation which we perform based on how exactly data is represented in our dataset. In the previous video, we explored some of the summary statistics which can be displayed in a visualization in Power BI. More specifically, we examined the total value of the vehicle inventory corresponding to each vehicle style. We also took a look at the average and median prices for each vehicle style, as well as the most expensive vehicle in each vehicle style category. We can in fact apply one more aggregation, more specifically the count, in order to view the count of vehicle corresponding to each style to get an idea of the different variety of vehicles on offer in our fictitious car dealership. Once this change is applied, well, unsurprisingly, the top category is sedan, followed by 4-door SUV, and then some way behind are coupes and convertibles. We saw in the previous video that the value of sedans in our overall inventory was the highest, and now we know that this is because of the count of the vehicles more than their average price. And now, having explored a variety of different aggregations which can be computed, we will now see how we need an understanding of what kind of data is present in our tables before applying certain types of aggregations. For that, let's clear out this visualization by removing MSRP from values and also the vehicle style from the axis. And now, each bar in our bar chart will correspond to the make of each vehicle. Make, of course, refers to the brand of each vehicle, and what we will now convey by means of the length of each bar is the popularity of the brand. So, when we plot this, by default, as you might expect, it is the sum of popularity which is displayed, and right at the top in our chart are Ford vehicles. So, does this mean that Ford has the highest popularity among the vehicles, or are there just many more Ford vehicles, due to which the sum of popularity is very high? Well, this is something which has to do with what exactly popularity in this dataset represents. And before we get to that, let's go ahead and change the default summarization from sum over to average. And when this is done, well, Ford is still the most popular. However, the ordering of the bars has changed. I'm just going to minimize the filter pane so that we have a better view. So right at the top, we have Ford with an average popularity of just under 5,700. You'll observe then that this is followed by BMW, Audi, and Ferrari, and right at the bottom is the make Saab. Now we can hover over each of the individual bars to get their corresponding values. However, you could say that this particular bar chart is rather crowded, given that there are a lot of brands here. Of course, in order to clear up this chart, we can apply a filter So rather than view all of the different brands, we will apply a filter on the make column and then specifically a top n filter so that only specific makes will be displayed. And we will set this to the top 10 makes, and this will be based on the popularity. Once again, let's just apply an average aggregation here, and then we can choose apply filter. Now we're restricted to the top 10 most popular brands. So the bar chart is a lot less crowded. Now, of course, it is easier for us to examine these values, and then I'll apply a few formatting changes to improve the visibility of the visual. However, once that is done, let's see what happens if we were to change the metric here from the average of popularity to the median. And then when we hit apply filter, well, it is the exact same bars which are on display. Now, if we were to change this back to average, sure enough, there is no change. And this is because in the case of our data set, the average and the median are exactly the same. We can see this when we apply median to the visual itself and not to the filter. And the data labels are identical. So in this particular case, median and average do seem to have the exact same values at about 5700 for Ford and 3900 for BMW. And the reason for this is that in our dataset, the popularity value corresponds to a specific make. So for every model of Ford, you will have the same value for popularity. And similarly, for every row corresponding to BMW vehicles, there will be a single popularity value. In such a case, when we represent makes as categories within a bar chart or any other kind of visual, the aggregation which we apply should be either average or median, which will both have the same value, but it should definitely not be an aggregation like sum, since the value of popularity is effectively duplicated in our dataset for each row corresponding to a make. You can, of course, confirm this by switching over to the data view and then scrolling over to the popularity column. So in my case, you will observe that the popularity for each and every row which is in view is exactly the same, 1851. And then scrolling to the left, you'll observe that all of these correspond to the same make of vehicle, namely Dodge. So the value of popularity has been duplicated for each Dodge vehicle, no matter what the model. Dakota, Ram 250, Ram 150, as well as Ram Charger all have the same popularity value. So we really need to be quite careful about the type of aggregation which is applied when data is duplicated in our dataset. And when this is the case, we can almost assume that the sum aggregation will almost always be meaningless, and average, median, or even min and max will be more appropriate. In the previous videos, we saw that it is possible for us to apply a filter on our visualizations, specifically when applied to a bar graph, in order to reduce the number of bars overall. This ensures that the visualizations which we include in our reports are less cluttered and also enables the end user of our reports to focus on what is important rather than be distracted by noise. In this demo, we will continue focusing on the important categories for which we will use the same car data dataset we have been working with so far. However, we will make use of our own domain knowledge in order to define our own categories based on the existing ones. More specifically, we will zoom in on the engine fuel type field and cast together some of the different types of engine fuel types into single groups. Alright then, let's go ahead and create a new clustered bar chart in our report. I'll just bring this more into focus. And now, let's populate it first with engine fuel type along the axis so that we have different bars for different engine fuel types, and then drag and drop the MSRP, which represents the price of the vehicles, over to the values. As we have seen before, by default, it is the sum of all values which is computed. So this will give us the total value of vehicles corresponding to each engine fuel type in our inventory. This, of course, is a function of the count of the number of vehicles corresponding to each engine fuel type category. So to get a better idea of which engine fuel type results in more expensive or cheaper vehicles, let's apply the median aggregation instead. And it is the resultant visualization which tells us more meaningfully how the engine fuel type affects the price of the vehicle. Right at the very top, we have flex fuel with premium unleaded required within parentheses. Flex fuel represents a mixture of gasoline and methanol or ethanol. And we can see here that there are multiple different categories corresponding to flex fuel. The first and third bars here correspond to flex fuel, as does the fourth bar from the bottom. If the different varieties of flex fuel are not important for the consumer of our reports, well, there is a case to be made that each of these three categories can be grouped together into a single category. We will get to that in just a little bit. But first, let me just apply some formatting changes to this visualization so that the values are a little more clearly visible. I'll go ahead and adjust the text sizes first along the y-axis and then along the x-axis as well, and then add in a few data labels. With that, well, it is now clear to us that the top category in terms of engine fuel type is flex fuel, corresponding to premium unleaded required, and the median price of vehicles in this category is over 140,000. Now, to simplify our analysis, let's just group each of the different flex fuel categories into a single unit. For that, well, there are a few different ways to apply the grouping. One is to make use of the visualization itself. So here, let's first click on the top bar corresponding to flex fuel, and then go ahead and use the control key and click on the third bar as well. Control click, of course, allows us to select multiple values in most Windows tools. To start off, let's create a new group corresponding to these two categories, for which we can just right click and then pick the option to group data. When we do this, well, the two different flex fuel bars have been grouped into a single unit. And significantly, all of the other bars have also been grouped together into a unit called others. You can in fact view these two groups in the legend of this visualization. You'll also see that within the visualizations pane, under legend for this visualization, there is now a field called engine fuel type with groups in parentheses. This is in fact a new field which has been created within our car data table, and you can in fact see it selected within the fields pane. So this gives you an idea of how grouping works in Power BI. However, we have barely scratched the surface. Now, before we move on and make any changes, let's just hover over one of these bars, and you can see that the engine fuel type is listed here along with the median MSRP value and also the group represented by the engine fuel type group. The name of this particular group is rather long and is essentially a combination of the different categories it is composed of. Of course, the groups as they stand are not particularly useful given the rather long and awkward name for this particular group, the fact that each of the other engine fuel types belong in a single group called other, which is not quite descriptive. And also importantly, we still need to add in a third type of flex fuel into a newly created group. So what we really need is to edit the existing data groups, for which we can navigate over to the data groups option under column tools and then choose to edit data groups. And when this is done, well, we have a menu in place where we can select any of the existing groups which have been created and then edit them. As of now, we only have a single data group, namely engine fuel type groups. And this is what appears in the name field and is the only one which is available for edit. Furthermore, you can see that the field property at the top points to the existing field in our table out of which this grouping field has been created. So it is engine fuel type, from which our engine fuel type group field has been derived. And then further below, we have two different columns, one containing values which are ungrouped, and then others containing the fields which have been applied to specific groups. From here, it is possible for us to create new groups and then include some of the existing ungrouped values within those groups. And then we can also remove values from existing groups. Let's expand this new flex fuel group which has been created, and we can see the two different values for engine fuel type which correspond to this group. Now, We already discussed the fact that this name is rather long and awkward, so we can just double click and then we have the option to type in a new name. Let's just call it Flex Fuel, which is more succinct and easier to comprehend. Now, of course, we need to add in this other Flex Fuel value over to this Flex Fuel group. To do that, we first need to click on this value from the ungrouped value set, and then from the group and member set, let's click on the group that value needs to belong to. So with these two selections made, well, we can just go ahead and hit group. And we can see that the Flex Fuel group now maps to 3 different values for engine fuel type. With that done, we have now simplified each of the Flex Fuel categories. However, there are still a total of 7 different values for engine fuel type, which can do with further grouping and simplification. You'll also notice at the very top that there is also a blank value. We will address that in just a little bit. But for now, let's focus on the values which appear towards the bottom of this ungrouped value set. The bottom 3 correspond to different types of petrol or gasoline. And then we also have natural gas right above it. To start off, let's pick each of these 4 ungrouped values, and we can make use of Control click once again in order to multi-select. And to begin, let's include all of these in a single group. For that to happen, we can just click on Group over here. And now a new group has been created on the right. We now have the option to edit and set a name for this group. Let's just call this petrol/gasoline. And now there are just 3 different values, including a blank one, which remains ungrouped. Let's address the blank first by first clicking in order to select it, and then selecting group. Then we can set a name in here, and then we just set it to a more meaningful name of unknown to point out the fact that we really don't know what this blank corresponds to. Then when we hit enter, well, we also have an unknown group. So now, from the original 10 distinct values for engine fuel type, we are down to 3 groups and then 2 ungrouped values. So of course, our visualizations will be a lot simpler now. To get an idea, let's just hit OK. And this is what we end up with. At the very top, you can see that there are 4 different groups, if you will. Flex fuel, petrol/gasoline, unknown, and also other. So with that, we now have an idea of how to group categorical data within our Power BI datasets into specific groups. In the next video, we will continue working with these categorical groups and explore some of the other options which are available when working with them. In the previous video, we successfully created our own customized groups based on the distinct values in the engine fuel type field of our car data table. This allowed us to simplify the values which apply to engine fuel type from a total of 10 distinct values, including blanks, over to 4 different groups, which include an unknown. As we have with all bar charts we have worked with so far, we can hover over individual bars to get additional information from the tooltip. So in this case, the engine fuel type is blank. However, the groups which we have defined points to an unknown value. And then moving over to the longest bar in our visual, this still maps to the engine fuel type of flex fuel, premium unleaded required. However, there is also the more simple group name of flex fuel which this belongs to. So each individual bar still maps to the original values of engine fuel type in the dataset. However, later on, we will make sure that there are different bars corresponding to each of our customized groups. First, however, let's complete the work when it comes to setting up our engine fuel type groups, for which we can head over to that field under the Fields pane, and then clicking on the 3 dots next to it. Then, from the menu which pops up, we can choose the option to edit groups. This brings up the same edit group menu we looked at a little earlier. And now, let's make sure that the ungrouped values also map to specific groups, starting with electric. So let's just select that from the ungrouped values list and then click on group. Now that we have a chance to edit the name of the group, let's just call it electric with an uppercase E. And then similarly, we apply a grouping on the diesel values as well. So we select diesel and then select group. And then for the name of this group, we just call it diesel with a capital D. So both diesel and electric are groups which correspond to a single value for engine fuel type. However, at this point, let's just say that natural gas, which currently belongs to the petrol/gasoline group, is not quite a natural fit, if you will, within that group. So we want to ungroup this and then include natural gas within its own distinct group, just as we have for electric and diesel. So for that, we can select natural gas and then click on ungroup below. And now this has also become an ungrouped value. So we can now select it once again and then click on group and then set a name of natural gas for this one. So we now have a total of 6 different groups, including an unknown group. You'll also notice that there is a checkbox which allows us to include ungrouped values into a separate group called other. Of course, in this case, there are no more ungrouped values, so this does not really apply. So when we hit OK, well, we can see the effects of a new grouping in our visualization. Specifically in the legend, we'll now see 6 distinct values for our engine fuel type groups. And just like before, in order to see which of the groups each of the bars corresponds to, we can simply hover over them. Now, what if we don't really care about the original values of engine fuel types, at least in terms of our visualization, given that we now have a new grouping for the engine fuel type values? Well, we can simply modify our visualization. So for that, we first clear out the legend and then also remove engine fuel type from the axis. And instead, the axis will now represent the different values of engine fuel type groups. So we now have 6 bars corresponding to the 6 different groups which we have just created. And now we can see the median price corresponding to our groups. Now it is clear that diesel is the engine fuel type with the highest median price. This is followed by electric, and flex fuel comes in at a close number 3. And it's not so hard to make the case that this particular bar chart is much easier to follow and easier to interpret than the one we had before. One reason for this is that we are down from a total of 10 different values for engine fuel type, some of which were quite confusing and long, to 6 distinct values, which are definitely more manageable, and their names also more meaningfully convey what type of fuel the categories represent. When building reports in Power BI, we often need to take into account that our dataset in its raw form may not quite be usable in a visualization, in which case we can apply some domain knowledge as we have over here in order to simplify the data. More specifically, we applied some knowledge of cars to group different types of flex fuel into a single group, and similarly, different types of petrol or gasoline also into a single group. And while we have successfully worked with categorical data in order to create new categories out of them, in the next video, we will see how it is possible for us to represent numeric values in terms of categories as well. In the previous 2 videos, we successfully mapped groups of distinct values in the engine fuel type field in our car data dataset into our own customized groups. More precisely, we created a total of 6 custom groups, and this really allowed us to simplify our visualization and make them more meaningful to our consumers. We can also see that bar or column visualizations are very helpful when it comes to helping us understand our data. However, what if we wanted each individual bar to represent not a category of values, but a collection of numeric values instead? Well, this is where we will need to apply the binning technique on our data, and that is what we will now explore. First, however, let's clear out this particular visualization so we can eliminate our group from the axis field. So we just have a single bar corresponding to all of the vehicles in our dataset, and we can see that the median price here is about $30,000. But now, what if we wanted to check the median price of the vehicles? not based on a categorical value, but on a collection of numeric values. More precisely, what if we wanted to analyze the median prices of vehicles corresponding to different ranges of engine horsepower? If things still seem a little hazy, well, just follow along with me by dragging and dropping engine HP to the axis, and as you can imagine, we end up with a number of rather thin bars. This is because each bar in here corresponds to a distinct value of engine horsepower, and given that this is a numeric field, well, the possible values here are effectively infinite. More precisely, given that our dataset contains a total of about 11,000 cars right now, well, we may in fact have 11,000 distinct values, which means 11,000 distinct bars. Well, we have already previously alluded to the fact that even 10 bars in a bar chart can be rather confusing. So 11,000 bars is of course entirely meaningless. However, in Power BI, it is possible for us to group different data points together based on a numeric field by effectively grouping together the data points based on a range of values for that numeric field. I can imagine that what I just said may seem a little confusing, so let me elaborate with an example. Let's just say we group all vehicles where the engine horsepower is between 0 and 200 into a single group. Then we can represent that group of vehicles as a bar. Similarly, we will have another group corresponding to vehicles where the engine horsepower is between 201 and 400, and then maybe another group where the engine HP is between 401 and 600, and so on. In other words, we are grouping together the different vehicles in our dataset into a collection of bins. Well, to do that, let's just click on the menu corresponding to the engine HP field and then choose the option to create a new group. What pops up is a form which allows us to create new groups out of the field we just selected, which is engine HP. But given that this is a field containing numeric values, the form which shows up is a little different from what we saw before when we created a group out of the engine fuel type field. So the name of this group has by default been set to engine HP bins, since we are effectively creating multiple bins corresponding to ranges of values for engine HP. As for the group type, well, we will leave this as the default of bin. However, there are two different ways in which we can define the bins. One way is to set the size of the bins, where we effectively map a bin to a specific range of values for engine HP. And then the alternative is for us to explicitly define the number of bins, and the ranges corresponding to each bin will be automatically computed based on the overall range of values for the engine HP field. I will elaborate on this a little later, but for now, let's just leave the bin type as size of bins, which is the default, and the bin size down below is set to 20. So what exactly does this mean? Well, for that, I'll draw your attention to the min value and max values for engine HP, which appears here. So this is a range between 55 and 1001. When we set a bin size of 20, it means that the first bin or the first category will correspond to vehicles where the engine horsepower falls between the minimum of 55 and a value of 20 above that, so 55 to 75. Then the second bin will correspond to engine HP values between 75 and 95, and so on until all different ranges of engine HP up to the max of 1001 are covered. So when we hit OK, we can see that the engine HP bins field has now been created. And now to use that in our visualization, let's remove the engine HP field from the axis and then map engine HP bins in there. Already it is clear that the bars now are a lot less skinny, given that they encompass not individual values for engine HP, but a range of values. However, each bin over here still represents just a small subset of the overall dataset, and as things stand, there are between 45 and 50 bins which can be applied to our dataset. Once again, this can prove rather confusing and creates a lot of noise in our visualizations. So let's expand the bin size by checking out more options for engine HP and then choosing edit groups. Now let's stick to the bin type as size of bins, but the bin size will now expand from a range of 20 to 50. And with this change, well, our visualization is definitely cleaner given that there are fewer categories. At this point though, let's pause and see whether the bins which we have defined are really meaningful. For one, there are still a lot of them, and also there is a significant gap between 1000 horsepower and 800. This of course is mostly due to a single vehicle which has a horsepower of about 1000, and as we saw previously, this is also an outlier in our dataset. So these gaps may really be difficult to avoid, especially if we want to include outliers in our visualizations. However, we can still do with some reduction in the number of bins. For that, well, we can just head over to the edit groups option from a new bin and then change the bin type from size of bins over to number of bins. Then when we make the selection, well, we can take a look at some of the default configurations which pop up. So we can see that a bin count of 46 has been selected, and this corresponds to a bin size of a little over 20. So how exactly is this calculation performed? Well, given the range of values for engine HP and the specified bin count, well, the bin size can be computed using this formula. So if you want the range of values for engine HP from a minimum of 55 to a maximum of 1001 to be split across 46 bins of equal size, well, the size of each bin will be a little over 20. However, 46 bins is still way too much for our visual, so let's just reduce this to a more manageable 8. So in this case, the bin size of 118.25 has been computed using the same formula. So having redefined the number of bins and correspondingly the range of values corresponding to each bin, well, let's just hit OK. And we are now down to a more simplified visual. Let's hover over the top bar and we can see that the median value of the price of the vehicle here is about $1.7 million, and the lower bound of the engine horsepower range is 882. Similarly, the lower bound of engine horsepower for this range of values is 55, and the median price is just a shade under $18,000. And hovering over the other bars in this visualization, well, for one, you will notice that there are in fact just 7 different bars, even though we configure things so that there will be 8 different bins. Well, this is because there is a range of values for which there is no vehicle in our dataset. So effectively, there are no vehicles where the engine horsepower lies between say 750 and 880 or so, which explains the big gap between the top bar and the one immediately below it. So we have now covered how it is possible for us to effectively categorize numeric data by effectively splitting the range of values into a number of bins or groups. When it comes to analyzing data in Power BI, well, there are a number of different approaches which we can adopt in order to get a better understanding of our data overall and extract meaningful insights. We will now continue working with the car data dataset, and while we used this before in this learning path, in order to extract insights based on our own analysis, we will now see how we can get a little help from Power BI using some of its machine learning based features. To start off, we will make use of a clustering feature which is available for scatter charts in Power BI in order to divide our data into a specific set of clusters. Well, let's move along and create the clusters first before delving into the use cases for the clusters. Well, for that, we will need to make use of a scatter chart. So in an empty report page, let's just add a scatter visual. And then, before we resize it, let's just go ahead and add in the fields which will be conveyed in this visualization. Now, if you would like each point or each marker in our scatter chart to represent a specific make of vehicle, we can just drag and drop that field over to the details for our visual. And then, well, let's decide what needs to be plotted along the X and Y axes. And for that, let's stick with some of the fields we have already worked with previously in this learning path, starting with the engine HP, which we will plot along the x-axis, and then along the y-axis, we will represent the MSRP, which is the manufacturer suggested retail price for the vehicle. Once a scatter chart has been created, well, each marker or point corresponds to a specific make of vehicle, and its position along the axis represents the sum of engine horsepower along the x-axis and the sum of MSRP along the y-axis. Of course, when aggregating for a specific make of vehicle, the sum calculation is not quite so meaningful, since it is very much determined by the number of vehicles corresponding to the group. So, in order to get a better representation of the horsepower corresponding to a make, well, from the menu for engine HP, let's choose average as the type of summarization which needs to be applied, and then we do the same for the y-axis as well, so that this represents the average value for MSRP. Once this is done, well, towards the bottom of this particular chart, we can clearly see that an increase in engine horsepower does correspond with an increase in the price of the vehicle. However, this particular visualization is highly skewed thanks to a single data point, which you can see towards the top right. We will get to that in just a moment. But before that, let's take a look at some of the other points which correspond to high values for average engine HP. This represents the make of McLaren, which is a very high-end sports car maker. So the average engine HP is about 610, and the average retail price for a McLaren comes in at a shade under $240,000. As for Lamborghinis, well, the engine HP on average is about the same as a McLaren, but the average sale price is considerably higher at about $330,000. Now, our goal here is to divide all of these data points into a set of clusters. So in effect, we can create groups out of the existing data points based on similar values for engine HP and MSRP. The clustering, however, will be influenced by this outlier in our dataset. The make of Bugatti has a very high value for average engine HP as well as average price. Now, the example we have been working with so far in this learning path is of a fictitious automobile dealership, which has all of these cars in their inventory, and they want to use data analysis to decide on a sales strategy for the upcoming season. Clustering will help us create groups out of the existing data points, and potentially a similar sales strategy can be applied to those data points in the same cluster. With the Bugatti vehicles, though, you can imagine that this is very much special, and this needs to be treated as a group all on its own. But in order to perform meaningful analysis on the remaining makes within our dataset, well, it helps for us to leave out Bugatti altogether, and we can do that for our scatter chart by just right-clicking on this data point and choosing to exclude it. And when we do that, well, first of all, the points in our scatter chart are a lot less bunched up, so it makes it easier for us to hover over them to get additional bits of information and to analyze them more meaningfully. And furthermore, the relationship between engine horsepower and the price of the vehicle is a lot clearer. Furthermore, this clearly tells us that in the 150 to 250 horsepower range, there are a lot of different makes, and the price corresponding to each of these makes does not really vary significantly. However, as we move further towards the right from 250 horsepower, well, the price of the vehicle and the horsepower corresponding to the make do seem to go up in sync. However, given these characteristics of the vehicles, how exactly can we split up our data into a specific set of points? Well, previously in this learning path, we have implemented binning or grouping of data, and this was based on a single column within our dataset. However, if you'd like to create clusters or groups based on multiple columns, well, we can simply make use of a feature of a scatter chart, for which we head over to this menu, which is available by clicking on the three dots. And keep in mind that depending upon your Power BI settings, this may appear towards the bottom right of your chart rather than the top right, as is the case in my Power BI desktop. However, once you click on that, there is the option to automatically find clusters in the data. When we do this, Well, a form pops up where we can define some of the details of the clusters to be created, starting with the name corresponding to the field which represents these clusters. And then there is also the option to explicitly set the number of clusters. By default, this has been set to auto. So Power BI will automatically look at the data and then decide how many clusters needs to be created out of it. We will stick with the default of auto for the number of clusters for now. However, we will define a more meaningful name. So let's call this make of clusters for MSRP versus engine HP. And then we can convey this bit of detail over in the description as well. With that, let's just hit OK, and soon enough, each of the points in the scatter chart have been grouped into a number of different clusters, 5 clusters to be precise. You can see the 5 different clusters, clusters 1 through 5, appear in the legend of this chart and also in the legends section of the visualization properties. If you're unfamiliar with clustering in machine learning, well, you can think of it as dividing your data points into groups where the members of each group are similar to one another, and typically members belonging to different groups are quite different. So from the legend, we can gather that the dark blue markers represent vehicle makes in cluster 2, and we can see that all of the data points corresponding to this cluster are located towards the bottom left of this chart. Cluster 1 is represented by light blue markers, and all of these points can be found towards the extreme right, but not towards the top. In fact, this data point here is in a cluster all on its own. This represents the make of Maybach, so this is the single point in cluster 3, and we can see that this points to an average engine HP of just under 600 and an average price of over $500,000. The fact that this make is in a cluster all on its own points to the fact that Maybach is rather different from each of the other makes, at least in terms of average engine horsepower and average price. However, moving along to the points in cluster 5, we have the brand of Maserati, and we can take a look at the average of engine HP and MSRP over here. Now let's move on to one more point which is in a cluster all on its own. This is the make of Spiker. Now that we have got a glimpse of many of the different clusters, let's zoom in on the most densely populated one. This is cluster 2, at least in my case, and this includes, among other brands, the make of Alfa Romeo. Each cluster, of course, does have its own boundaries, and this represents one extreme end of cluster 2. At the other extreme, we have the brand of Plymouth, which is considerably lower priced, and its engines are a lot less powerful. However, the clustering which Power BI has performed tells us that Plymouth has a lot more in common with the brand of Alfa Romeo, which is part of the same cluster, as opposed to, say, Maserati or Maybach, which are in different clusters. Now, to draw attention to a specific cluster, we can just select that from the legend. So if we select cluster 5, all of the other markers become a little more transparent, which makes cluster 5 points more prominent. We already saw that Maserati is one of the makes which belongs to this cluster, and now we can confirm that Porsche is also part of it. But what exactly does this tell us? Well, it tells us that Porsche and Maserati do have a lot in common in terms of engine horsepower and price, which means that potentially these makes appeal to similar customers and similar marketing techniques can be adopted for these brands, as opposed to, say, Plymouth and Alfa Romeo, which are in a rather distant cluster. Let's move along and focus on cluster 4, and the single marker corresponding to this, pointing to the brand of Spiker, is now highlighted. Let's move along and focus on cluster 3, which we saw contains the single make of Maybach. And let's move on and examine cluster 2, which has the highest representation among our clusters. So the brand of Lotus is also part of this. And then moving on to cluster 1, well, one of the data points here represents the make of Ferrari. So the clustering algorithm here has pointed out that Ferraris need to be treated differently than even Maseratis and Porsches, given that on average, these vehicles are more expensive and also a little more powerful. So we now know how the technique of clustering can be used in order to segment our data points into a number of groups. And while we previously accomplished this based on the values in a single column, clustering allows us to do this using multiple dimensions. And significantly, it can identify groups without any input from us. In the next video though, we will continue exploring how the clustering can be tweaked to suit our own purposes and instances where it can be more useful than the specific case which we just covered. In the previous video, we applied clustering on the data points in a scatter chart. Each marker here represents a single make of vehicle, and the position of the marker is determined by the average engine horsepower and MSRP for a make. Now, when we automatically applied clustering using the default configurations, we ended up with 5 different clusters, where 2 clusters, specifically clusters 3 and 4, contain just a single data point. However, the 3 other clusters do contain multiple makes. So what exactly does this tell us? Well, as I said before, when there are multiple points in a cluster, it means that those points do have a lot of common attributes, and points which are not in the same cluster are typically more different than they are alike. So we see here that cluster 2, represented by the dark blue markers, point to vehicles where the price is relatively low, though they do cover a reasonably wide range of engine horsepower. And then we have cluster 5, represented by the pink markers, where we move into the territory of more powerful engines overall, and also a slight increase in price. Then we have the light blue clusters, cluster 1, and these are vehicles which are both expensive and very powerful. So with these 3 clusters, which represent multiple makes, well, we could potentially come up with 3 different marketing strategies in order to improve the sales for the vehicles in each cluster. For example, cluster 2 points to more mainstream vehicles, so regular marketing can be applied. When we move along to cluster 5, you could say that it is only auto enthusiasts who will go for vehicles where the engine horsepower is on average greater than 300 and which do cost a little more than the conventional vehicles. So these may be customers who do like to have a little fun when they drive. However, price is a significant factor when they make a purchase. And then when it comes to cluster 1, represented by the light blue dots, you could argue that the potential target customers here are those who are less sensitive to price. However, luxury and performance may be more important to them. As a data analyst, it is more important for you to identify these patterns and these clusters when analyzing data, and let the decision makers in your organization come up with what exactly to do with this bit of information. However, you still need enough domain knowledge to understand that creating these clusters of points is important for analysis. Alright then, let's move along and see how the clustering can be configured. And for that, well, let me just expand the fields pane so that you can see that a new field has been created corresponding to the cluster groups. Now, let's just say we want to change the number of clusters which are identified, given that there are 2 clusters here which contain just single data points. Well, for that, let's click on the options for this particular field and choose the option to edit clusters. At this point, a newly created cluster field can be changed by us explicitly setting the number of clusters. Before we do that, however, I'll draw your attention to each of the 5 clusters which already exist. So on the left, we can see that cluster 1 contains a total of 6 items. Cluster 2 is by far the most populated with 30 elements. And then there is cluster 5 with 8 items. Now, however, let's change the number of clusters to 3 and then hit OK. At which point the clusters are recomputed and we now have 3 different clusters. When we click on cluster 3, we can see that once again this contains just a single point. However, cluster 2 now contains more data points than it did previously, but this still points towards the bottom left of our scatter chart. However, some of the points from the adjacent cluster in the last run are now included as part of cluster 2. This includes the make of Porsche, which is now in the same cluster as the brand of Plymouth which we saw previously. And finally, let's move on to cluster 1. This still represents the high-end vehicles and Hovering over one of the points, well, we get the make of Rolls-Royce. So now that we have created 3 different clusters, well, we can see that there are effectively 2 clusters containing multiple vehicles. So we can effectively divide each of the vehicles in our inventory into 2 sets. Well, at least based on a combination of engine HP and price. However, upon closer examination of the data, you will notice that it is just the engine HP which seems to separate cluster 2 and cluster 1. If you draw a vertical line from just a little below 400 horsepower, well, we effectively have the same 2 clusters. So in this regard, you could say that clustering is really not that different from the binning operation which we performed earlier on in this learning path, where we created bins based on a single numeric column. However, clustering is more powerful than that. And to demonstrate that it can work with data in multiple dimensions, we'll just need to change our scatter chart a little bit so that the clustering is applied not just on engine horsepower and average price, but on a different combination of fields. In this particular case, there is a clear relationship between the average of engine horsepower and MSRP, which is why the split effectively seems one-dimensional. Now to change the data, let's remove our newly created cluster field from the legend and also the engine horsepower from the x-axis. However, we will retain the average of the vehicle price along the y-axis, and we will retain make for the details so that each marker corresponds to a single make of vehicle. However, in order to represent the true power of clustering, along the x-axis, we will now include a field which is not related to the average of MSRP in quite a linear form as engine horsepower was. More specifically, I'm going to drag and drop the popularity field. From a previous video in this learning path with the title Aggregating Duplicated Values, we know that popularity is a value which is duplicated for each make, and that it is in fact unique for each make. So, in order to accurately represent the popularity for a make, well, we can apply the average summarization, or we could also use the median. I'm just going to stick with the average though. And here is the relationship between average popularity and average price for each make of vehicle. Significantly, you can see that there is no clear relationship between these two variables. Towards the top left is a vehicle which is very expensive on average, but is also not quite so popular. And then towards the bottom right, there is a brand which is very popular and clearly not that expensive. And there really is no clear single line which we can plot to show that these two fields are correlated in any way. So now it is time for us to automatically find clusters which will give us some more meaningful and interesting insights based on the average vehicle popularity and price. Sure enough, this form pops up where we can set a name for the cluster. I'm just going to leave everything as the default and let Power BI decide how many clusters need to be created. And the answer is that a total of 5 clusters are created. Cluster number 5, represented by the pink markers, seems to be the most densely populated, and these are vehicles which are neither very popular nor very expensive on average. Then the purple markers represent cluster number 4, and here the vehicles have average popularity and again are not too expensive. And then along the right, we have a handful of orange markers representing very popular vehicles. So in this case, we can say that clusters 3, 4, and 5 are mainly different in terms of popularity, and that it is a single dimension which sets them apart. However, it is cluster 1, which is represented by the light blue markers, which make things a little interesting. These are vehicles which are as popular as the vehicles in cluster 5. However, these are more expensive. This is a clear indication that both average of popularity and price are considered when building the clusters. Let's move along then and edit the clusters, and then let's rename our new field to something a little more meaningful, and then use this more detailed information for the description as well, and then change the number of clusters to 4. And with this change, well, we do have a total of 4 clusters. However, it looks like what were previously clusters 4 and 5 have now been collapsed into a single cluster, which is cluster 4. Alright, let's just focus on cluster 4 then. We can see that the make of Porsche is part of this cluster, as is the brand of Cadillac. So both of these represent the higher end of the market in terms of price, but clearly these also are reasonably popular. However, these are also part of the same cluster where the make of Chrysler is represented. Let's focus on cluster 3 then. This contains 4 different points, including the make of Ferrari, which is quite expensive and also has a reasonably high popularity rating of about 2700. BMW is also part of this cluster, which is more popular but less expensive than Ferrari. And Ford is also part of this, which is much cheaper than any of the other brands in the same cluster and is also very popular. In fact, this is the most popular brand. And then focusing on cluster 2, there is just a single point here, representing the make of Maybach, which is of course very expensive, but doesn't seem to be very popular based on the metric followed by this dataset. And finally, we come to cluster 1. So this shows that the brand of Lamborghini does not have a particularly high popularity rating, though of course it is quite expensive. And the same can also be said for Rolls-Royce. So what exactly does this clustering tell us? Well, there are certain brands which are high in popularity, even if they're not particularly expensive, which could mean that customers generally like their vehicles and may stick to their preferred brands when they make another vehicle purchase. However, brands which are expensive and not quite so popular may require some advertising in order to generally increase the awareness of their brand and potentially to improve their overall image. And this mode of thinking was only possible due to the clustering which we just applied on our data. We'll now continue with our analysis of the car data dataset we have been working with so far. However, we will now analyze it from the perspective of time. More precisely, we will make use of the year column, which points to the model year of the specific vehicle, to see how the relationship between price and horsepower varies with the model year. And later on, we will also see how a number of other factors also vary with the model year. So effectively, we will be performing some time series analysis. And typically, when you hear the phrase time series analysis, you should automatically think of line charts. However, we will now make use of a scatter chart and see how a time dimension can effectively animate scatter charts. So once we include a scatter chart in our report, I'll go ahead and expand it so that it occupies the entire available width. And then following that, well, we'll configure the chart. First, by dragging over the make field over to the details so that each marker corresponds to a single make of vehicle. Along the x-axis, we will include the engine horsepower, and then along the y-axis, the price of the vehicles. We have already seen this before, so before making changes, I'll just switch to focus mode. So we have a larger visual now. However, we already know that by default, the engine HP has been summed up, which doesn't quite make sense. So we can change this to average, and then we apply the same summarization to MSRP. So we choose average over here as well. And this is the visual we end up with. Towards the top right, we have this marker which stands out and represents the make of Bugatti. And given that this is so much of an outlier, in order to improve our analysis, we can simply exclude this from our dataset. So we just right click and choose exclude. And now the data points are a little more spread out, which definitely makes analysis just a little easier. So here we can see the relationship between average engine horsepower and average price over the entirety of our dataset. However, what if we would like to analyze this relationship not as a whole, but for each individual model year for our vehicles? Well, this is something which can be done in a Power BI scatter chart. We just need to scroll further along in the visualization configurations and then add in the year column to the play axis. So I'll just drag and drop this field to this particular property, and you'll observe that the visualization has changed. Towards the top right, we have the model year, and we can see now that each of the points represent the relationship between the average engine HP and the price of each make for this specific model year, that is 2017. Further down in the scatter chart, you can see that there is an axis which corresponds to the different model years, starting with 1990 and ending at 2017. So we can say that in our inventory, we have vehicles which were first launched in 1990, all the way down to vehicles launched 27 years later in 2017. Now there is a reason why this particular configuration for a scatter chart is termed a play axis. This is because this chart is effectively animated, and we can see its effect by hitting the play button. This starts off with the model year of 1990, where we can see the relationship between engine horsepower and price. So the prices here are all relatively low. However, as this animation plays further along, we can see that the points keep moving a little bit, although they are all rather flat overall, until we get to the year of 2001. This is where we have a handful of makes which do have very high values for engine horsepower and are also considerably more expensive than the other vehicles. So while this animation does allow us to see how the relationship varies with time, if you would like to pause this animation at some point, we can just hit the pause button, and now it has stopped at 2004. Well, at this point, we can go on and perform the typical analysis which we have seen so far. So, at the extreme end, we have the brand of Porsche, and even models from the year 2004 command an average price of $440,000. Hovering over some of the other points, we have the brand of Scion at the other end, with an average price of just under $13,000 and an average engine horsepower of just over 100. The Scion brand has been discontinued from the year 2016, so this will feature in the 2000s, but will not appear in the latest year in the dataset. However, a fictitious dealership still has this brand in their inventory, and we have an idea of what these cars are worth. So, from the point of view of the DA-100 certification exam, and also when you perform your own analysis for your organization, keep in mind that it is possible for us to animate a scatter chart and convey the information at different points in time by using the play axis. So we now have some idea that the play axis effectively serves as a dynamic slicer. Now before we continue exploring our data over each year, let's add in one more dimension over to this scatter chart so that it conveys not just the make, engine horsepower and price, but also conveys the popularity corresponding to each make. We can do this by dragging the popularity field over to the size configuration of our visual. And then, of course, we will need to set this to the average popularity. And now, the location of each marker points to the horsepower and price, and then the size of each marker corresponds to the brand's popularity. When we hover over one of the larger markers, well, this represents the brand of BMW. And of course, when we make use of the size dimension in a scatter chart, there is a serious risk of overlapping markers. Now, in this case, we can see that Porsche happens to be quite popular, even though it is on one extreme when it comes to the price and horsepower. But now, with this new size dimension added to our visual, we can hit the play button once again to see how price, horsepower, and popularity vary with time. In the case of our dataset though, keep in mind that the popularity will remain constant for each brand and will not change with time. And when you're ready to perform a deeper dive into a specific year, you can just hit the pause button. I'm going to pause at 2004 once again. And then we can head over to the marker towards the extreme right. And this still points to the brand of Porsche. Given that this is a scatter chart, we can convey additional bits of information using the color as well. So let's point to the groups of engine fuel types which we had created previously and add this to the legend. And the 6 different categories of engine fuel types are also conveyed here. This also means that there are additional markers, given that we will need to aggregate based on not just the make, but also on the fuel type. And now when we go on and hit play, well, we can see how the relationships change over time. And significantly, we will observe that in the 1990s, most of the vehicles pretty much ran on petrol or gasoline, indicated by the pink markers, and then flex fuel, represented by orange, begins to make an appearance in the 2000s. Electric vehicles are represented by the dark blue marker, and these only make their appearance first in the year 2012. However, there are many more dark blue markers as we head towards 2017. So, with this animation, when we examine our data from the perspective of time, we get many more interesting insights. We can, of course, effectively rewind by dragging over this slider, and we can pause at 2010 when there are no dark blue markers pointing to electric vehicles. We do have an orange marker corresponding to flex fuel, and this represents the make of Bentley. We can then drag the slider further until we see some interesting bit of information. Well, I'm just going to pause at 2004 since this points to the purple marker corresponding to unknown, and hovering over this, we can see that this corresponds to a brand of Suzuki. And then we can scroll further along towards the past where there are more and more pink markers, but then let's move forward once again until we see the first appearance of an electric bubble. So this is the dark blue marker towards the left, and hovering over it tells us that this corresponds to the make of Toyota. So this specific bubble represents electric Toyota vehicles. And given that we are aggregating based on make as well as engine fuel type, we will find multiple appearances of the same make. So this large bubble corresponds to the make of Ford for their petrol or gasoline vehicles, and we can see that the average price here is about $48,000 with an average engine horsepower of 550. So very powerful and expensive Fords here. However, the other big bubble here corresponds to the make of Ford once again, but where the engines are capable of taking in flex fuel. That is a mix of gasoline and methanol or ethanol. So we have now seen how scatter charts can effectively be animated by effectively allowing us to view data from the point of view of time, where effectively we get the snapshots of our data at different points in time. In our example, we will see how the relationship between engine horsepower and the price of the vehicles varied over time, and also how different fuel types were introduced for engines at different points in time. In the previous video, we saw how we could effectively perform a time series analysis of our data by introducing the year variable in the play axis setting for a scatter chart. However, it is a line chart which is most closely associated with time series analysis. And we can now go on and add one of those over to our report. So for that, let's switch over from focus mode back to the report view, and let's introduce a line chart in this report page. So I'll just click on the bottom half where I would like the line chart to appear, and then make the selection from the visualization pane. And then I'm just going to leave some room for a slicer, which I'm going to add a little later. So I'll just resize this line chart and then configure it. Along the x-axis, we would like the year to be rendered, since in this line chart, we will take a look at how many vehicles we have in our inventory from each model year. This means that once we have included year along the axis field, we can include the count of any categorical field along the values, as long as we know that this does not have too many blank values. So with the count of make along the y-axis, we effectively plot the number of instances where make has a non-blank value corresponding to the given year. So the count of vehicles for that model year. And now we can analyze this data. Of course, this line chart just takes up half this report page now. So I'm just going to switch to focus mode so that we can focus on this visual. And this gives us a clearer idea of how our inventory varies for each model year. For instance, it is clear that for the model years between 1990 and 2000, there are hardly any vehicles in the inventory. There is a slight uptick from the year 2000, another rise from the year 2007 or so, and then the peak is hit in the year 2015, with 2017 being the latest year for which vehicles are available. We can of course hover over the individual points to see the exact counts corresponding to each year. So there are 1652 cars corresponding to the 2017 model year, 2154 for 2015, and just a shade below that for 2016. As you might expect with automobiles, there is a greater stock of newer cars on offer in this dealership. Of course, there are a fair number of older cars as well, though there is a significant difference between 2014 and 2015. And then as we go further back in time, the inventory generally tends to fall, though the numbers remain fairly consistent in the earlier part of the 2010s. Alright then, so we now have a clearer idea of how the inventory has varied over time overall. Now, if you would like to perform more detailed analysis, we can further break down the count based on a categorical value. For instance, we can drag and drop the engine fuel type groups field which we created earlier, so that we have a breakdown across the different fuel types. So this is included in the legend property for our visual, and it is now clear that overwhelmingly the vehicles in our inventory use petrol or gasoline as the fuel. There are a few instances of flex fuel and also diesel and a handful of electric vehicles as well. But given the vast disparity in the numbers here, it does make sense to hover over the visual to get more detailed information. So for the year 2016, for example, there were just 203 flex fuel vehicles on stock and 7 electric vehicles. And of course, almost 1900 vehicles which ran on regular petrol or gasoline. While we already had some hint of this when we played the animation for the scatter chart, electric vehicles did not really make an appearance in our visual until the model year of 2012. So there is a single electric vehicle on stock from that year. And it is also clear that until the late 1990s, there were just two fuel types represented, petrol and diesel. Significantly, one way in which this line chart varies from the scatter chart, which included a play axis for the year, is that the scatter chart only allows us to view the data for 1 year at a time. That is, when we include the year column in the play axis. However, in this line chart, we have the full picture for all the years from 1990 to 2017 for this dataset. Now, when it comes to performing a time series analysis, it's not that one chart is better than the other. Each of them serve their own use cases. For example, a line chart allows us to examine trends over time, while the use of a date along the play axis in a scatter chart allows us to perform detailed analysis of the data at different points in time. More specifically, we can examine the relationship between two variables. Now, I did mention in the last video that introducing a date field along the play axis for a scatter chart effectively serves as a dynamic slicer. However, let's see what happens now if we were to introduce a Power BI slicer visual into this report and whether it has any influence at all on the scatter chart. Well, for that, I'm just going to click on this empty space in the report page and then choose to include a slicer here. And the field which will be represented along the slicer is the model year. So we can now select a range of years in order to perform more detailed analysis. So I'm just going to slide each end of this slicer, and once the charts have updated, you can see that both visuals have in fact been impacted. So the text is not quite so clear, but the start year now has been moved from 1990 to 1997. The x-axis of the line chart now begins at 1997, and even the slider beneath the scatter chart, which represents the play axis, now starts at 1997. So both visuals have been affected by this slicer. I'm going to drag the slicer from the other end as well. So the range of dates now start from 1997 and go on until 2010. And once again, both visuals have been affected. Now, if we were to head over to our scatter chart and then play this visual, the animation will begin from the year 1997 and then go on until the upper bound of our range set by the slicer, which is 2010. So we now have a better idea of the different ways in which time series analysis can be performed in Power BI. In this demo, we will continue working with the car dataset which we have been analyzing so far in this learning path, but now we will make use of the key influencers visual. This is one more visualization where Power BI gives us some help in our attempts to understand our own data. So what exactly can key influencers help us with? Well, in a nutshell, it guides us towards the most important factors which influence a metric which we are analyzing. For example, if you'd like to know the factors which influence the highway MPG of a vehicle, the key influencers visual will examine all of the different data points within our dataset and then figure out how changes in other fields within the table influence the highway MPG. We will get more into the details of the key influencers as we implement it in this demo. So let's get right to it. And specifically, we will focus on the different factors which affect the MSRP or the retail price of the vehicles in the dataset. First, however, let's create a card visual so that we can take a look at some of the overall metrics related to the price. So once the visual is in place, let's drag MSRP over to it. And by default, an overall sum is calculated. But what we are more interested in first is the average price. So once we make that selection, well, we see that the average price of a vehicle in the dataset overall is a little over $40,000. Alright, let's move along and take a look at the median price. Again, I'll place in a card visual, drag over MSRP to it, and then compute the median summary. And the median price is just a shade under 30,000 US dollars. So with these two values, we have an idea of the value of the cars within our dataset. Given that the average is considerably higher than the median, we can say that there are a handful of very expensive vehicles which do pull up the average. And we know this from a previous analysis of this dataset. However, the questions we will now look to ask are, what exactly contributes towards the price of a vehicle? So, among the existing columns in the car data table, how does the make of the car influence the price? Are there certain makes which bring up the overall price? And if so, what exactly are those makes? All of these questions will be answered by the key influencers visual. And before we get to that, let's just clean up our report view. I'm just going to remove this card visual and then repeat the trick for the average card as well. And then we can just add in this key influencers. And then I'll just resize it so that it occupies more of the report page. And then I'll draw your attention to the properties which can be configured for this visualization. There is an analyze property, and this is where we will place in the field which we wish to analyze. Our goal is to figure out what factors influence the price of the vehicle. So we can just drag and drop MSRP into the analyze property. You can already see that the visualization has changed a little bit. We can take a look at key influencers. There is also a top segments tag, all of which we will explore in just a little bit. However, in the middle of the visual, you can see that there are no fields mapped to the explain by property. This is where we can place one of the columns in our car data table to figure out how different values corresponding to that column have an influence on the MSRP. Before we get to that though, let's make sure that the MSRP is not aggregated and ensure that its aggregation has been set to don't summarize. And then, well, to explain how the MSRP is influenced by different values for the make, let's drag make over to explain by. And immediately we can see that the visualization does convey some important bits of information. First, however, I'll draw your attention towards the top left, where we can decide whether we want to see the different values of make which cause the MSRP to either increase or decrease. By default, this has been set to increase, and we can see the different values of make which cause the MSRP to go up. There is a little column chart over here which contains a single column for different makes of vehicle which lead to an overall increase in the vehicle price. So we can see that by far the brand of Bugatti is the one which causes the most significant increase in vehicle price, whereas the overall average of vehicle prices in our dataset is about $40,000. The average Bugatti costs over $1.7 million. This tooltip, however, also points out that within our dataset there are just 3 Bugattis overall. So It not just points out how different Bugattis are from the average vehicle, but also how many of these vehicles exist in the whole dataset. The next influencer when it comes to causing the prices to go up is the make of Maybach. We can see here that the average Maybach is over $500,000 more expensive than the average car in our dataset, and there are a total of 16 such vehicles in our inventory. And then we can just go a little further down these bars over here towards the ones which don't have as much of an influence on the overall vehicle price. For example, I'm just going to hover over one of these bars towards the end. This represents the make of Lexus, and at an average MSRP of just about $47,000, it is not that much more expensive than the average vehicle overall. And then moving along from this column chart, we can take a look at this visual on the left. Here, there are different values corresponding to the make, and the little circle over here tells us by what amount the average price corresponding to that make is different from the overall average. And as you might expect, this visual on the left is linked to the column chart on the right, given that the selection of Lamborghini over here has highlighted the Lamborghini column in the accompanying chart. To see this interaction in effect, we can select Bentley from this left visual, and the Bentley column gets highlighted in the chart. So, we can play around with this key influencers visual, but importantly, what exactly does this tell us? What are the interpretations we can come up with looking at this data? Well, the most obvious one is that there are certain makes which are more expensive than average, and with this selection of the make BMW, we can see by what factor it is more expensive. While the number is not entirely clear in this particular view, it points out that BMWs are about $22,000 more expensive on average than the average vehicle. To get a more zoomed in view, we can check this box so that only the most influential vehicle makes are displayed in the chart, and we can see that the brands of Bugatti as well as Maybach are no longer represented. This is because while those brands definitely commanded a very high average price, there were too few of those vehicles for them to have any meaningful impact on the MSRP overall. In this more restricted view, we can take a look at the more influential brands. For example, when we select Maserati, we can see here that there are a total of 58 vehicles in our dataset corresponding to this make. And while we can continue making other selections from the left pane, I'll draw your attention to the column chart once again. And though it's not entirely clear in this view, you can make out that there is an orange dotted line towards the bottom, and this points to the overall average price of the vehicles in our dataset, excluding the selected make. So now that the brand Bentley is selected, well, we can see that the average of Bentleys is about $247,000. However, the number right above the dotted line tells us that without Bentley, the average price in our dataset is about $39,000. This is as opposed to the average of a little over $40,000 when Bentley is included. So we can say that the presence of 74 Bentley vehicles in our inventory causes the average vehicle price to go up by about $1,000. So it is quite significant when it comes to influencing the average price. Hovering over this visual for Rolls-Royce, well, Power BI has deemed this as the key influencer when it comes to increasing the average price. So the tooltip which has popped up tells us that when you only consider Rolls-Royce vehicles, the average price is about $301,000 higher than the average without Rolls-Royce, and that Rolls-Royce vehicles make up about 0.23% of the entire dataset. Alright then, we now have an idea of how certain values of the vehicle make cause an increase in the average MSRP. The next question then is, what are the makes which bring down the average price? Well, for that, we can make a selection from this drop-down menu where we choose to take a look at the influencers which decrease the MSRP. And now we have a different set of columns in our column chart. Furthermore, the dashed or dotted line is a little more clearly visible now in this column chart, which shows us the average without the selected make. So, The selected make here is Plymouth, and the dashed line tells us that without any Plymouth vehicles in our inventory, the average vehicle price will be about $40,800 as opposed to the overall average including Plymouth, which stands at about $40,500. So, this brings down the overall average by about $300. So, while Plymouths are considerably cheaper than the average vehicle in our dataset, there are again too few of them. Let's now pick a brand which is a little better represented in the dataset as a whole, namely Volkswagen. When we make this selection, we can see that the dotted line now points out that without these vehicles in our inventory, the average price will be about $41,500. And this tooltip points out that Volkswagens themselves are about $13,000 on average lower than the dataset without Volkswagen. So we should expect that the average Volkswagen costs about $28,000. These vehicles also make up over 6.6% of the dataset, and then hovering over the corresponding column in the chart confirms that the average Volkswagen does cost about $28,000. So now that we have an idea of how to use the key influencers visual to identify the values in particular columns which have an influence on the values in another column, in the next video, we will see how we can perform some more complex analysis using the key influencers visualization. In the previous video, we saw how different values for the make in our automobile dataset can influence the MSRP. If you're already quite familiar with automobile brands, well, the insights which we are able to extract will not seem particularly, insightful. You might say that, of course, it is obvious that a Lamborghini will bring up the average price of a vehicle inventory as opposed to, say, a Volkswagen. However, when it comes to identifying the key influencers on a specific metric, the insights offered by Power BI can make up for years of experience. Now let's continue exploring the key influencers visual and move along to the top segments tab here. And this is where we will be able to take a look at not just single values of make which influence the overall vehicle price, but potentially a combination of such values. Now, just below the two tabs at the top, the message tells us that the segments now correspond to those where the MSRP is more likely to be low. And Power BI has identified 5 different segments. So these are as opposed to many more different make values. So some of these segments will represent more than just a single make of vehicle. For instance, let's focus on segment 1. We can see here that the average price of vehicles in this segment is just about $22,000, which is of course considerably less than the average. There are a total of 626 vehicles in this particular segment, and that population count is represented by the size of the bubble corresponding to the segment. And similarly, there are 4 other segments, each of them containing hundreds of different vehicles, but the most populated segment here happens to be number 4. Here, the average vehicle price is just about $28,000, but it does contain over 1,100 vehicles. Let's zoom in on this segment and take a look at what exactly it represents. So we can see here that this segment is defined by those vehicles where the make is Chevrolet. This is what is conveyed in the segment definition on the left, and then towards the right, we have 2 different charts. The bar chart shows us that the average price of the vehicles in the segment, that is, the Chevrolet vehicles, is about $28,000 versus the overall average of $40,500. And then the donut chart right below that points to the overall contribution of the segment in our inventory. So it makes up about 9.4% of the data. We can just click on each of the other segments here. Segment 1 is made up of Dodge vehicles, and we can see the comparison of Dodge vehicles versus the overall average. Segment 2 is made up of Ford vehicles. Segment 3 is composed of Volkswagen brands. We have already seen segment 4. And finally, there is segment 5. So in this particular case, the segments don't really give us any additional information than what we have seen before, given that each of these are only composed of single vehicle brands. Let's see if the segments are a little different when we take a look at those segments corresponding to high vehicle prices. So with that selection, well, there is just a single segment and we can just click on it to take a look at it. And from the left, we can see that this segment is defined not by the makes which are part of the segment, rather than by the makes which are not part of it. So there are a total of 7681 vehicles in this segment, and these are composed of all of the different vehicles which are not of the makes Dodge, Chevrolet, Ford, Volkswagen, and Toyota. So what are some of the takeaways from this particular segment definition? Well, for one, we could say that when it comes to devising a sales strategy for vehicles, we can devise one for these 5 brands which bring down the overall price of a vehicle. And keep in mind that these are brands which do sell in large volumes. Makes which are present in the dataset and have very low average prices but are represented in very small quantities do not have a very big influence on the overall price. Alright then, let's move along and then add some complexity to our key influencers visual and see how the definition of the segments changes as a result. So far, we have been trying to explain the variation in MSRP by the make of the vehicle, but now let's try to explain MSRP not by a single field but by a combination of them. So let's go on to the fields menu and drag and drop engine fuel type to the explain by property. What this means is that we will now try to gauge the key influencers of MSRP not merely based on the make of the vehicle but also on the type of fuel which is consumed by its engine. And you can already see the little change in the key influencers visualization. So the column chart on the right still only points to the key influencers in terms of make, but in the chart which appears on the left, we can see that there is now a value for the engine fuel type. So let's just click on this and we can see that the visual on the right has changed. So in this column chart, there are 2 different types of engine fuel types which are represented, and both of these are deemed to contributing towards an increase in MSRP. Now, just in case the text is not quite readable, both of these point to different types of premium unleaded fuel. One of these is flex fuel with premium unleaded required, and the other is just premium unleaded required. And intuitively, this makes sense. If a vehicle is required to have premium fuel pumped in, well, it is fair to assume that it is a premium vehicle which commands a premium price. Alright then, now that we know the different categories of engine fuel type which lead to an increase in overall price, let's see whether there are any fuel types which cause the price to decrease. And in our dataset at least, there is just one, and this corresponds to the fuel type of regular unleaded gasoline. But the influence of this fuel type is also quite significant. We can see that the average price of vehicles which take in regular unleaded gasoline is just a shade above $20,000, but the dashed line at the top points to the fact that the price of vehicles, excluding those which run on regular unleaded petrol, is about $67,000. So this engine fuel type is certainly very influential when it comes to the vehicle price. Now you may recall from the previous demos in this learning path that there are a total of 10 distinct values for engine fuel type. However, from what we have seen, there are just 2 distinct values which cause an increase in the MSRP of a vehicle and a single value which causes the price to come down. What about the other 7 possible values for engine fuel type? Well, the answer is that they don't influence the MSRP of the vehicle enough. At least not enough to be counted as a key influencer according to Power BI. This could be because their average prices are too close to the overall average, or simply because the number of vehicles corresponding to those categories are just too few overall. So we can continue taking a look at the key influencers, which in our case includes the make of Toyota and also the make of Honda, which are quite well represented within our dataset, as is the engine fuel type of regular unleaded. Next, however, we will take a look at the top segments, but before that, we will also explore the different values and segments which cause the MSRP to increase. Then when we head over to the top segment section, well, just a single segment has been identified. And then when we zoom in on it, we can see that this is defined merely by means of an engine fuel type. So when a vehicle is required to use premium unleaded petrol, well, among these vehicles, the average price is over $100,000 as opposed to just about $40,000 overall. And given that such vehicles make up about 17% of the data, they do pack a significant punch when it comes to influencing the MSRP. However, let's now head over to the segments which cause the MSRP to decrease. So we have three different segments now, but let's explore them to see whether any of these are defined by means of a combination of make and engine fuel type. Heading over to the last of these segments, well, we now get a better sense of how exactly segment definitions can help us analyze data in Power BI. So this particular segment is composed of vehicles where the engine fuel type is regular unleaded and the make is Toyota. So these are Toyota vehicles which run on regular unleaded petrol. So just above the donut chart, we can see that there are a total of 666 such vehicles in our dataset, and the bar chart points us to the fact that the average price in the segment is about $27,000 versus about $40,000 overall. Let's navigate to one of the other segments. This is composed of vehicles which run on regular unleaded gasoline, and the make is not Toyota and not Chevrolet. The average vehicle price in this segment is just about $22,000, and it nearly makes up 50% of the entire dataset. So here is where we can truly see the power of the key influencer visual. By identifying such segments based on a combination of fields in our table, it helps us zoom in on factors and the combination of factors which influence a metric such as the price of a vehicle. Of course, you can use this to analyze what influences the sales in a region if you have a different data set, or if you're analyzing data from a streaming service, well, you could check out what factors influence the popularity of a TV show or movie. In the previous videos, we made use of the key influencers visualization to see how the MSRP of a vehicle can be influenced by two different categorical fields. These, of course, are the make of the vehicle and the vehicle style, but now we will see how the MSRP can be influenced by a numeric field and how the key influencers visual conveys that information. So I'm just going to clear out the two fields in explain by and then drag and drop the year field. So how does the model year of a vehicle, that is the year in which a vehicle was launched, influence the price of the vehicle? Well, you will recall that in our dataset, the oldest vehicles are from the year 1990, and we have vehicles as new as from the 2017 model year. Now, the key influencers visual has effectively categorized each of these vehicles based on model year. So there is one group of vehicles where the year is 2000 and earlier. Based on the settings in our key influencers visual, if the year happens to be 2000 or less, the price of the vehicle decreases. So within this set of 1657 vehicles, which are from the model year 2000 and older, the average price is just about $2,500 as opposed to $40,000 overall. And from the dotted line above, we can see that excluding this set of vehicles results in an average price of $46,700. So the presence of these older vehicles in the inventory brings down the average price by about $6,000. Next, let's take a look at the values of model year which cause an increase in the MSRP. So, if the year is between 2010 to 2015, this leads to a significant increase, and this also applies when the model year is greater than 2015. So once again, the key influencers visual has categorized this numeric field by effectively binning the values here. However, the bins are not of equal ranges. The bin 2010 to 2015 comprises a total of 6 years, whereas more than 2015 is just composed of two different model years, 2016 and 2017 in our dataset. Once again, you will notice that the checkbox for only show values that are influencers has been checked, which is why vehicles where the model year is between 2001 and 2010 are not quite represented. Now from this visual, we can of course make individual selections to zoom in on them, and then we can also head over to the top segments. Let's quickly take a look at how exactly some of these segments are defined. Looking at segment 1 in here, well, this just points to a category we have already looked at, where the year is greater than 2010 and less than or equal to 2015. So the average price here is about $51,000. And then when the model year is greater than 2015, the average price is just a shade under $45,000. Just in case you're wondering why slightly older vehicles, where the model year is between 2010 and 2015, are more expensive than the newer vehicles, well, consider the fact that some of the more expensive vehicles in our dataset, where the make is Maybach, Rolls-Royce, or Bugatti, are all from the older model years and not from 2016 or 2017. So now that you're familiar with the key influencers visual, well, you might pose the question, how exactly does Power BI identify these key influencers? For example, when we take a look at the influencers which bring down the price and then head over to this segment, how is Power BI able to identify that a year of 2000 or less causes the vehicle price to drop? Well, when we try to explain the MSRP by the year column, Power BI under the hood effectively performs a linear regression. And if the explain by field is categorical, as we saw with make and vehicle style, a logistic regression is performed. This course delved into the different ways in which insights can be obtained from data in Power BI using a combination of visualizations and analysis features. You kick things off with an exploration of the different ways in which numeric data can be summarized and the context in which these summaries are useful. You covered how the sum, mean, and median statistics, among others, give us different views of the same data and what their limitations are. You then moved on to modeling your data into customized groups in order to represent it in a form which is better understood by your end users. This applied to both categorical fields as well as numeric data where binning is used. You saw the different ways in which groups and bins can be configured. Next, you delved into how scatter charts can be used to identify clusters and how they enable analysis of snapshots of data with a play axis. Finally, you explored the key influencers visual in Power BI, which help you identify how certain metrics in your data are influenced by the values in other fields. You saw how metrics are influenced by a combination of values from multiple fields and how these can help you gain a better understanding of your data. Having completed this course, you can consider yourself an expert in analyzing your data and gathering meaningful insights, which can then be applied to make important business decisions by the consumers of your Power BI reports. You can now use these skills to build reports and dashboard which help drive your organization forward. Or you can dive into some more advanced analysis features available in Power BI, such as forecasting, anomaly detection, and the Q&A visual. So far in this course, we have made use of a number of Power BI features which give us a little help when it comes to analyzing our data. While Power BI previously helped us identify clusters in our automobile dataset and also the key influencers on the price of those automobiles, we will now change the dataset in order to explore some of the other features offered by Power BI in order to help us perform more detailed analysis. And we will begin with the Analyze feature available in some visuals. On the screen in front of you, I have brought up the US Superstore dataset, and as the name implies, this contains information about sales and orders at a fictitious superstore in the United States. The dataset is included in the course materials and can also be downloaded from this URL on kaggle.com. So what exactly does it contain? You'll notice that there is just a single sheet or single table's worth of information here, and it includes a number of different orders which have been placed for products in this fictitious store. Let's take a quick look at what each row in this particular data set represents. So there is a row ID followed by an order ID, and from rows 2 and 3 over here, you can see that the same order ID may appear in multiple rows, each representing a separate line item in the order. Each row has a corresponding order date and ship date, as well as details such as the name of the customer, the country, city, and state to which the order is being shipped, and each state is deemed as belonging to a region as pointed to by column M. Beyond that, when looking at the category, subcategory, and product names columns, you can see that each line item in this particular orders table represents an individual product in a specific order. The sales column points to the total value of the sale corresponding to that line item, and then towards the extreme right, we have the profit generated by the sale for that line item. A lot of the aggregations which we will perform will be when we aggregate the sales or profit based on category, subcategory, or potentially some of the geographical entities such as region, state, and city. Alright then, it's now time for us to load this data into Power BI Desktop and then perform an analysis. Once we switch over to Power BI Desktop, well, at least in my case, you will notice that I have an empty report. Now it's time for us to pull in our data, for which I'll head over to Get Data, and given that the data set is part of an Excel workbook, I'll make that selection here. I'll just navigate over on my file system to this orders file, and then we'll open it up. Well, the navigator in Power BI pops up, and from here we can choose which of the tabs in our Excel file we wish to pull in. Given that there is just a single worksheet, let's just make the selection of orders from here. Sure enough, the preview of the dataset is generated, and once we can confirm that everything looks okay, well, let's just select this and then choose to load with the default settings. Well, it could take a minute or so for the data to be pulled in, but soon enough, you will see that this dataset contains thousands of rows, and once it is ready, we should see the orders table pop up in the fields menu. Upon expanding it, we can confirm the different columns which appear here. Significantly, profit and sales have been marked as numeric, which is why it is possible for us to summarize these values. Beyond that, you will notice that the order date is also something which seems to be treated as a numeric value. Upon clicking it, we can see that this has been cast as a whole number. Given that this is a date, let's just change the type here. From the drop-down menu, I'm going to cast this as a date field. And now we can treat it as a date in our visuals. You can see that an order date hierarchy has been automatically created. Next, let's apply a similar transformation for the ship date as well, which currently is treated as a whole number. But now when we cast it as a date, well, this also has a date hierarchy. Now it's time for us to create a new visual before we make use of the Power BI Analyze feature. And the visual which we will now generate is a clustered column chart, where we will examine the sales corresponding to various subcategories and choose to analyze the potential causes behind high or low sales corresponding to subcategories. If things seem a little hazy, well, they will become much clearer as we go ahead and implement this visual. First, let's drag and drop subcategory along the axis so that there will be a separate column corresponding to each subcategory of products in our fictitious superstore. And then, for the values, let's drag and drop sales. Well, the visual which has been generated gives us the total value of sales corresponding to the different subcategories of products. And then, switching over to focus mode, well, we can just hover over the different columns to take a look at these different subcategory sales. Here we can see that within the furnishing subcategory, the total sales recorded was about $91,700. And then when it comes to the subcategory of chairs, over $300,000 of sales were recorded. And this also applies to the phones subcategory. So, looking at this dataset, we can see that phones and chairs seem to be the most popular subcategories in terms of total revenue generated for the superstore. And before we proceed, well, let's try to put ourselves in the shoes of a high-level manager in an organization which owns the superstore. A manager will want to know why exactly phones and chairs sell so well and what exactly are the factors which influence their sales. In the overall distribution, we can see that phones and chairs are the best selling, as opposed to furnishings and paper, which don't sell as well. Are there any situations though where the story is a little different? Well, this is what the Analyze feature in Power BI will help us uncover. To use the Analyze feature, we can just right-click on any empty portion of the column chart and then choose the option to Analyze. And in this case, we will be pointed to situations where this distribution is different based on various conditions. Once the selection is made, well, there are a number of different visuals which show up, each of which show us different situations where the visuals are different from what we have seen for the overall sales by subcategory. So the first visual here shows us how the distribution will look like when we only consider specific ship modes. By default, it is the second class ship mode which has been shown. So when you only consider those orders which were shipped by means of second class post, how exactly do the sales compare for various subcategories? Well, we can see that in this case, it is the chairs which are the top seller, given that the second column corresponding to chairs is the longest. This is followed by phones, and then we have a distribution which is somewhat similar to the overall distribution, which is indicated by the grayed area. Here, I'll draw your attention towards those points in the graph where there are big gaps between the columns as indicated by the blue columns and then the gray area, specifically towards the sales for binders and machines. When it comes to orders shipped by second class post, you can see that these sales are rather low as compared to the overall sales. Now, if you like what this particular visual tells you, well, you can leave some positive feedback. And of course, there is also the option to leave negative feedback. This will help Power BI learn whether the suggestions made are useful to you. And if you like a particular visual, there is the option to add it to a report page. Let's move on from that, however, and take a look at how the distribution of sales across subcategories is distributed when we only consider orders which have been shipped using standard class post. And you can see here that this very closely resembles the overall distribution. To some degree, this also applies to orders which have been shipped using first class post. Now, in this particular column chart, you'll observe that we are in fact working with two separate y-axes. On the left, we have the values which correspond to the heights of the blue columns, and then on the right, we have the corresponding axis for the grayed area representing the overall sales. This is because we are comparing the proportions of sales for first class posted orders versus all orders. However, it is possible for us to turn off this comparison of proportions and instead look at absolute values. Given that only a handful of the total orders are fulfilled using first class post, there is a significant gap between the overall distribution and the distribution based on first class post. And you'll also notice that the second y-axis is now no longer visible. While we can continue playing around with this particular visual, let's scroll further down and take a look at what other suggestions are made by the Analyze feature. Here we are told that the state from which the orders have been placed can affect the distribution of sales across subcategories. And when we only look at the data from the sales in Washington, well, we can see that the distribution is in fact quite different. So while looking at the overall data points to the fact that phones and chairs are the top selling subcategories, when only looking at Washington state, well, it is tables and binders along with copiers that are the categories which generate the highest revenues. For comparison, we can switch the state over to Texas, and this more closely resembles the overall distribution of sales across subcategories, and this also applies to the state of New York. Though in this case, the sales of machines very closely resembles the sales of phones and chairs. So what exactly can we interpret from this data? Well, we can say that when it comes to the sales of machines, these do sell much more in the state of New York than they do in the country overall. So the organization might recognize that the sales team in the state of New York, who are tasked with selling machines, may be doing a better than average job. Scrolling along, we can see that the region also influences the distribution of sales across subcategories, and the sales in the South region quite closely resemble the overall sales. Now, it could be the case that the consumers of your report may be interested to know that the sales in the south do resemble the overall sales, in which case you can choose to add this visual to the report page. Once we do that, well, we can treat it as any other visual, but first, to get out of this view, we just click on the report page and then resize the visuals over here so that we can view both of these column charts side by side. So we have the sales in the south region by subcategory on the left and the overall sales by subcategory on the right. As with any visual in Power BI, when we interact with one visual, it modifies the query context, which in turn affects the other visuals on the same page. So we now know how the Analyze feature works with the column chart, specifically that it allows us to see what situations cause the distribution to change. In the next video, we will focus on using the Analyze feature in line charts. In the previous video, we saw that the Analyze feature can be applied to column charts, and that helps us see different situations where the distribution across various categories can change. We will now see how the Analyze feature can help us explain increases or decreases in value in a line chart. So you'll notice that I have cleaned out my report page in Power BI Desktop, and we will continue working with the same US Superstore dataset. But now let's go on and add a new line chart to this report. And then once this has been resized, well, let's fill in the different fields for this line chart. First, we will plot the order date along the axis, and then we will plot the profit for the values. As you might expect, the order date has been used as a hierarchy, so this visualization is rather granular given that it sums up the profit for each day in the dataset. And the visualization also tells us something which any employee of the company would really like to see, specifically that the profits have been going up year on year. So this line chart does give us some good news, but we will need to use the Analyze feature to figure out why exactly the news is good, and also to explain situations where the profits may not have risen quite as steadily. So when looking at overall profits over time, even though the profits have been climbing, this does not really present an interesting picture. Let's try to introduce the region dimension and see how that affects the profit. So over the years, how has the profit varied in each region? And now we can see that the overall picture is a little complicated. There are two regions where the profits have increased overall, and then there are two regions where they have dropped between 2016 and 2017. Let's now get a little more granular. Rather than using the entire date hierarchy, let's only take a look at the profits generated by each month. So we eliminate year from the order date and also the quarter. And now what we are left with is how the profit varies across the different months. Now, given that the profits for the months have been aggregated across the different years, this does point to a seasonality in terms of profit. We can see that in pretty much all of the regions, the profits are very high in the month of December, and this makes sense given that this happens to be one of the most significant shopping periods in the United States, and the profits generated in the month of January are universally low across all regions. Alright then, let's do some more detailed analysis. When we zoom in on the month of November, we observe that nearly all of the profits have been generated in the East and West regions. And for all of the orders in our dataset, the month of October was not particularly kind to the South region, where in fact the region ran a loss. Before we dive into the Analyze feature, let me just demonstrate one more feature by right-clicking on an empty portion of this chart and then choosing the option to summarize. Here, Power BI will automatically generate some text which summarizes the line chart for us, and it is up to us to add in some additional text. All of this, of course, can give some very important context to the consumers of our reports, and it is something to keep in mind if you feel that your end users will better understand the reports with this context. Alright then, I'm just going to expand more options here and remove the summary, and then let's move on and take a look at how the Analyze feature can work in this visual. For this, I'll draw your attention to the dark blue line, which represents the profits in the East region, and you'll notice that between August and September, there was a significant increase in the profits. Now, to figure out what exactly may have led to this increase in profits, well, we can just hover over this point which represents the September sales in the East region. And of course, the tooltip points us to the sales in each and every region here. But when we right click and then choose to analyze, we can see that Power BI will try to explain why exactly the profits increased here. And what we end up with are a collection of visuals which point to potential factors in the increase. So the first visual here is a waterfall chart which begins with the overall profits in August for the East region, and this was just about 4.3 thousand. And then for the month of September, the total profits were 12.3 thousand. So what are the different factors which explain this $8,000 increase? Well, from the title of this visual, we can see that this plots profit by month, region, and subcategory. So it is the subcategory which is the new dimension here compared to what we have in our line chart. So what are the subcategories which led to this profit increase? Well, we can see that an extra $3,000 of profits were generated by the sale of chairs. Phones contributed to a $1,900 increase in profits. And then storage and accessories also led to an increase. It was only binders which caused a decrease in profits by a factor of about $1,600. And in the middle, you can see that all of the other subcategories have been combined into an other group. Now, this is a waterfall chart which has been generated, but we can also take a look at this by means of other visuals. The scatter chart has profits for August along the x-axis and profit for September along the y-axis. And we can see that the most profitable subcategory here is chairs, which is right at the top. From the x-axis, we can see that chairs, in fact, generated minor losses in the month of August. However, they are highly profitable in the month of September as indicated by its position along the y-axis. And then looking at binders at the very right, given that this is well above the 0 mark along the y-axis, binders were in fact profitable in September. However, in August, they were just much more profitable. So for the month of September, they did in fact result in a net decrease in profits. Heading over to a stacked column chart, this once again gives us more detailed breakdown of how the profits were affected between August and September. And then we can also take a look at the ribbon chart. One thing to keep in mind is that these charts are all interactive. So we can use them as we would any chart in our report and get additional information in tooltips. This also applies to the scatter chart, which we just took a look at. So all of this information can be gleaned when we use this Analyze feature to get more detailed information about our line charts. So these set of visualizations explain how the subcategory of the products has influenced the change in profits between August and September. I'll just scroll further along over to one more useful visual. In this case, we can see how the city in which sales have been recorded has affected the profits. So we know that there is an $8,000 difference in the profits between September and August. And in fact, over that same period, the profits from the city of New York City also went up by that same amount. And this visual also tells us that there was a significant reduction in the profits from the city of Philadelphia over that period, which was compensated for by increases in profits across other cities in the East region. Now, to get out of this particular view, which explains the increase in profits over the East region, we can just click somewhere outside of this pane, let's just say on our report, and we're taken back. Next, let's focus on one more dramatic increase. This is for the sales in the West region between February and March. So we can just right click and then choose the option to analyze in order to explain the increase. And once again, we can see that the subcategory plays an important role in the difference in profits. So it went up from 2.7 thousand in February to little over 16,000 in March. So what explains this over $13,000 increase in profits? Well, a bulk of this improvement in profits, almost $9,000 worth, can be explained by the increased profitability of copiers. Scrolling further along, we can see how the shipping mode affects the profits. And then scrolling still further along, we can see the influence of city followed by state. So you can see how the analyze feature can help us drill down and then point us to why exactly there was an increase or even decrease in profits. You can already see that this is a very useful tool when it is not entirely clear to us why exactly there is an increase or a decrease in any metric in a dataset. And with the Analyze feature, well, this helps us perform some crucial exploratory data analysis, which can help us decide exactly what visuals we would like to feature within our reports. In fact, we could easily use one of these visualizations which have been automatically generated by using the Add to Report button indicated by the plus sign, just as we did in the previous video. So far in this learning path, we have made use of line charts on a few occasions, including in the last video, where we applied the Analyze feature of line charts. That helped us understand that Power BI is not merely a data visualization tool. Power BI does not merely help us create and format charts into reports, it also helps us perform detailed analysis of the data by extracting a lot of key insights on its own. In this demo, we will continue using the US Superstore dataset in order to analyze this data, and we will once again make use of a line chart, but we will see that this includes a forecast feature which enables us to estimate what the line chart will look like at different points in the future, based of course on the past patterns. To see exactly how this works, well, it helps to clean out the report page, and then we can add in a line chart. I'll just resize this once again, and then let's populate it with the fields. First, let's drag and drop the order date over to the axis. So it is going to be a time series which we generate, and the values which we will plot over time are the sales and revenues. We previously saw that there was an increasing trend for the profits, and at least since 2015, we can say that there is also a consistent increase in the overall sales. So, sales were effectively flat between 2014 and 2015 and then climbed after that, but this merely gives us the details at a year level or an annual level. Given that the order date is represented as a hierarchy, it is possible for us to drill down that hierarchy. If you would like to see how the sales varied across each year and quarter, we can hit this expand one level down the hierarchy button, and we can now see that the increase in revenue is not quite as steady as when we are only looking at it in terms of annual revenues. Here we can see that consistently across all of the 4 years in our dataset, the sales in the first quarter, starting in January, were always quite low. However, the final quarter of the year was the strongest in terms of overall sales. So this is a cycle which has been repeating itself every year. However, there is a year-on-year increase in the quarterly sales. For example, when we compare the sales in January 2015 to Jan 2016, there is an increase, and there is a further increase when we head to Jan 2017. So even the lowest points of the year are getting steadily higher as we move along in time, and this also applies to the highest points. So you can see that the peak in 2015 was somewhat high, but the peak was even higher in 2016 and higher still in 2017. Now the question is, if we were to forecast the sales going into the future, will this seasonality as well as overall increasing trend be accounted for? That is something we will get to later on. But first, let's continue exploring this data without the forecast feature. When we drill down, we can take a look at the sales recorded over each of the months in the 4-year time frame. So once again, we can see that the sales are rather spiky. But now for the sake of simplicity, let's head up one level so that we're looking at the sales recorded over the quarters. And then if you'd like an understanding of the data, you can just hover over the different points to see the total volume of sales. Next, however, let's switch over to focus mode. So the chart now occupies the space a little better. And as the next step, let's plot a trend line to see how exactly the overall sales have been increasing. So for that, we'll need to head over to the analytics pane for the visualization and then expand trend line, where we choose to add a new one. So we can clearly see that there is a trend in the upward direction. Again, this is quite heartening for any employee or anyone associated with this fictitious US superstore. We can give this trend line a more meaningful name than the default of trend line 1. So we can call this sales trend. And following that, well, it's time for us to forecast what the sales will look like going into the future. And conveniently enough, a line chart includes a forecast menu item. Here we can choose to add a new forecast. And the moment we do that, well, you can see that the line chart has been extended to points in the future. So all the way into 2020. Now I recognize that it is well past 2020 by the time you watch this video. However, given this dataset, 2020 very much represents the future. So what exactly does this tell us? Well, beyond the solid blue line which represents the actual sales recorded, there is the solid black line which represents the expected sales going into the future. However, there is not just a solid black line, this is surrounded by a transparent gray region. This region represents the area within a specified confidence interval. When you take a look at the forecast settings, you can see that the confidence interval has by default been set to 95%, and what this means is that the forecasting mechanism predicts with 95% confidence that the future sales will lie within this gray shaded area. There is a lot of math behind this confidence interval calculation, and going into that is beyond the scope of this course. However, let's focus on some of the other key factors of this forecast. First of all, we can see that the forecast length has been set to 10 points. Given that we have drilled down to the level of quarterly sales in our line chart, this means that the forecast has been generated for the next 10 quarters from the latest date in the dataset. Let's play around with some of these settings. First, we can explicitly call this forecast a sales forecast, and then we can adjust the forecast length. You can see that we can specify this in terms of various time metrics. So if you only want the forecast to extend to 10 days into the future, we can make this selection and then scroll down and hit apply. And you can see that the black line now just extends a little beyond the solid blue line. If you were to change to 10 months, well, the forecast extends just a little further then. So we now know how to control for what duration the forecast is generated. Forecasting sales, of course, can help an organization make a lot of key decisions. If the sales are consistently going up, well, there is a stronger case to be made that the organization may need to hire more employees, potentially open up more stores, and maybe even stock up on inventory. One setting which is available for the forecast here is the ignore last property. The forecast is generated by looking at some of the most recent points in the line chart. However, it is possible that the most recent data is not quite representative of the overall data. Potentially, you may have some anomalous months in terms of sales, maybe one-off sales of items which are not likely to repeat in the future, in which case you may want to ignore the last few data points when making forecasts into the future. So, what will happen to the forecast if we were to ignore the sales recorded in the last 3 months, given that the latest 3 months represent October, November, and December of 2017, which is also the quarter which has recorded the highest revenues in our entire dataset? Well, when we hit apply, the forecast is a lot less rosy. So the ignore last property should only really be used if the previous few data points are in fact anomalous. We can of course keep changing this to come up with different forecasts, but now let's go on and play with one more setting, namely the confidence interval. Now you can see that the shaded region around the forecast line is rather broad, and in fact, this gets wider and wider the more we go into the future. This is because this confidence interval in some ways represents a margin of error. To say something with 95% confidence, we do require a wider margin of error. However, if you were to reduce the confidence interval to 80% and hit apply, well, you can see that the margin of error also becomes more narrow. Let's move along then and make this forecast a little more meaningful. Firstly, by projecting into the 10 quarters into the future, and following that, we can set the ignore last property back to 0 since we want all of the quarters to be considered. At this point, I'll draw your attention to the fact that the solid black forecast line seems to follow a rather similar pattern going 8 quarters into the future. For example, we can see that the projected sales for the final quarter of 2018 and also for 2019 seem identical to the actual sales recorded in the last quarter of 2017. And then the three troughs which are projected for the first quarters in 2018, 2019, and 2020 also point to similar values. This is not in line with the overall increasing trend of sales which we have seen when we look at the data from 2014 all the way through 2017. And this is thanks to the seasonality setting. By default, this has been set to auto, which means that Power BI will automatically look for cycles in the data and will have likely detected that a sales cycle seems to occur over 4 quarters. Let's see what happens if you were to change this to 20 quarters instead. And what we see is a significant decline in the overall forecast. Why exactly is this the case? Well, keep in mind that we only really have 16 quarters worth of data in this dataset, which means that when we ask the forecast feature to go back 20 quarters, it will estimate that in the first 4 quarters, the total sales recorded was 0. If you were to change this to 10, which is not quite a multiple of 4, we end up with rather skewed results. Just the shape of the line tells us that this forecast is not quite accurate. However, if you were to change to 8 points into the past, well, the sales from the previous 8 quarters or 2 years will be considered. In this case, the increasing year-on-year trend will also be captured, which is why you can see that the high points forecast for 2018 and 2019 are higher than the ones recorded for 2017, and even the low points in the forecast are expected to be lower than the previous years. So now we can use this forecast to make predictions on what the sales are likely to look like going into the future, and then make decisions accordingly. In the previous video, we saw how line charts in Power BI can be enhanced using the forecasting feature. We will now see how line charts can also be used to detect anomalous data points in a time series. To demonstrate this, I have cleaned out the report page, and we can now add in a new line chart. And once this has been resized, well, let's fill it up with data. First, we can drag sales over to the values. So we will be analyzing sales once again. And then we can drag and drop order date into the axis. So just as we saw in the previous video, we are looking at how sales have varied over time. Now this plots the sales on a year-on-year basis. So let's drill down the hierarchy so that we can see how sales have varied across individual quarters, and then drill down further into how the sales have changed over each of the months in our dataset. So we now have 48 different data points corresponding to the 48 months recorded within our dataset. And before we search for any anomalies, let's take a quick glance and see if there are any patterns which we can detect. As we saw before, it is usually the first quarter which records the lowest sales overall, and we can see this repeated here. The months of January are usually quiet, as we can see for the first data point for Jan 2014. Then there is a dip going into February before sales spike up in March. We can in fact see this pattern for each of the years. In 2015, things are slow in January and February before they pick up in March, and the same can also be seen in 2016, though there is a marginal increase from Jan to Feb. And then the biggest peaks of the year are usually recorded in November or December. Now, any of the artificial intelligence-based features available in Power BI, which includes the anomaly detection tool, is capable of finding such patterns. A data point is flagged as an anomaly only if it does not quite fall into the detected pattern. So what I mean is that very high sales in the month of December or very low sales in the month of February will not be cast as anomalies merely because they represent a spike up or spike down, since that is to be expected given the data we have. Alright then, what exactly are the anomalous points in our data? Well, for this, we head over to the Analytics pane and then scroll down below over to the Anomaly Detection tool. So, when we head over to find anomalies, well, there are a few configurations which we can set. once we add an anomaly detector. So let's just call this anomalies, but before we change anything in the configuration, I'll draw your attention to the visualization on the left, where the actual sales as recorded by the blue lines are surrounded by a gray shaded region, which represent the expected range of sales values over the data points. To understand this, I'll draw your attention towards the first two data points for 2015 for the months of January and February, since these are quite close to the bottom. So the actual sales recorded were a shade below 20,000 for January and maybe about 10,000 for February. However, these sales numbers have not been marked as outliers. This is because they're well within the gray shaded region, which expects that the sales number for these 2 months could have been a few $1,000s higher and could even fall to as low as 0 for the month of February. In fact, this visualization tells us that there were no anomalies detected in the sales for each month over the 4-year period, since anomalies are marked in a different manner. Let's see what happens if we were to change the sensitivity. So if we reduce this to just a little below 60% from the default of 70%, we see that the gray shaded region increases in size. This means that the anomaly detection algorithm is less sensitive to any changes in the sales recorded and is less likely to mark out a particular data point as an anomaly. If you were to increase the sensitivity to 85%, well, the shaded region now gets narrower. However, there are still no anomalies detected. Alright then, let's see what happens if you were to drill down further into the sales recorded for each individual day. Well, this is where there are a number of different anomalies as indicated by the gray markers. So, based on this algorithm, there were no anomalous months in terms of sales which have been recorded. However, there clearly are a number of anomalous days of sales. Now we can play around with the sensitivity here, and I'm going to bring this down to about 51%, and we can see that there are fewer data points which have been marked as anomalous. And then I'll just further reduce the sensitivity all the way down to 22% so that the algorithm is less sensitive to any changes in the recorded sales and is less likely to mark points as anomalous. And now we can see that there are only 2 anomalous days overall. Furthermore, the gray shaded region is now much more clearly visible, conveying that the Power BI anomaly detection algorithm is looking for a range of dates for the sales values to fall within, and only if it exceeds this range will it be cast as an anomaly. I'll just adjust the sensitivity to some value, let's just say 93%, and then hover over some of the true anomalies here. This one was recorded on the 2nd of October in 2016, so in the 4th quarter. The actual sales recorded on this day were $18,452, but the expected value was just $761. Furthermore, we can see that the algorithm also calculated a range of expected values from a minimum of about $749 to a maximum of $772. Of course, the actual sales recorded are well above this range, which is why it has been cast as an anomaly. Let's move along then to the highest point in this chart, which is for the 18th of March 2014, and we can see that the range of expected values was somewhere in the 1500s, but the actual sales recorded was over 28,000. So what insights does this offer us? Well, in the case of an online store, you might expect that the sales will be rather spiky. Anomalous sales may indicate that there were special discounts on offer or potentially some kind of marketing campaign. However, if you don't really know what the root cause is for the anomaly, well, this anomaly detector will draw your attention, and this may be followed up with some detailed investigations. In the case of this dataset, we can see, for example, that on 22nd October 2017, the sales recorded was a little over 15,000, but instead of daily sales, what if you were examining the data related to the average temperature of a machine over a number of different days? If there were certain days where the temperature was abnormally high or abnormally low, you may want to check whether the products manufactured by that machine on those anomalous days do adhere to your quality standards, just in case there was something off. We'll now continue exploring various analytics features available in Power BI to help us understand our data better. Specifically, we will use a Q&A visual, and we will operate this on the same orders dataset containing fictitious order information from a US superstore, and we will see that, as the name implies, a Q&A visual can help a user get the answers which they are looking for as long as they ask the right questions. So there is an empty report which I have now created, and let's take a quick look at the different fields available within our US Superstore dataset. We know that sales as well as profits are numbers which can be summed up based on various categories. As for the categories themselves, they can be found in fields such as subcategory, category, as well as state and region. But then let's go on and add a new Q&A visual over to the report page. And once this is expanded, well, we can see that there are already a few suggested questions based on the available fields. However, I'd like to draw your attention first to the box which appears right at the top, where we can type in the question which we want to ask of the data in something resembling normal English. I say something resembling English because there are a few restrictions which we will soon come across. Going back then to the suggested questions, the first of these is number of categories. So, we can ask how many different categories are present in our dataset, and if you want to ask this question, we just click on this, and we are returned a card visual which returns the count of categories as 3. This is in fact correct. The 3 different categories in our dataset include office supplies, furniture, and technology. So this has effectively counted the number of distinct values of category in that column, and we have got this information by asking a question in something resembling plain English rather than have to extract this by analyzing our data. We can just cancel out of this question if you want to ask something else. And if you're not satisfied with all of the suggested questions here, well, there are additional suggestions which can be made available. Well, one of these here is the average value of discount for each different quantity. So the question here is, does the discount amount vary with the quantity of products in an order? Are there steeper discounts when a customer orders more items? Well, we can click on this to find out. And the answer to this question is given in the form of a line chart. So we can see here that it does not really seem to matter what the quantity is in an order. When the number of items in an order is anywhere between 1 and 8, we can see that the discount rate really doesn't change much on average. So it is about 0.16 or 16% when the order quantity is 7, and just a little higher when the order quantity is 8. When it comes to the higher order quantities, well, it is safer to disregard them because there won't be too many samples with these order quantities. Alright then, we have received the answer to one more question, and this was a suggested question. So we can just cancel out of this view in order to ask one more question based on the suggestions. And if you would like to get back the list of orders sorted by row ID, we can just follow this question, and we get back a table with all of the orders sorted by row ID. This is just to give you an idea that it is possible for us to get back sorted data when asking a question. Alright then, now that we have an idea of the types of questions which can be asked to a Q&A visual, let's cancel out of this view and then ask a question of our own. What is the top order in terms of profit? So we can just ask top order by profit for this, and we get back a single order line item. And to see whether this is in fact quite profitable, let's scroll along to the right and take a look at the value of profit. And at a little over $8,000, well, this is in fact the most profitable order in our dataset. So we now know how to ask a question and get back an answer. And keep in mind that when a table is returned, in this case it's a table with a single row, we can still hover over it in order to view all of the information corresponding to this line item as a tooltip. Alright then, now that we know what the single most profitable order is, we can move on to the 10 most profitable orders. So we close out of this view and then ask top 10 orders by profit. And sure enough, we get back a total of 10 rows of data. Scrolling along all the way to the right, well, we can see that each of these orders are in fact quite profitable. Each line item here has generated over $2,000 in profit. Given that this is a table, it is possible for us to sort based on the profit. By default, it is sorted in descending order of profit, but we can also click on this header in order to sort in ascending order. So now that we have asked a couple of questions of our own, let's try to get a sense of what exactly the pattern is which needs to be followed when asking questions to a Q&A visual. Well, Power BI uses natural language processing in order to translate a question into a query on the underlying data. So you can in fact type in phrases in normal English as long as the phrases are not too complex. In this case, top 10 orders by profit is rather simple overall. Top 10 confirms that we would like to get back 10 data points in total. Orders points to the orders table, so we will get back the top 10 rows from orders, and given that we require the top 10 orders, this means that a descending order sort needs to be performed on a specific column, and that column in this case is profit. However, we can also change the order in which the results are returned. So if we just add in ascending order at the end of our already asked question, the orders are sorted in the ascending order of profit and returned to us, and what we get back are in fact the orders which generated the highest losses. Of course, we can again apply a sorting over here, but now let's go on and see what happens if we do a descending order for the top 10 orders by profit. And scrolling along, we are back to the most profitable orders. So we need to be a little careful when we type in the questions, because in this case, you could say that the question is a little too complex. Top 10 orders by profit was simple enough. However, when we added in descending order, it did not really change the outcome and in fact made the question a little ambiguous. Alright then, let's move along and ask one more question. Once we cancel out of this view, we can ask Power BI to give us the most profitable order in the dataset. Well, it has returned a single row, which is something we can expect, but scrolling further to the right, we can see that this has generated sales of over $22,000, but this was not the most profitable order, and this is because the Power BI Q&A visual has translated profitable to mean sales rather than profits. We can see that in the message just below the text box where we typed in the question, where we are notified that Power BI is showing us the results for top order by sale. To confirm that, let's just click on this suggestion over here, top order by sale, and we get back the same data, which you can confirm when we scroll to the right and take a look at the sale value of over 22,000. So we have now come across a limitation of the natural language processing here. For many individuals, the distinction between sales and profit may not be very important. However, when it comes to analyzing data, this is absolutely essential. However, this does not mean that Q&A in Power BI is not capable of translating profitable to mean profits and not sales. And we will soon see that it is possible for us to teach the Q&A visual how to translate specific words and phrases. For now, however, let's proceed and simply type in show orders, and this will simply return all of the orders. If you're familiar with SQL, this is the equivalent of select star from orders. Moving along then to the next question, we'll now ask Power BI to give us the profit by category. And now we see a bar chart which shows us the total profit across the three categories: technology, office supplies, and the least profitable, which is furniture. Just below the question we have posed, we can see one more way to phrase the same question, which is category and total profit. When we click on it, well, we get back the same bar chart. Let's move along then to the next question. This time we will ask for a visualization which will give us the total sales by order month, and as you might expect, a line chart is returned. And as with any line chart visual in Power BI, this is interactive. So we can now see the sales by order month in terms of a line chart. However, given that in our dataset, the data for each month in fact encompass the sales in that month over 4 different years, a line chart may not be the best representation of how the sales have varied. So You might instead want to view this information in the form of a column or bar chart, and we can do that by simply asking for the total sales by order month once again, and then ask for a column chart. And what we get back is a column chart. So we now know how the Q&A visual works in Power BI, and in the next video, we will focus on teaching Power BI the meaning of a particular word or phrase in the context of a dataset by setting up a synonym. In the previous video, we made use of the Q&A visual to generate, among other things, this column chart which gives us the total sales recorded across each of the different months in our dataset, which shows us that September, November, and December are the months which generate the highest quantity of sales. Now, a question you might ask is, when exactly do we use a Q&A visual? Well, when building reports in Power BI, it is important for you to construct your own story in order to convey important patterns and points which you have gleaned from the data and which may be of interest to any of the consumers of your reports. However, there will still be instances where it is not clear to you what kind of questions your consumers might be asking of the data, in which case you can always leave in a Q&A visual so that they can ask those questions themselves. Now, we will see how we can address some of the limitations when we ask questions of the Power BI Q&A visual. So let's cancel out of this view and then ask the question, what are the total revenues? And from the auto suggest as well as the card visual which pops up, we can see that what we are returned here is in fact the total profit. In the previous video, we saw that the Power BI Q&A visual considered that profitable and sale mean the same thing. And now we can see that it also considers that revenue and profit are exactly the same. To confirm, let's extend this question and ask for the total revenue by order year, and from the y-axis label, we can see that what has been plotted here is in fact the profit by order year. So this is a limitation of the natural language processing which Power BI uses, and at least at the time of this recording, revenue and profit are considered the same. Now, you may be wary of this, especially if the end users of your Power BI reports include the top sales executives in your organization, as well as other financially savvy folks. However, it is possible to teach the Q&A visual that revenues and profits are not the same, and that revenue equates to sales instead. Well, to do that, we can just click on this button to teach the Q&A visual what certain terms and phrases mean. So what we really want is for the word revenue to be mapped to sales rather than profits, and we can do this by navigating over to the field synonyms. Here we can specify certain synonyms for the different fields in our dataset, and once we get to this page, well, we can simply expand the orders table to get a list of the synonyms which have been applied to the different columns or fields. When it comes to orders itself, which is the table, we can see that the terms instruction, direction, as well as edict map to the orders table. So these are not quite the types of orders which this dataset contains, but you now get a glimpse into how the natural language processing for the Q&A visual works. For the field of city, we can see that some of the suggested synonyms include town, metropolis, and municipality, which do make more sense. And then scrolling further along, well, let's get down to the profit column. One of the synonyms here is revenue, which is why the Q&A visual returns the results which we just saw. Clearly, revenues and profits are not the same, and to make sure that these two terms are not confused, we can simply remove revenue as a synonym for profit, and instead we can apply this to the sale column. So revenue is no longer associated with profit, and we can head further down to sale and then choose to add a new synonym. Here we just type in revenue, and then when we hit enter, well, revenue now gets added as a synonym for sales. So if we expect that the consumers of our report will ask the Q&A visual for the revenues associated with various categories, we should make sure that this synonym is set correctly. And while we're here, we may as well make a little change. So income and sales are not quite the same, and income should translate to profits rather than sales. So we can just cancel this out. and then take a look at some of the other synonyms associated with sales. Realistically, of course, you will need to spend much more time setting the synonyms and then removing any confusing synonyms which are associated with the fields in your tables. For now, let's just make sure that things work correctly when we ask for the revenues associated with different years. So when we close out of this view, well, the line chart has now changed. Glancing over at the title for the y-axis, it clearly says sales while it previously said profits. And then, just below our question box, we can see that Power BI is now showing us the results for total sales sorted by order year. So we have now seen how a specific term can be mapped to a specific field in our dataset. However, what if the definition of a term in the context of our data is a little harder to define? So let's go ahead and ask another question for the Q&A visual to return to us each of the loss-making orders. So when we type in loss-making, you can see that the text itself is grayed out. This points to the fact that Power BI does not quite understand its meaning, and this is also underlined in red. We can consider a loss-making order as one where the profit generated is less than 0. From the table which is returned, however, when we take a look at the tooltip, we can see that the profit field is not represented here. And even when we scroll further to the right, the profit column is not available. Given that the table is rather large, Power BI has simply truncated the table itself. And beyond that, what is returned to us are all of the orders. First though, let's fix the fact that we cannot see the profit column. We can simply append the text with profit after loss-making orders, and the profit column now appears. The output confirms that it is pretty much all of the orders which have been returned, regardless of what the value of profit is. So again, we'll need to teach Power BI that loss-making in this context means where the profit is less than 0. So specifically, we want all of these orders where the profit is negative to show up in the results. Alright then, let's set about teaching this to Power BI's Q&A visual. And for that, we can simply click on one of these words underlined in red. When we click, a message pops up telling us that Power BI does not really understand the meaning of the term loss. But we do have the option to define what loss is. So let's just click on this. This takes us back over to the Q&A configurations. And over here, we have the ability to define what loss making really means. First, we can define what loss translates to. And you can see that in the question box towards the top, it is loss which is highlighted. So let's just define what loss means in our context. So in this field, we can define loss in the form of an expression on our orders table. So we simply point this to those rows where profit is less than 0. And once we hit the save button for this to take effect, we immediately get a preview over here. And from the preview, we can confirm that it is only the loss-making orders which show up. So this does look promising, but to test it out, let's close out of this Q&A setup. And now our visual has been refreshed, where we can confirm that the orders which now appear have all generated negative profits. That is, these are all loss-making. So the profit column now appears on the left. We can also see from the text box for our question that the word loss is now underlined in blue, as opposed to red previously. Furthermore, the orders which are returned are sorted in ascending order of profit or descending order of loss, depending on how you want to look at it. And to confirm that it is only the loss-making orders which appear here, let's sort in terms of descending order of profit. And even at the other end of the table which is returned to us, we only see losses, that is, where the profits are negative. So, we have now seen how we can teach the Q&A visual what certain phrases mean by both mapping a word to a specific field in our table and also defining what a word means by means of an expression. Finally, let's head over to the Q&A configuration and then head over to the Manage Terms section, where we can see that there are entries here for both revenue as well as loss, which are words whose meanings we have defined in the context of our data. Of course, if you're unsatisfied with your own definitions, you can always delete the term definition and recreate them if needed. We have now come across several examples where Power BI gives us a big hand in extracting meaningful insights from our data. We will now take a look at a decomposition tree visualization, which also helps us in this regard by essentially aggregating data across various categories and then allowing us to drill down into various subcategories. To see this in action, well, we'll start off with an empty report page, and to that we will add in this decomposition tree visual. Once it has been expanded to occupy the full page, let's just expand the fields menu, and we will continue working with the same US Superstore dataset, which of course includes this orders table. And then you'll observe that it is possible for us to choose a metric which we can place in the analyze property of the decomposition tree visual. This is a metric which we can aggregate across various categories and subcategories. So if you would like to see how the sales can be broken down, well, let's choose sales and then drag and drop it for analysis. Now I'll just adjust some of the formatting for this visualization so that the text is more clearly visible. So from the format pane, I'll just search for text so that we can adjust the text sizes. And you don't really need to follow along with me, since I'm just making adjustments so that the text is more clearly visible. Once this is complete, however, let's head back over to the fields configuration for the decomposition tree. So we know that we wish to analyze the sales recorded across a fictitious US superstore. However, across which dimensions? From the visualization, we can gather that the aggregate of the sales recorded in our dataset is about 2.3 million, just a shade under that. But how exactly are these sales distributed? Well, this is where we can drag and drop fields into the explain by section, and we can start off by explaining the sales in terms of the different categories. So there are 3 different values for categories, and now when we add this to the explain by field, you'll observe that there is a little plus sign which appears next to the bar for the total sales. This means that we can expand the total sales and explain it by means of the different values for category. So we can just click on this plus button, and we have 3 different options here. There is high value and low value with a little light bulb next to it, conveying that these are AI or artificial intelligence related features. We'll get to those a little later, but for now, let's choose to break down sales by the different categories. And this is what we end up with. We can see that out of the nearly 2.3 million in total sales, about 836 million were recorded in technology, 741 million in furniture, and about 720 million in office supplies. So, the category which has recorded the highest sales is technology, and you can see that this has the longest bar. The bar corresponding to furniture is expressed in terms of the total technology sales, as is the bar corresponding to office supplies. However, we can see that when we break down the total sales by category, it is technology which has the highest value. And this brings us to the AI related options which we saw. In order to break down the total sales, to see those in action, let's close out this expansion by means of category. And now let's see what happens when we hit the plus sign next to sales and then choose to point us to the highest value the sales can be decomposed to. And this points us to the category of technology. So the lowest value which sales can be divided into should point to office supplies. And to confirm that, let's eliminate this level of the decomposition tree and then hit the plus sign and ask to be pointed to the lowest value which sales can be broken down to. And sure enough, we are pointed to office supplies. Furthermore, when you take a look at the label of category at the top of this level of the decomposition tree, you will notice a little light bulb next to it. This means that this level was generated by means of an AI feature, and while being guided to the highest and lowest values for the breakdown of sales seemed rather trivial in this case, a little later we will see that when we have multiple fields which can be used to explain the overall sales, that feature becomes much more important. For now, however, let's just hover over each of these individual bars, and the tooltip does give us all of the information which we need. Now, one of the cool features of the decomposition tree is that we can in fact decompose the total sales or any metric across various dimensions and not just category. So let's just clean out this particular tree first, and then to the explain by field, we will drag and drop the subcategory as well. Now, when we choose to expand the overall sales, we can break it down either by category or subcategory or allow the AI to perform the split. For now, however, let's explicitly pick category, and we have the sales broken across the three distinct values for category just as we did before. However, this time, it is possible for us to drill down a little further as implied by the plus sign next to each of these categories. So when we click on the one next to technology, well, we can choose to drill down further by subcategory. So the $836,000 in sales recorded in technology was split across phones, machines, accessories, and copiers, with phones recording the highest sales at $330,000. Alright then, we have now included some additional complexity in our decomposition tree. Let's clean out the visual just a little bit so that we can start off from the overall sales. But to enable further drilling down, we will now include the region field in the explain by property. So it is now possible for us to break down the overall sales across the different values for subcategory, category, as well as region. And when we hit the plus sign next to sales, well, we can choose which of the different fields we wish to expand the sales by. Before a selection is made, I'd like to draw your attention to the explain by section of the visualization. So the order of fields there is subcategory, category, and region. However, it is not that same order which shows up in this context menu where we have category, subcategory, and region. This is because the ordering of the fields in explain by is really not that important. This will get reordered depending on what selections we make in the decomposition tree. So if we first choose to split the sales by region, well, you can see that region appears at the top in explain by, and significantly back in the decomposition tree itself, we can see how the sales have been split across the 4 different regions in our dataset. Alright then, let's drill down a little further. The West region has recorded $725,000 in sales overall, but now let's see how this is split across the various categories. And here we can see the distribution. It's an almost even split across the 3 categories, with furniture gaining top spot. However, let's further divide the numbers for sales for furnitures in the West region, and this time we will draw our attention towards the low value, and this points us towards the furnishings subcategory. So we can now play around with this visualization, but significantly, we have seen how the decomposition tree allows us to decompose a specific metric, sales in this case, across various dimensions. So we have decomposed sales in terms of region, category, and subcategory. But now let's focus on some of the most specialized features available for this visual. We can see that there are no options available in Analytics. But when we head over to the Format section, well, under Analysis, there is the option to enable or disable AI splits. We have already made use of some AI splits before. So let's see what happens if we were to turn it off. And when we do that, and then choose to expand the sales, well, we see that the high value and low value options which we saw before no longer show up. But now to truly demonstrate the power of the AI split, let's first split across categories, and we have the 3-way split of sales now. And at this point, let's choose to re-enable AI splits. And now, what if we wanted to see how technology sales are split, and specifically, we want to be directed to either the region or subcategory which has the lowest value when technology sales are broken down. So this is where the power of the high value and low value comes into the picture, where we don't want to make the decision to break down the technology sales by subcategory or region and let the AI decide based on the breakdown which generates the lowest value. And we are directed to the South region, which recorded $148,000 in sales. Now you'll observe that there is also an analysis type setting which we can configure. And to understand that, we can first perform a little cleanup. And let's choose to expand the overall sales in terms of the highest value when a breakdown is performed. What this means is that we have been directed to the category of technology, which represents the highest absolute value for sale when we break down the overall sales across any of the distinct values for category, subcategory, or region. But relative to the other categories, technology sales are really not that high. Given that there are three distinct categories, we can expect that if the sales were evenly distributed across them, then each category would have about $765,000 in sales. The sales recorded for technology at about $836,000 is just about 1.09 times an even split. In relative terms, though, this may not represent the highest split. We will get to that a little later, but for now, let's further break down technology, again, based on the highest value in terms of absolute numbers, and this is the split we get. But now, if we were to change the analysis type from absolute to relative, well, we get a very different split. So phones is considered to be the highest value in terms of a relative split, and this is because at about $330,000 in sales, this subcategory stands out when splitting the overall sales. This is because if the sales were evenly split across the 9 different subcategories, each of those would record $255,244 worth of sales. So relatively speaking, the phone subcategory is 1.29 times the even split and represents a better relative split than the technology category. In fact, when we split across two different levels, we can see that the East region at $100,000 of the phone sales represents about 30% of the overall sales when it is expected to only cover about 25%. So we have now covered the many different ways in which a metric such as sales can be decomposed. This course introduced you to some of the analysis features in Power BI, which use AI and other advanced techniques to extract key insights from your data. First off, you use the Analyze feature to understand how the distribution of values of a metric vary with different categorical fields. You saw how a column chart would look different when applied to different fields in your data. You also apply this feature to explain the fluctuation in sales displayed in a line chart. Next, you apply the forecasting feature in a line chart to estimate future sales for a fictitious organization. You then identified outliers in terms of daily sales using the anomaly detection feature and saw how the sensitivity of the algorithm can be adjusted to find more or fewer anomalies. You then moved on to the Q&A visual and delved into how this allows users to use plain English to extract insights from data. Finally, you created and configured a decomposition tree to break down the sales of a fictitious organization across different categories. Having covered this course, you can consider yourself a data analysis expert, especially when using Power BI. You understand exactly what visuals are required to gain an accurate understanding of your data and how to optimally use Power BI's features to extract useful and actionable insights. You are all set to build accurate and meaningful reports which your organization can use to drive the business forward. However, to truly master Power BI, you should also take up a course which delves into how the Power BI service can be used to collaborate with teammates and share your reports with end users, while also streamlining your report development process. We will now dive deep into a topic which is quite important for the DA-100 certification exam and crucially needs to be understood correctly for it to be applied in your own organization. The topic here is user permissions. We will now explore this in a number of different dimensions, starting with role level security, and we will then explore user permissions at the Power BI services workspace level as well. On the right, you will observe that we continue working with the orders table from the US Superstore dataset, and this dataset is part of your course materials and alternatively can be downloaded from this URL. So before we dive into the implementation, let's quickly discuss at what levels permissions may need to be set. Well, if you have looked into the learning path, Design Data Models in Power BI, you will know that row-level security ensures that users of your Power BI reports only have access to their own data. In the context of this orders table, you may want to set up access such that specific users can only view their own sales-related information. And to get a better idea of how this can be set, let's switch over from the report view over to the data view. Once the orders table has been loaded, well, consider the fact that for each line item in these orders, there is a category. For the sake of our example, let us assume that there are specific users who should only be able to view sales from a specific category. And there are 3 different categories in this dataset: office supplies, furniture, and technology. We will now implement row-level security for a report out of this orders table, and will later explore how this applies in the Power BI service. For that, however, we will need to head over first to the model view, where we currently have a single table. However, we will now need to create a second table which maps categories to individuals who will access our reports and whose access needs to be restricted to their own categories. Alright then, let me clear things up a little bit here. And to import the data we will be working with, let's head over to Get Data and choose to import information from an Excel workbook. And this is the Category Managers workbook, which is part of your course materials, and we will explore its contents in just a little bit. Once we navigate to it on our file systems and choose Open, and from the navigator, we can choose the Category Managers worksheet. When we do that, we can see what this workbook contains. So things are rather simple here. There are 2 columns, UPN and Category, where UPN represents the user principal name of a user who is expected to use our workbook. And these are managers of the different categories. Now, I already have set up Power BI service accounts for Diana and Elroy, which is why it will be possible for me to show you how exactly we can set the permissions for these users. In your case, if you do have access to 2 different users for Power BI service, you can enter their credentials here instead in the Category Managers table. And then, the category column maps them to the category of products and orders from our dataset, which they should be able to view. In the UPN column, you'll observe that I have used what look like email addresses for 3 different users in my own organization: Diana, Elroy, and Charles. So I have been able to create separate accounts for these individuals who are all fictitious, and we will explore the permissions of Diana and Elroy when row-level security is enforced. So, Diana should only be able to view the details related to furniture orders, Elroy should only be able to view office supply related information, and Charles should only be able to access technology orders. Significantly, the categories in the category column exactly correspond to the different values of category in the orders table. Alright then, before we load data, you'll observe that UPN and category, which are the column headers, now appear as the first row in this table. So rather than hit load and then get the data into Power BI desktop with the default configurations, we will choose transform data in order to promote the first row as the header. This of course will bring up the Power Query editor, and then we just head over to this particular option to use first row as header and then make this selection here. Once that is done, well, sure enough, you'll observe that UPN and category are now the headers of this category managers table. So we can just hit close and apply. And the moment we do that, in the model view, you will observe that the category managers table has been successfully loaded and that it has already been mapped to the orders table. So the link between the 2 tables confirms that these are related. But before we proceed, let's quickly glance into the nature of this relationship. And this will give us a glimpse into how exactly row-level security can work. So we can just right-click and choose Properties. And this shows us that the category column in the orders table is mapped to the category column in category managers. Also, the cardinality of this relationship is many to one, with many orders mapping to a single row in the category managers table, and the cross-filter direction is set to single. This means that the category managers table can be used to filter the contents of the orders table, so that category managers will only be able to view their own orders. And this is the basis of row level security. Alright then, now that we understand the nature of this relationship, we can just click out of this by hitting OK or even cancel. And now we can go ahead and explore the data view and confirm that at the bottom there are 9994 rows which are visible, so nearly 10,000 rows in all, without any filtering applied or any row level security implemented. In the category managers table, all 3 rows are visible. And now let's head over to create a new report to the report view. So our goal now is to create a new report and see what it looks like for the different users once row level security has been set. So we can confirm that the category managers table is visible here. And with that said, let's go ahead and create a new clustered column chart in this report. And the chart itself need not be particularly complex. Remember that we are more interested in the implementation of row level security here. So I'm just going to drag and drop subcategory into the axis and then sales into values. And we can see here from the report that it is phones which has the highest number of sales, followed by chairs and storage. Significantly, a total of 17 subcategories are visible here, as represented by the 17 bars. At this point, I'll just head over to the format view and then apply some formatting changes in order to increase the text size to help with visibility. And a good practice with column and bar charts is to turn on data labels. So now, we can view the exact values corresponding to each bar. Alright then, once the formatting changes have been applied, we can view the exact numbers. And once the formatting is done, let's head back over to the field view, where I'm just going to rename the first page of this report from page 1 to column, since this represents a column chart. Next, let's go ahead and add a second page to this report. And in this page, we will add a new donut chart. So once again, the chart itself can be quite simple. For the legend here, I'm just going to drag in the region field from the orders table. And then for the values, we'll plot profits. So we now have a region-wise breakdown of the profits. Before moving on, once again, I will apply some formatting changes here so that the text is more clearly visible. And we will need these in order to view how the values change when row level security has been established. Alright then, once the formatting has been applied, let's quickly take a look at the overall split here. At nearly 38%, it is the West region shaded in purple, which represents the biggest proportion of sales, followed by the East region shaded in dark blue at about 32%. When users are only able to view their own data, well, it is likely that these proportions will change. So now, let's apply one more touch by renaming this page of the report as well to the more meaningful donut. So now that we have a column chart and a donut chart, well, in the next video, we will go ahead and see what each of these charts look like when row level security has been implemented. Having set up a simple report containing 2 separate pages here, well, let's head back over to the first page of the report containing the column chart. And now it's time for us to establish row level security so that different category managers are only able to view their own data. When that is done, the distribution of sales across the different subcategories will be quite different. So let's quickly take a glance at this chart, because when we revisit it, it is likely that the ordering of the bars as well as the values attached to them will have changed. So in order to set up row level security, we will need to head over to the model view, and more specifically, we can head over from here over to the Manage Roles option. This is where we set up the permissions for each user, and then to simulate the view for each user and ensure that the row level security has been configured correctly, we will head over to the View As option. Alright then, let's head back to Manage Roles then and click so that the Manage Roles menu comes up. From here, we will need to create a new role. Once we make that selection, let's give this role a name. I'm just going to call this User Sees Own Data so that the name is rather descriptive of what it really represents. This role will apply to the Category Managers table, where we restrict the category managers to only have access to their own row within this table, and given that category managers is related to orders and the cross-filter direction between these two tables is set such that category managers will filter orders, it means that a category manager will only be able to view their own orders. For that, let's expand on the options for category managers and then choose to add a filter on the UPN column. So here, we can specify exactly what the filter will look like by means of a DAX expression. When we set the right-hand side of this expression to user principal name, this means that a user will only be able to access those rows of data in category managers where the user principal name matches the UPN column. In the Power BI service, the user principal name will map the username with which the user signed into the service. So in this manner, a user will only be able to access those rows to which they have been given permission in this category managers table, and this is how row level security is set. Now we can hit this button here in order to validate the DAX expression, and if you don't see any notification, it means that the expression is all good. So we can just go ahead and hit save. So with that done, well, row level security has been set. But when we head over to the report view, looking at the column and donut charts, well, we still have access to all of the data, but we'll only be able to view the effects of row level security if we were to head back over to the model view and then impersonate the permissions of a specific user. So at this point, let me just expand to the full view of the top menu, and you can see the Manage Roles and View As options here. I'm going to choose View As, but for that, I'll minimize this pane once again so that visibility is improved, and then make the selection. At this point, we will need to specify what user we wish to view the data as. I'm going to select Other User, and then type in one of the three category managers we have set. Let's start with Diana at lunicorn.com. In your case, of course, you may be using a different UPN, so you can just enter that in here. And then check the box next to the role which we just created to make sure that this is activated. And then to view what the report will look like to Diana, we can just hit OK. And I'll just remind you that Diana is set to be the category manager for the furniture products. So from the model view, let's head over to the data view, and Diana has only access to her own row of information within the category managers table. So this is how row level security has been set up. Diana only has access to her own row in category managers, but if you're familiar with row level security, you will know that this filter also applies to the tables which category managers is related to. Now, since we have set Diana as the manager of the furniture category, when we head over to the report view, well, it is only the furniture subcategories which are visible in the column chart. So while we previously had access to 17 different bars corresponding to the 17 subcategories in our dataset, we are now down to the 4 subcategories which Diana has access to. So within these subcategories, it is chairs which has recorded the highest value of sales, followed by tables. For a sanity check, we can head over to the donut chart, and in the case of Diana, we observe that there are just 3 different regions which are represented here. So there have been sales recorded in the west, east, as well as south regions, but none in the central region. So we now have confirmation that both the column and the donut charts look very different when row level security has been set up. At this point, we can turn off our viewing of the report as Diana by clicking on the Stop Viewing button, which appears over here. And the moment we do that, we are back to a full view of the sales, which is why the donut chart now once again has 4 different sectors corresponding to the 4 regions, reflecting the breakdown in overall sales, and then over to the column chart, where once again the subcategory breakdown with the full list of orders is now visible. For a quick sanity check, we head back over to the model view and then back over to view as so we can simulate the permissions of one more user. And this time I'm just going to enter the details of Elroy at lunicorn.com, who you will recall is the manager of the office supplies category. So once we enable the role and then hit OK, we are now viewing as Elroy. We can confirm from the data view that Elroy only has access to the office supplies row, and then over to the report view, where it is only the subcategories within office supplies which are now accessible. These include storage and binders and go all the way down to the $3,000 of sales recorded within fasteners, with a total of 9 subcategories out of the total of 17. And then over at the donut chart, well, in this case, there are 4 different regions here, but you can see that the breakdown is quite different from the overall sales. So within Power BI Desktop, we now have confirmation that row-level security does seem to work as expected. Later on, of course, we will need to see that we get a similar view when we sign in as Elroy from the Power BI service. Alright then, once we stop viewing as Elroy, we are back to the full dataset view. And now, we can go on and publish this report over to the Power BI service, where we will not only check out row-level security, but also how access can be configured at the workspace level. Now that we have applied and then tested out row-level security within Power BI Desktop, we can now publish our report over to the Power BI service and then test out the permissions at that level. Beyond that, we will also see how we can configure workspace level access. But for that, let's switch over from Power BI Desktop over to a web browser, where we can navigate over to the Power BI service. This is accessible from powerbi.microsoft.com, and then you will have to sign into the service. Once we make this selection, well, in my case, I have previously signed in as Diana at lunicorn.com, so I'm just going to pick that account. Then enter the password corresponding to Diana. And then after signing in, well, I'll just confirm that I would like to stay signed in. And I'm now brought into the home page of the Power BI service for this user Diana. Keep in mind that if you have set up multi-factor authentication in order to sign in to the Power BI service, you may need to follow slightly different steps in order to get to this point. Now, however, let's head over to the Workspaces menu. And from here, we can now select the option to create a new workspace. So it is not the default My Workspace which we will use. And then from this Create Workspace page, let's set a name for the workspace first. I'm going to call mine LuniWS, and then just enter some description. Then there are a number of different configurations which are possible to set for the workspace at this point. To get a glimpse into them, we can expand the advanced settings. And first of all, you'll observe that we can specify a contact list. We can map this to a OneDrive workspace. And then there is the license mode. Note that I am making use of the Pro license, and this is something which will be required in order to test out a lot of the configurations which we will now explore. You'll observe towards the top that I have in fact activated a trial of this Pro license, and this is available for a total of 60 days from the day of activation, and I still have a fair few days left here. Alright then, now that we have taken a look at the different configurations, let's just hit save. And with that, we now have a brand new workspace. So of course, this workspace is currently empty, but we will address this with our next step, where we publish a report to this workspace. And for that, let's head back over to Power BI Desktop. And then from the home menu, let's choose the option to publish this report over. At this point, well, we'll need to make sure that our PBIX file has been saved down. And once that is confirmed, well, if you haven't quite signed in to Power BI service from your desktop, you may be prompted to enter your sign-in credentials. In my case though, I am already signed in as Diana@Lunicorn.com, who also happens to be the owner of the workspace we have just created, which is LuniWS, which is why the two workspaces available in Diana's account are visible here, and I'm just going to select the newly created workspace. Then within a few minutes, you should see this success message confirming that the report has been published over to Power BI service. And then to confirm that, let's switch over to the browser. And yes, in my case, the workspace and RLS report, which I had created on my machine, and then the corresponding dataset, which of course includes the orders as well as category managers table, have been uploaded to the service. At this point, however, what will we see when we navigate over to the report? Will Diana only be able to view her own sales? Or given that she is the administrator of this workspace, will she have access to everything? Well, the answer is the latter. Given that Diana owns this workspace, all of the data, including all 17 of the subcategories, are accessible, and the report view will in fact cover the entire dataset. A little later in this learning path, we will see that row-level security only really applies to the viewers of a workspace and not the admins. Now, however, let's head back over to the workspace view in order to get an idea of the types of operations which can be performed here. So from the workspace, you'll observe in the menu at the top that there is a settings option, and then we can also configure access to different viewers of the Power BI service. Then focusing on the contents of the workspace, you'll observe that the first one points to a report as indicated by the typed column, and then the second object here is the dataset. As touched upon, this is what includes the data underlying our report, which includes both the orders and category managers tables. Towards the right, you will observe that there is a next refresh column. This is something which is available to datasets where we can schedule when exactly the data will be refreshed from the underlying source over to the cache in the Power BI service. You may recall that by default, this dataset is loaded in import mode, which means that all of the data is cached. Scrolling over to the right, the other settings which are possible for both the dataset and the report include an endorsement, a sensitivity, which can be used to mark certain datasets as well as reports as confidential, and then there is the option to include a report in an app. Now you may recall that a report is essentially what we will share with the consumers or the end users of our report. A workspace is meant for us to work with our collaborators, whether these are teammates or other teams within our organization who may help us build the report. So now that we have an idea of how a workspace effectively serves as a container for reports, well, let's set about towards one important topic when it comes to the DA-100 certification, which is the set of permissions which can apply to a workspace. To set this up, we will need to head over to the access configurations, and this is where we can add other members to our workspace as either administrators, members, or contributors, or simply viewers. It's now time for us to explore the similarities as well as differences between these four different roles. Each role, however, will apply to different users, so let's start off by selecting another user from our organization. In my case, I already have such a user set up in the form of a fictitious member called Elroy. So we'll need to supply the email address of this user. And following that, we also need to specify what their capacity is with regards to this workspace. So we can just expand this dropdown to take a look at the four different types of roles. And these roles here are listed in the descending order in terms of the number of privileges which apply. Admin, as you can imagine, can pretty much do anything with a workspace. And at the other end of the spectrum, we have a viewer. So when we add a viewer to a workspace, we're essentially allowing them to view and interact with our reports, but not really do anything more than that. And a viewer is also the level at which row-level security applies, since each of the other different types of roles will make all of the data accessible. For Elroy though, let's just select viewer as the role for now and then choose add. And then down below, we now have two different users who can access this workspace. Diana, who is an admin, and then Elroy, who is a viewer. So for this user addition to take effect, let's just close down. And after that, well, in order for us to enable row level security, the row which we defined within our Power BI desktop, where users can only view their own data, needs to be enabled, and the user Elroy needs to be added to that role. This is something which needs to apply to a data set rather than a report. So we can just expand on the settings for a data set and then choose the option to configure its security. We will get to the other options available for a dataset a little later, but for now, let's proceed with the security settings. And then in the menu on the left, you will see that the role which we had set up in Power BI Desktop, user sees own data, is visible here. However, it does not currently have any members, which means that this role does not apply to anyone just yet. We can of course add additional members, which I'll just go over and do by specifying Elroy's email address. This can be followed by hitting the add button so that Elroy becomes a member of this role. And we can then go ahead and hit save. What this means is that the role user sees own data now applies to Elroy Evans. And then, before we test it out, we will make one more change to the workspace. We can head over to it by using this link. And then from here, we will now proceed to create a new app from it. You will recall that there is a one-to-one relationship between the workspace and the app. So there is just a single app for each workspace and represents how exactly we choose to share a workspace with the final consumers of our reports. At this point, the user Elroy has been configured as a consumer rather than a collaborator with only view permissions in the workspace. And we will use the app to test out their permissions. So from the Create App page, we can specify the name of the app itself. I'll just call this Looney WS app, so nothing too creative here. And then set a description. And before we publish this app, let's take a look at some of the other options which are available here. From navigation, it is possible for us to define how exactly a consumer can get to this app. You'll observe that it is possible for us to have links to different reports within the workspace, but we won't be getting into that for now. Instead, we'll head straight over to the permissions view, and this is where we can define permissions at a granular level for the app. Again, we will leave things as a default, and instead head back over to the setup view, and then scrolling a little further down, you'll see that we can specify a support site, apply a logo to our app, and also set a theme color. For the theme color, I'm just going to make a random selection here and select a brownish shade, and then leaving everything else, including the contact information config as is, we'll choose to publish the app. The moment we do that, we will be prompted for a confirmation. We can just choose to publish, and in a few seconds, you should see this message that the app has been successfully published. And significantly, a URL to the app will also be supplied. This is the URL which we can use to distribute the app and the reports within it to our consumers. And this is something you should keep in handy, though of course it is always possible to retrieve the URL. Alright then, now that we have successfully published our first app over to the Power BI service, in the next video, we will test out the permissions with regards to an app and the workspace in general. In the previous video, we had published a report over to a workspace, and then we had also created an app out of the workspace. The URL to that app is available here, and we have the option to copy it and then share it with the consumers of our report. Let's just copy it over and then make note of this URL so that we can come back to it at a later point. And then to check out our app itself, we can just navigate to it from this button for now, so that we will have a view of what Diana will be able to see in the app, since Diana is the owner of the workspace and the app as well. And this is what a Power BI app looks like. In many ways, this is similar to the report view in Power BI Desktop. So we can navigate to the different pages on the report from this menu on the left. In our case, we have the column and donut pages, and then the bulk of the page is occupied by the report page itself. So the full column chart with all of the details is available here. This is given that Diana is an admin for this workspace and hence the app. Next, let's head over to the donut page and we can view the donut chart for the full dataset. We can, of course, interact with it just as we could in Power BI Desktop. Another thing to note here, towards the right, you will notice that the filters pane is available just as it is in Power BI Desktop, so we can apply filters on the data which is rendered in our charts. However, keep in mind that it is not possible from an app for us to configure the report. So we cannot add or modify report pages, create new visualizations, and so on. Alright then, once you're done interacting with the report, let's take a look at some of the other options which are available. So at the top, you can see that there is a file menu which includes, among other options, the option to generate a QR code for this app. The export menu will allow us to view this app inside Excel, for example. And then to make the best use of the available space, we can hide the navigation pane so that the report page occupies the full width of the screen. Alright then, now that we're done playing around with the app, let's go back where we are navigated to the home page of the Power BI service. From here, when we navigate to the apps menu option, well, our app is accessible here. Alright then, now that we know that our app has been published and we also know what the app looks like to the owner of the app, let's see what it looks like from the point of view of a viewer, that is a consumer. Well, for that, we will need to sign in as the user Elroy, which was created earlier with view permissions on the workspace and who has also been added to the role which we had created earlier, which allows viewers to only view their own data. And to sign in as Elroy, I'm going to head over to a different browser where I have navigated to powerbi.microsoft.com, which is of course the URL for the Power BI service. And then we'll choose to sign in. And I have already previously signed in as Elroy from this browser. So I'll just select that user, supply the password, and then choose to stay signed in. Alright, I'm now in the home page of this user Elroy, who of course only has view permissions on the workspace and hence the app. Now let's head over to the Shared with Me menu option. This is where we will get access to the different reports which have been shared with the user. And sure enough, the Workspace and RLS report is here. So the question is, what exactly will Elroy see when navigating to this report? Well, we now have access to the donut chart, and what we can see here is that while 4 different regions are accessible, the split confirms that Elroy only has access to the office supply line of products. That is, Elroy is only able to view the data corresponding to his own category. So, at about 43%, the share of the Western region is higher than in the overall dataset, which is about 38%. And then let's head over to the column chart, where we can confirm that just 9 different subcategories are accessible, corresponding to the office supplies category. So, we now have confirmation that row-level security does work at the Power BI service. Elroy is only able to view their own data within the service, even though they still have the ability to interact with the charts and do pretty much else as long as they don't really change anything or view the data which they're not supposed to have access to. So this is where the user is able to access the report directly in Power BI service. But what if they wanted to view the app instead? Heading over to apps, well, we see that there are no apps available in this particular view. However, what happens if the user were to navigate to the app via the URL? Well, as mentioned earlier, it is usually the URL to the app which will be shared with the consumers, and assuming you have copied over the URL to the app, we can pull up a new tab and then navigate to it. And once this is done, well, the app is visible to this user as well. And importantly, the view which is available is restricted to those subcategories which the user has access to. So we only have the 9 subcategories, with the highest selling one here being storage. So we now know that for a user with view permissions on a workspace, whether they access the report from the Power BI service or the corresponding app using its URL, they'll still only have access to the same data. And for a quick sanity check, let's just confirm that we can interact with this visual as this user. And yes, the tooltip information is available. And then heading over to the donut page, well, Elroy can only view the sales distribution for the office supplies category. Alright, now they're satisfied that the view permissions on the workspace works as expected. Let's close down this tab to the app, and then from the Power BI service, let's head over to Workspaces. Given that Looney WS was shared with this user, well, this is accessible from here. However, clicking on it confirms that the view of the workspace is quite different. This user is able to view the report within this workspace, but does not have access to the dataset. And significantly, from the menu options, you can see that there is no way for a user with just view permissions to change the access around a workspace, and there is no option to create any new objects within the workspace. Just to confirm the type of account for this user, pulling up the user information, you can see that the license type has been set to Pro over here as well. So it's not anything around the type of license here. However, switching back to the different browser where I'm logged in as Diana, who is the workspace admin, and then navigating over to the same Looney WS, well, you get an idea of how this workspace view is different. There is the new menu in the top left, which allows the creation of various types of objects within a workspace, and we will get to those a little later. And significantly, the access button is also available in order to configure access. In the next video, we will explore the different workspace roles and then take a look at the types of permissions which are available with each of them. In the previous video, we saw how row-level security applies to users with view-level permissions on a Power BI workspace. We also saw that there were 3 other levels of permissions which can be applied on a workspace, specifically admin, member, and contributor, and we will now explore each of those roles in a little more detail. Note that row-level security will not apply here. I'm currently signed into the Power BI service as the user Diana, who is an admin of this Looney WS which was created earlier, and it includes a report as well as a dataset with the name Workspace and RLS. Now, to test the permissions associated with the other workspace roles, we head over to Access, and we can see that the user Elroy Evans is currently a viewer. Now, we can expand the menu here and then set Elroy to be a member instead. A member is a type of user who can do nearly all of the things which an admin can. However, they don't have the ability to add other admins to a particular workspace, and they cannot even delete a workspace. So once we set Elroy as a member, let's go on and close. And to test out the permissions for the user Elroy, I'm once again going to switch browsers over to the browser where Elroy is signed in to the Power BI service. So we previously saw that Elroy only had this view of the Looney WS. So only the report is available, and the access button is not visible here, and neither is the new menu. However, let's go ahead and refresh this page so that Elroy's new permissions become activated, and this is how the view changes. So there is a new menu towards the top left, and the access button also shows up here. And significantly, when we head over to the options related to a report, well, there are many features available here, including the option to save a copy, create a paginated report, or view the settings and permissions associated with the report. We won't be changing anything here, and instead we'll take a look at the options associated with the dataset. And much like with a report, there are a lot of options here, including one to create a report from this data, to delete the dataset, and also to configure its settings. Next, let's head over to the access options. And you can see here that this user does have the ability to grant access to other users, but these need to be members or below. So they can be members, contributors, or viewers. Closing out of this view, when we pull up the other options, we can see that a member has the ability to endorse an app. So this is the app associated with the workspace, and an endorsement effectively promotes an app as something which is important to its consumers, and it features more prominently in their homepage. From the menu options here, you'll observe that a a member also has the ability to unpublish an app, and towards the top right, there is also the option to update an app. And speaking of apps themselves, when we head over to the apps menu, now this user has the ability to access the Looney WS app from this view. So they don't need access to the URL alone in order to view the app. Let's click on this link, and sure enough, the user is directed to the app. And in fact, from the contents of this report page, we can confirm that all of the data is now accessible to this user Elroy, given that all 17 subcategories are now available here, and the top selling category is marked as phones, which was not previously available when Elroy was just a viewer, and row level security restricted this view to just office supply subcategories. Heading over then to the donut chart page, sure enough, this chart has been constructed with all of the data, and we can continue interacting with it in this view. So we now know that when a user is marked as a member of a workspace, they do have access to all of the data, and row level security does not quite apply to them. Heading back then to the Power BI Service main page, from the apps view, we navigate back to Workspaces and then over to the Looney WS. And then from here, let's access the report. From here, we can take a look at some of the additional menu items which are available for a report. Given that this user is no longer just a viewer, there is the ability to edit reports. Also, given that the dataset is now accessible, and for a sanity check, we can head over to the column chart and ensure that the edit permission is available here as well. Of course, you may go ahead and play around with the settings over here and maybe even make a change to this report. But once you're done, let's head back over to the Looney WS. And now it's time for us to modify the permissions associated with this user Elroy once again. And I'll just switch my window over to the one belonging to the user Diana. Just to confirm which user I'm currently signed in as, we'll pull up the menu here. And once we're satisfied that it is the owner of the workspace we're currently signed in as, it's time for us to make one more change to this Looney WS workspace, for which we head over to Access once again, and then over to the user Elroy, where we will change the privileges to Contributor. So Contributor is one level below a member in terms of the number of available permissions, and while a contributor does have the ability to add, modify, or even delete reports from a workspace, they don't have the ability, for example, to modify or create an app in the workspace, which we saw were options available to the member role. To test it out, I'm once again going to switch windows, and in the background, I have already refreshed this page where the user Elroy is signed into the Power BI service and is accessing the Looney WS workspace. And significantly, you can see that towards the top right, this user no longer has a button in order to create or update an app. This is a significant difference between a member and a contributor when it comes to a workspace in Power BI, where a member can create and update an app while a contributor cannot. However, a contributor can still, if you will, contribute in many different ways. For instance, a contributor can share the reports in their workspace, and then they can also access a lot of options from the menu, including the settings corresponding to the report. The same also applies to the datasets within the workspace, but let's now head over to the workspace level settings, where you can see that they don't quite have the ability to modify the name of a workspace, and then expanding the advanced settings, they can't really make any changes here as well, though of course they can view each of the settings. Heading over to the Premium tab, we can see that contributors can't really do anything to change the license mode which applies to a workspace, and later on we will see that this is something which admins can definitely change. And then over to Azure connections, and then expanding storage, well, it is possible to connect a workspace over to an Azure Data Lake account. So now we have some idea of what a contributor to a workspace is capable of doing. And once again, I'll confirm that I'm signed in as the user Elroy. And now let's click on the report, where we can still view the data here and still interact with the charts. You'll see above that the share button is activated, which means that a contributor is capable of sharing reports with other users. And then when we expand some of the menu items, well, a contributor can edit a report in order to change its contents and create new visualizations if they so choose. Alright then, now that we have some familiarity with a contributor, let's head back over to the Workspace page, and then the next thing we will do is to promote this user over to an admin, but for that, we will need to switch windows over to a current admin. So I'm in the window for the user Diana, and we'll head over to Access, where I'm going to now promote the user Elroy over to an admin. With this change, well, we now have two admins for this workspace. So when we hit close, let's confirm that I'm currently signed in as Diana, and will now switch windows where I'm logged in as Elroy. I have just refreshed the page in the background, which is why you will see that the Update App button now appears towards the top right, and significantly, the access to the workspace can also be set by this user now. Let's head over to it, and we can confirm from here that both Diana and Elroy are admins. And now that Elroy is an admin, well, this user has the ability to change the permissions of the user Diana, who is also an admin. Let's cancel out of this view. And now when we head over to the settings corresponding to the workspace, well, not only can this user modify the name as well as the description associated with this workspace, but significantly, you'll notice further below that the option to delete the workspace is now also available. Heading to the advanced settings, well, these can also be edited now. And then let's head over from the About tab over to the Premium tab for this workspace, where it is now possible for us to set the license mode and change it from Pro to Premium per user. And finally, when we head over to Azure Connections and expand storage, we see the same options as we did before for a contributor. So we have now explored the different degrees of permissions which are available to different types of roles for a Power BI workspace. To wrap up our demos related to user permissions in Power BI, we will explore one more feature when it comes to row level security. When we previously implemented this feature, we made sure that each category manager only had access to their own categories. So Diana could only access furniture related orders and sales, Elroy could only view office supply details, and Charles could only access technology related orders and sales. However, rather than a one-to-one relationship between users and categories, what if the relationship was many-to-many instead? So for the sake of our example, let's assume that the user Elroy has been given a promotion. Elroy not only manages office supplies, but also takes care of furniture and technology-related sales as well. So, how can we ensure that Elroy has access to those two categories within the dataset? Well, for that, I have pulled up the Excel file where we store the category manager's information, and we're now going to modify this and then pull in the updates into Power BI Desktop. So the edits which I'm going to add here include another row corresponding to the user Elroy, and in this case, Elroy should also have access to the furniture category in addition to the office supplies which he previously did, and we'll add in a third row for Elroy where the technology related sales will also be accessible. So as things stand, Diana will only have access to furniture related data, Charles can only access technology related information, but Elroy will be able to view orders and sales details related to office supplies, furniture, and technology. So, once the edits in this workbook have been made, let's save things down, and it's now time for us to pull this updated information about category managers into Power BI Desktop. So we switch over to that application, and we're currently in the data view, but can make the switch to the model view. So in here, we have already modeled a relationship between category managers and orders. More precisely, this was automatically detected and applied by Power BI itself. When we open up this relationship, we can see that this has mapped category in each of the tables to one another, and then the nature of this relationship is many to one. However, before we pull in the new information, From the updated Category Managers workbook, we need this relationship to reflect the fact that the nature of the relationship has changed. So it is no longer many to one, but many to many, since we can have multiple managers mapped to multiple departments, and similarly, multiple departments may have multiple managers pointing to it. So once we change this cardinality, well, in this case, we are notified that, as things stand, this relationship need not be many to many, and we should use a lower cardinality if possible. In our case, however, we know that the relationship has changed, so we go ahead with this modification. And then following that, we need to reload the data from the workbook category managers into Power BI desktop. And for this, we can head over to the options for the category managers table, and keep in mind that the storage model is currently set to import, and then we choose to refresh the data from the data source. Once we do that, in a few moments, we should see this refresh success message, and keep in mind that had you not altered the cardinality of the relationship from many to one to many, you would have instead seen an error message. Alright then, now that we have successfully updated the relationship between orders and category managers and pulled in the new data, let's head over to the data view and confirm that category managers now has 5 rows of data, with Elroy mapped to each of the 3 different categories. Let's quickly head over to the report view and take a look at what we see when all of the data is accessible. When all 3 categories are in view, then the 17 subcategories are also visible. And then switching from the column chart over to the donut, we can see the distribution of sales across the 4 different regions. Alright then, heading back to the column page, it's time now for us to test the permissions of Elroy. So we head over to the model view. We will need to head over to the view as feature and then choose to view as another user. We supply the UPN for Elroy, enable the user sees own data role, and then hit OK. Now when we head over to the data view, it is the 3 rows corresponding to Elroy which we can view here. So we only view a subset of this table. However, from the report view, all of the 17 subcategories are available to us, given that Elroy has access to each of their parent categories. Switching from the column view over to the donut chart, the story is much the same here. All of the data is accessible, so the distribution of sales across the regions is exactly what we saw previously when all the data was accessible. Alright then, so we now know how to assign users permissions by means of a many-to-many relationship with the fact table in our schema. Let's now stop viewing as Elroy and then heading back over to the data view. Sure enough, all 5 rows are visible. But now, let's consider that we want to once again restrict Elroy's access, but not to a single category, but 2 different categories. So let's just say we made a little mistake, and that Elroy's promotion does not mean he is in charge of all 3 categories, but only in charge of office supplies and furniture. Well, for that, we will need to make a little change over to the Excel file where the category manager data is stored. So assuming that Elroy should not have access to the technology category details, we can just eliminate this row from the Excel file. So once this has been cleared, let's save down the change to the file and then heading back over to Power BI desktop and over to the model view, we can now choose to refresh the data for category managers from the file over to the table. Note that the relationship is still many to many, so we don't need to make any changes to the cardinality of the relationship here. Alright then, now that category managers has changed, let's see how this affects the view which is available to Elroy. First though, we quickly head over to the data view and confirm that there are now 4 rows in category managers, and then back to the model view where we choose to view as Elroy. For this, of course, we will need to set the other user option, specify the username for Elroy, and enable the user sees own data role. Then when we hit OK, well, we head back to the data view where 2 out of the 4 rows are now visible, furniture and office supplies, and heading over to the report view, well, we can confirm that the view is different from what we saw previously. While we were able to see 17 different subcategories before, we are now down to a total of 13. For instance, the top selling subcategory of phones is not visible here, given that that belongs to the technology category and Elroy does not have access to that data. And then heading over to the donut chart, well, the distribution of sales across the different regions has also changed on account of Elroy's varied permissions. While in the complete dataset, the share of the West region sales was about 38%, it's about 45.5% when the technology category is no longer in consideration. So you now know how row level security can be adjusted so that the relationship between a class of users and the data in a fact table is not one to many, but many to many. If you have any experience with software development, you will have recognized that building a Power BI report and creating an app out of it shares a lot of similarities with developing an application in any programming language, such as Java or Python. We will now see how that concept effectively gets extended when we deploy our Power BI workspaces to pipelines. Do note that you need to be an admin of a workspace in order to work with pipelines, and in my case, I'm signed into Power BI service as the user Diana, who is the owner and admin of the workspace called Lineage WS. Pipelines are a feature which are available in the Power BI service, and from the menu on the left, you'll observe that there is a deployment pipeline section. Let's navigate over to that, and if this is the first time you are setting up a Power BI pipeline, you should see a page such as this one, where there are no pipelines listed, but there is an option to create a pipeline along with a description of the steps involved in using one. So, these steps pretty much summarize how pipelines are used. We create a pipeline, we map a workspace within our Power BI service to the pipeline, and while doing so, we assign the workspace to a specific stage in the pipeline, either development, test, or production. Just like with application development, at each stage, different types of operations can be performed. So, step 3 lists that it is possible for us to develop and test our pipelines. So, in the development stage workspace, we would collaborate with team members and then build our reports. Then we deploy it to the next stage, which is test, and then test our reports. And the developers and testers may be different sets of individuals. Finally, we move on to step number 4, where we deploy our workspace from test to production, and this is where we are ready to share with the end users. Alright then, things may seem a little hazy right now, so we can just move on and create the pipeline so that things do get a little clearer. So when we choose to create, we will first be prompted for a name for the pipeline. I'm just going to give this a generic name of Lunicorn pipeline and then choose to create. And at this point, you'll observe that the 3 different stages for the pipeline have already been created: development, test, and production. Note that these are the only 3 stages which are possible in a Power BI pipeline as of this recording. Now then, it is time for us to map a workspace first to the development stage before we can migrate it to the test and later production stages. So, let's choose to assign a workspace, and at this point, we are notified that there are no workspaces for us to map to the development stage. The reason for this is that in order to map a workspace to a pipeline, we must configure its properties so that it resides in something called a premium capacity. As the name implies, this is something which is only available to premium users of Power BI, but let's see how this can be set up. First, of course, let's cancel out of this particular notification, navigate over to Workspaces, and then from there, select the workspace which we created before. In my case, this has a name of Luni WS. Now we need to head over to the settings for this workspace, and there is a shortcut to this from this menu. So we can just navigate to settings here, and sure enough, the settings pane pops up on the right. From here, we navigate over to the premium tab, and this is where we have the ability to set the license mode which applies to the workspace. So you'll observe that the options which are now available here are Power BI Pro and Premium per user. The main difference between these two license modes is that Premium per user offers additional capabilities which are related to artificial intelligence and also pipelines. If you have opted for a trial of Power BI Pro, you will have the option to set a workspace in Premium per user mode, which allows it to be mapped to a pipeline stage. So let's go ahead and set this particular license mode for this workspace, and immediately you'll observe that a few additional options become available. First of all, there is the default storage format, which is set to small dataset storage format by default. This means that the size of the dataset is limited, and in Power BI Premium, it is possible for us to work with larger datasets. Those details, however, are beyond the scope of this course, so let's proceed to convert the license mode for this workspace so that we can use it in our pipeline. So when we save, let's confirm that we wish to continue with this. And now from the deployment pipelines page, we will try to assign a workspace to the development stage. Now we have the option to assign a workspace to the different stages of the pipeline. From the drop-down menu, let's select LuniWS. And once we do that, well, from the radio buttons, let's make sure that it is development which is selected. And before we assign the workspace to the pipeline, let's quickly take a look at the description of the different stages to get an idea of how these really work. When a pipeline is in the development stage, it means that it can constantly be changed and there may be multiple collaborators working on the workspace. They could be adding new reports and datasets and also modifying existing ones, and may even conduct reviews much like a code review in software development. Once you're satisfied with the features of the workspace, it can be migrated to the test stage, and this is where potentially a separate testing team can play around with it by taking a look at not just the features, but also evaluating the performance and then verifying that everything is in compliance with the intended goals of the workspace, such as all of the business and technical requirements being met. And then all of the workspace content can be migrated to production. This is where no changes will be made, and it is only meant to be shared with the end users or consumers of your Power BI workspace and apps. Alright then, let's continue with this assignment of the LuniWS to the development stage of the pipeline. And the assignment is a success. We can already view a little preview of the contents of the workspace over here. We can see that there are 0 data flows associated with the workspace. There is one data set. There is also one report and no dashboards at the moment. We also have the option to show additional details, and this is where we can access both the data set and the report within the workspace. In fact, we can also configure each of these from this view. For example, expanding the menu for the report, it is possible for us, for instance, to view the lineage view for the report. A lineage view effectively allows us to see what a particular report has been built out of. Let's navigate to it to understand why it is important. And you'll notice that in this view, we can see exactly what a report is made up of. On the left are the two files which are loaded into Power BI Desktop. So these are category manager.xls and orders.xls. And then we can see that both of these files came together to create a dataset. This is a dataset called Workspace and RLS, and it is that dataset out of which we have created this Workspace and RLS report. The benefit of this lineage view is that it is possible for us to trace exactly what changes might occur if we were to change any of these components. So for example, you'll observe that there is this feature for us to view the impact of a particular file across all workspaces within a Power BI service. So if you are using the same file across multiple datasets and then across multiple reports, and these map to multiple workspaces, you will know exactly which of these will be affected if this origin file were changed. Next, let's take a look at the lineage view which is available to highlight the lineage of this particular file. And we can see that it takes us to the Workspace and RLS dataset and then the report of the same name. The lineage view is not just available for the files themselves, but also for the dataset which is created from files. So now that we know what the lineage view of a workspace looks like, well, let's switch back to the default of a list view. And this is something which we are already familiar with. Before moving on, I'll just draw your attention to the top of this page where the name of the workspace, LuniWS, appears. You will now observe that this has a diamond logo to its right, conveying that this is now a premium workspace. And then right next to it, there is the development badge, pointing out that this is also mapped to the development stage of a pipeline. Alright then, let's head back over to the lineage view to explore some of its other features. We did discuss the fact that it is possible for us to assess the impact of a particular file across different workspaces. So let's take a look at this view. And at least in our case, the view is rather simple. This particular file is part of just a single workspace. It is not part of any data flow, and it is used to make up one dataset. The name of the workspace and dataset which this file is mapped to are available below. Let's cancel out of this view then, and following that, take a look at the impact view for the dataset. And we see something similar here. This dataset is mapped to a single workspace and is used to compose one report, and the name of the workspace and the report are visible below, along with the number of viewers and views corresponding to the workspace and report. Scrolling further along over here, we can also see the number of dashboards which the dataset is associated with, and at least in my case, this is 0. And in case you're wondering why the number of views shows up as 0, well, this is because it excludes the current day from the analysis. And in my case, the workspace and the dataset has only been created a few hours ago. Alright then, now that we're familiar with how to create a pipeline and map a workspace to it, and also how to explore the lineage view of a workspace, in the next video, we will complete the building of our pipeline and then see how we can deploy workspaces to the test and production stages as well. In the previous video, we started off building a pipeline and we left things off where this LuniWS workspace was mapped to the development stage of a pipeline. Now, to navigate over to the pipeline which this workspace is a part of, we can hit the View in Pipeline button towards the top of the page. But since we already know which pipeline it belongs to, we can just head over to the Deployment Pipelines menu and then choose the Lunicon pipeline which was created previously. So we're back to the pipeline view, and as of this moment we just have a single workspace mapped to the development view, which means that this workspace and all of its resources are at a point where a lot of changes can be made. Since the workspace is considered under development at this point, well, you can go ahead and share this workspace with a number of additional developers. So this is where you can navigate to workspace access and grant the required level of access to different members. Once a workspace component such as a report or a dataset has been modified, you will need to update the workspace's app with that. So you have that option here. And then we could of course view the app as well. Alternatively, if this workspace should no longer be part of the development stage of this pipeline, we can simply choose to unassign it. In our case, however, let us assume that all of the development work for this workspace is complete, which means that it is ready to move along to the next stage of the pipeline, and this is the test step. You'll observe that no workspace has been mapped to the test or production stages, and in fact, it is not possible for us to create a separate workspace and assign them here. This is because the test and production stages must be derived from the development stage. And if you are familiar with development, testing, and production environments from application development, you will know that it is important to keep each of these environments in sync. So, the only way now for us to create a test workspace which maps to the test stage is for us to deploy our development workspace. When we do that, well, this is where a new workspace has been created out of our development workspace, and this has been mapped automatically to the test stage of the pipeline. So, all of the resources in our development workspace have now been migrated to this new test workspace, and it is now up to us to share the workspace with the reviewers and testers to make sure that all of the technical as well as business requirements for the workspace have been satisfied. Now a little notification has popped up that a test stage workspace has been created and we can navigate to it from here. Alternatively, I'll just pull up the Workspaces menu where we can confirm that this Looney WS test workspace has been created. And while we can navigate to it from here, I'm just going to make use of the shortcut which came up in this notification. And you'll observe that this is pretty much a carbon copy of our development workspace. Towards the top, however, you can clearly see that this is mapped to the test stage of a pipeline. At this point, just as with any other workspace, it is possible for us to configure access to this test workspace and then make sure that the right people are able to view it and then potentially make changes if required. Alright then, now that we know what this workspace looks like, I'm just going to go on and close this tab where the workspace view has popped up. So we're back to the pipeline view and expanding the show more menu. Once again, the dataset as well as the report in this workspace can be accessed. We have already seen that it is possible for us to access the menu corresponding to each of these resources. So over to the dataset where we can delete it from the workspace and pretty much treat it as a dataset in any other workspace. Now, however, let's head over to the report options and take a look at a new feature we haven't covered yet, which is the usage metrics related to the report. And from this view, well, it is possible for us to navigate to the metrics report which has been generated now. And this is what the metrics view looks like. So you'll observe that it is possible for us to take a look at how many people have accessed our report in terms of the views per day as well as the unique number of viewers per day. Towards the top right, the total views as well as the total viewers will also be given to us, along with a rank which is calculated based on other reports in our own organization. And then the list of users can also be accessed from the bottom right. Of course, in our case, all of this is blank, given that our workspace is brand new. Towards the left, the distribution methods will point us to exactly how the report was accessed. Were the members given access to the workspace itself, in which case they navigated to the report? Was the report shared with an end user rather than them accessing it via a workspace, or did they view it from a mobile app? The platform view tells us whether they accessed it from the Power BI service or a mobile app. And for a multi-page report, you can also examine which of the pages were viewed by the users. So we do get a lot of granularity in terms of the usage metrics. So now that we have an idea of the usage metrics corresponding to a report, let's just head back in our browser over to the pipeline view. And at this point, let's assume that all of the testing work is now complete for the workspace and we're ready to share it with the end users and final consumers, in which case we can just choose to deploy the test workspace and this will be migrated over to a new production workspace. In a few moments, we are notified that the deployment is complete, and from the workspaces view, we can confirm that a new production level workspace has been created. And then from the shortcut, when we navigate to it, sure enough, this is a carbon copy of our workspace in the development and test environments in terms of the fact that it contains a single report and dataset which have the names workspace and RLS. But of course, from the name of the workspace at the top, along with the little badge next to it, we know that this is a production level workspace. We will now explore the concept of endorsements in Power BI. And for that, well, let's put ourselves in the shoes of a consumer of Power BI reports. In a large organization, it is possible that such a consumer has access to a wide variety of reports coming in from different departments and for a different set of projects. So let's imagine that the user Elroy, who I'm currently logged in as in the Power BI service, happens to be such a consumer, and in the home page, well, a number of such reports will be available. Now, if the management in the organization wishes to draw the attention of the consumers to specific reports which may be more important than the other ones, they can endorse it and make sure that it appears within this recommended section when the consumers log into their Power BI service. So, before we get to how exactly we can endorse a Power BI report, we can explore some of the different options available from this menu. So, of course, we can head over to the Workspaces section in order to navigate to one or more workspaces which may be accessible to the user. Each user will have their own My Workspace. However, to access another workspace, they will either have to create one themselves or have another workspace shared with them. Now, previously, the user Elroy on my machine did have access to a workspace, but I have ensured that that access has been taken away for now. From the Workspaces view, we can head over to My Workspace, which in the case of this user, does not really have any resources just yet. Next, when we take a look at Shared with Me, if any reports or dashboards have been explicitly shared with the user, this is where they will be accessible. And then we can move along to the Power BI apps. Once again, once an app has been explicitly shared with the user, or they have been marked as a member or a contributor to a workspace which has a published app, well, this is where the app will be made available. Let's move on then back to the home page, and from here, a user will be able to navigate to recently accessed resources, which can include workspaces, reports, and dashboards. They can also mark specific resources as favorites, and then they can also navigate to their own apps. So from the homepage view, a user is able to access not just their own apps, but also their more recently accessed resources such as dashboards and workspaces. But once again, you can imagine that if this user has access to multiple reports and dashboards, the homepage could get a little crowded, in which case, reports which are important and which have just been published may not really feature, or at least will be difficult to search. And just to reiterate, our goal is to make it easy to navigate to important reports and dashboards by promoting them and making sure that they feature in this homepage. For that to happen though, we need to be either an admin, a member, or a contributor of the workspace containing the report. And I'm currently signed into this window as the user Elroy, who, as things stand, does not have access to any workspace containing a report. However, I'm now going to switch windows over to where I'm logged in as the user Diana in my organization, and Diana happens to be the admin of the Looney WS workspace, which was created earlier on. And significantly, this workspace includes a report along with a dataset. So, how can we ensure that this workspace and RLS report features in the home page of an end user and is also marked as promoted? Well, first of all, we'll need to make sure that the consumers of this report do have access to it. And one way to ensure that is to head over to the access settings for the workspace itself and then go on and add the different users who require access. So I've just added the user Elroy once again, and we'll set the permissions of this user to viewer. Once we hit add, well, we now have two different users who have access to this report, including the admin Diana and the viewer Elroy. Now we can just click out of this, and then it is good practice to ensure that each user only has access to their own data just in case row level security has been set up. This is something which can be applied at the dataset level. So let's head over to the options related to the dataset and then over to security. From here, well, at least in my case, there already is a role called user sees own data, which was previously used in order to set up and then test out row level security. To this role, I'll once again add the user Elroy. And once this role has been enabled for this user, we can just hit save. Alright then, let's head back over to the home page for the user Diana. And at least in here, you can see that Diana is only able to view the frequently accessed workspaces and reports under the recommended section. And significantly, this does include the workspace and RLS report. Now, let's head over to the report in order to modify its settings, for which we head over to the workspace containing it. And then from here, we just expand the menu for the report and then navigate to Settings. This is where we are presented with a few options. We can set a name and description along with a list of contact persons corresponding to the report. But what we are interested in now is further below under the endorsement section. There are different types of endorsements which are possible in Power BI. One of these, of course, is none, where there is no endorsement whatsoever. The next one is promoted, and this is what we are going to explore in more detail. This is where we effectively tell the consumers of this report that it contains something important and interesting which they should check out. This is something which is relevant to their work directly, but could also be a report which has recently been updated with new data, in which case, users who have access to the report may be interested in knowing how things have changed with the new data. The third way to endorse a report is to certify it. Now, certification in Power BI is a much more complex feature, and this is something which needs to be explicitly turned on. However, once a report has been certified, it effectively means that it has gone through a rigorous certification process within the organization. For now, however, we will be happy enough just to promote this particular report, and automatically the feature on home option has also been checked. So both of these features are a little different, and we will soon see why. So let's save down this little change to our Workspace and RLS report. And now when we scroll along over to the right, we can see under the endorsement column that this has been explicitly marked as promoted. Now to see the effects of this on the viewers, first, let's stick with this admin user of the workspace and the owner of the report and head over to the home page where, well, we can still see the report as we did previously. It features under the recommended section, and we can also view it in the list which follows below that. So the workspace and RLS report can be viewed further towards the bottom, at least in my case, since I have accessed other resources after that. And now to see the effect of the endorsement on a viewer of the report, I'll just switch my browser window to one where I'm logged into the Power BI service as the user Elroy. So we previously saw that under the recommended section, this user could only access their own workspace called My Workspace, and then some of the standard Power BI resources which have shown up here. But for the endorsement to take effect in this window, we will need to reload the page, and we can now see that the Workspace and RLS report shows up in here. Significantly, there is a message which conveys that it is the user Diana Duncan who explicitly featured this particular report, and this is thanks to that user setting this report to feature on the home page of its users. Alright then, what is the effect of the promotion of this particular report? For that, we'll need to scroll further down, and you might see the report featured here. If not, you can navigate over to the workspace in which this report is available, and to view the endorsement from this view, we can click on See All, and then scrolling a little further to the right, we can take a look at the endorsement. So the report now shows up as promoted in this view. So this user will now know that this report has been marked as promoted and potentially is more important than the others which are not quite promoted. Such a user is more likely to click on this report and analyze its data. Alright then, let's switch back over to the home page where keep an eye on the fact that this report now features under the recommended section. Now let's switch windows back over to Diana, who of course is the admin, and I'll just confirm that I am in fact logged in as Diana here. And now let's head over to the settings corresponding to our report. The change which we are now going to introduce is under the endorsements once again. However, we will leave this report as promoted, but will uncheck the box in order to feature it on the home page of its consumers. Then when we hit save, well, to view its effects, I'm going to switch windows over once again to the user Elroy, who of course could see the Workspace and RLS report under recommended. But once refresh is now hit, well, that report no longer features on the home page. However, it is still marked as promoted. To wrap up the demos of this learning path on analyzing and interpreting data in Power BI, we will explore the Performance Analyzer feature. As suggested by the name, this is something which can point us to those components of our visualizations and reports which may prove to be performance bottlenecks. In this demo, you will observe that I have a report up, and this is one which we have used previously. The first page in this report contains a column chart, and the second one a donut chart, and we will soon add a third one which we will use to analyze the performance of our visuals. We will soon see that the Performance Analyzer gives us very detailed information on what exactly is going on under the hood of our visualizations and does point towards how we can improve its overall performance. Alright then, let me first expand the visualizations pane, and then we'll also expand the fields pane. Just as a quick reminder, we have constructed this visualization as well as the donut visualization on the next page using a dataset containing two tables: orders, which is a fact table, and category managers, which you could say serves as a dimension table if you could model this on a star or snowflake schema. Given that there are just two tables, those schemas don't really apply here. Alright then, let's move on to the Performance Analyzer feature, for which we will first create a new page in this report. Then I'll just go ahead and rename this page, and the name which I'm going to supply is losses, because in here we will analyze those orders within the table which resulted in a loss for our fictitious US superstore whose order information this table contains. Just to quickly remind you of what our tables contain, Category Managers has just two columns. However, we won't really be using this in this demo. Let's head over then to orders, and you'll observe that there is a profit field within this table which conveys the profit generated by each line item, and we will be focusing on those line items where the profit is negative. So how exactly will we analyze the losses? Well, let's start off by creating a new measure, for which we can head over to Table Tools and then choose the option to create a new measure. Then once the formula bar pops up, we'll set a name for this measure, which is losses, and this is the formula we will apply. We will make use of the calculate function, and we will use this to sum up from the orders table the contents of the profit column. So we will be summing up the profits, but not all profits, only those where the profit column has a value which is less than 0. So this is the full formula we will use in order to create this measure. So the filter context which we have set here is that the profit column is less than 0 in the orders table. So we will be focusing on the loss making line items, and then we will sum up these losses. However, with any measure, this is something which will happen within a query context. Alright then, now to use this new measure, let's add a new visualization to this losses sheet. Specifically, I'm going to add a clustered bar chart, and what we will plot here will have the subcategory column within the axis. So this is going to serve as the y-axis, and what we will plot as the values are the losses. So I'll just drag and drop this measure over to values, and this is what we end up with. You will notice that the 0 point is towards the right of this visual, and the bars extend towards the left. This of course is because each of the bars now represent a negative value, since it is only the loss-making line items in our table which are considered for this visual. Now, given that our focus in this demo is to analyze the performance of the visual, let's not focus too much on interpreting the data. However, just for a quick summary, you can see that it is binders followed by tables which generated the most losses overall. Alright then, let's move along and add one more visual over to this report page, specifically a card visual. And while the bar chart which we have used gives us the losses for each subcategory of products, in the case of this card visual, we will simply render the losses so that we can see the sum of all of the loss-making line items. For the next step, let's move on and add a slicer to this report page. So I'm just going to click on the slicer, and the field which this will map to is the region field. The contents of the slicer shows us that there are 4 distinct regions within the orders table. I'll just quickly adjust the text sizes for the slicer so that it's more clearly visible. And once that is done, well, we now have three different pieces of visuals in this report page. There is a bar chart, a card visual, and a slicer. As with any Power BI visualization, it is possible for us to interact with each of the charts within this report page, and this dynamically alters the contents of the other chart. Since when we click on either the slicer or one of the bars in the bar chart, we effectively set a new query context. So for instance, when we select the south region from the slicer, the bar chart automatically adjusts to show the losses incurred within the south region, and the card visual also shows us the aggregate losses in that region. All of this, of course, you should be familiar with by now, but what we are going to figure out is whether these constant interactions may affect the performance of the visuals. Given that our dataset is rather small, and given that the tables have been loaded in import mode, well, there really is no bottleneck in performance. However, let's try to see how the Performance Analyzer tool can be used in order to identify potential bottlenecks. For that, we head over to the View menu, and there is the option to bring up the Performance Analyzer. Once that is done, a new pane pops up for the Performance Analyzer. But of course, this means that the visualization itself has shrunk a fair amount. So I'm just going to minimize the visualizations and fields menus so that the visuals themselves are a little more clearly visible. And then looking at the Performance Analyzer pane, you will notice that there is a button with the label Start Recording. This is where we can effectively turn on the Performance Analyzer and then go on and interact with our visualizations. While we do that, every single operation which incurs some cost in terms of performance will be recorded, and metrics corresponding to those will be generated. To see this in action, we can of course go on and hit the Start Recording button. Once we do that, well, we can go on and interact with our visualizations, but to get a sense for how long the visuals themselves take to load, let's choose the option to refresh the visuals. And once we do that, well, some data has popped up within the Performance Analyzer pane, and we can now drill down and take a look at what metrics have been generated. At a high level, you'll observe that there are line items here for each of our three visuals, starting with losses by subcategory, then the card visual, and then the slicer. We can see that losses by subcategory took 86 milliseconds to load, followed by 101 milliseconds for the card, and then 117 for the slicer. If we expand losses by subcategory, we can take a look at the amount of time it took for the three different steps involved in loading this visual. The first of these was the execution of the DAX query, which of course computed the losses for each subcategory. So this only took 8 milliseconds to run. Rendering the display then took 11 milliseconds, and all of the other steps took 66. So it is clearly other which has taken up the bulk of the time in here. Looking at the card visual, well, the DAX query took just 14 milliseconds to run, and this of course simply computed the aggregate of all of the loss-making line items. Rendering the display took 10 milliseconds, so it took just a little less than the bar chart, and then everything else in order to render the card took 77 milliseconds. Expanding the slicer, again the DAX query and the visual display steps took just a fraction of the overall time. Alright then, let's go along and play with our visualizations. I have just clicked on one of the bars in here, and this corresponds to the step cross-highlighted, which appears within the Performance Analyzer pane. I'm just going to record a few clicks in this bar chart, and of course, the card visualization changes accordingly. And now when we scroll down in the Performance Analyzer pane, you'll observe that for each click, there is a cross-highlighted step which appears. This causes the card visualization to re-render, and in fact, the query context which applies to the slicer also changes. So we now have an idea that we get a detailed breakdown of the various steps involved in loading a visual, starting from the DAX query over to rendering the display when we make use of the Performance Analyzer. I'm just going to refresh the visuals once more so that we start from scratch. And now we'll interact with the slicer. Again, you will notice that a step changed a slicer now appears, and this has resulted in the slicer itself being re-rendered. The losses by subcategory chart also gets generated once more, as does the card visual. What this makes abundantly clear is that each interaction with the slicer does involve a performance hit, which is why we need to be a little careful when using a slicer within a report. Once again, for each of the steps here, a detailed breakdown of the various operations involved is available. And now that you have a fair idea of how the performance analyzer works, well, it's fair to ask the question, how exactly does this help? Well, as I'd mentioned, in this case, we're working with a small data set which has been loaded in import mode, in which case there is not much of a performance hit. Well, consider the fact that you may have a very large data set. Datasets up to 10 gigabytes are supported when using the premium version of Power BI, and measures which are more complex than the one we have used, say measures which involve multiple filters being assigned and also more complex operations, will take longer to run. The performance analyzer, as we have seen, allows us to view a detailed breakdown of the different steps when loading a visual, and this includes a DAX query. When interacting with the slicer though, you will notice that there is no DAX query step here. So you now have an idea of how the performance analyzer can help us identify where exactly our visuals are slowing down. Keep in mind that if you use the direct query storage mode, the performance analyzer will be able to tell you how long it takes to access the data which lies beneath the report. Once you have identified the bottleneck, well, taking corrective action becomes much simpler. If it's a DAX query slowing you down, you may need to simplify or optimize it, potentially by using variables. Or if it's visuals which are the bottleneck, well, you can consider including fewer elements. This course delved into involving other people in your Power BI reports, whether they are collaborators in report development or the consumers of your analysis. You kick things off with the building of a report which is configured with row level security so that viewers only have access to data which is within their scope. You tested out the views of the report in Power BI Desktop before publishing it to the Power BI service and confirming the level of access there. In the Power BI service, you also covered how you can share your workspace with teammates and other collaborators and the different roles they can play along with the varying degrees of permissions. You got to see how row level security only applies to users with the viewer role and got to see the different options available to workspace members, contributors, and admins. You then explored the pipeline feature, which helps streamline report deployment and got to see how workspaces can migrate from one stage of the pipeline to another. Finally, you covered some of the useful features available in Power BI when it comes to sharing and enhancing the performance of reports, such as adding endorsements and using the native performance analyzer. Having completed this course, as well as this learning path, you can consider yourself a master data analyst and a Power BI guru. You are all set to take the DA-100 certification exam and can then apply the skills you have acquired to build interesting and insightful reports which your end users can use to make important business decisions.